Yes, thank you. Thank you very much for the invitation. I started to see you in New Zealand yesterday, and now we are here. I see you are still alive.
Do I look tired? Do I look tired? Do I look like I should go to sleep? No,
a little bit.
Oh my God! Oh no, that's the worst thing you can tell me.
But yesterday I started seeing you, and you remain very motivated. So that's
of course.
That's the most important, yeah. So my idea is to speak about how we work with photonics in Brazil. I go a little bit further. We work also with smart systems. So the idea is how we connect photonics with smart systems to make good solutions that work with photonics here in South America. I was very happy to see on the presentation of Portugal that our bridge was there, and a good example that photonics can be used for instrumentation. That are the things we do. Okay, let's tell a little bit about us. We are a science foundation, CERTI. We work with development of product systems, hardware, software. Here are some examples. We develop complete products, more electronic products. So you can see our voting computer. You can see digital signal processing for television. You can see here the Brazilian standard for digital TV. So we are very skilled developing complete systems. We do also consultancy, so we can help others to improve the solutions, to do some strategic analysis. We help our customers to build up big projects like a technology park. And of course, we do here, and I will tell a little bit about this, we do photonics development in Brazil. Now, it was interesting to be on the beginning of the presentation, as we saw New Zealand, Australia, and places like this. And we are a little bit similar. We do the things more integrating. Like I saw now on Iran, we have to work with integration. And in this case, we have to do a job on system level. Here, an example of a photonic product we developed here in Brazil. Here we had a local company who told us that they want to make phototherapy on newborns. So we developed end-to-end a solution like phototherapy for a newborn. In this case, you have to take care a lot about certification. So,
Manuel, were you planning to show us some slides?
Yes. Oh, right. Sorry.
No, it's
sorry,
okay. You were so convincing. We were listening and we're thinking, what a beautiful story. And at some point, we realized maybe he wants to show something.
Excuse me.
Not a problem. You were so good that we were just listening to the story and it was fascinating.
Okay, sorry. Now you have also some slides. Here you have the application what I was telling about. Here we have a typical product we work for. That is a medical equipment producer, a local one. They asked us how I can do phototherapy for newborns. Of course, we look at for the complete cycle. We have very, very mature processes, how we can go from the idea to the introduction in the market. So we have to think about the photonic solution itself. In this case, it is a LED, the wavelength, the power, everything you need. But we have to look also for the market. We have to look for the business. We have to look for the software. And of course, one of the most important parts is the certification. So in these cases, we make the complete solution together with our partner. In this case, the partner is a local company who wants to put photonics inside a product. Okay, the case here is who are our customers and what they need. And we discovered we need manufacturing. So we also do the complete manufacturing for the final solution that our customers ask for. We do mainly electronic assembly. Of course, inside electronic assembly, we have to look for the components. In this case, we have, for example, a solar panel. Here we have a customer of us that we developed a complete solar panel. And this solar panel had a failure. The failure was the electrical interconnection. So we got here on a tomograph and look at the failures you have on this. Here we have the planicity of an electronic component. This shape was not okay, so we improved the analysis and we improved the process to have a better shape for the component, and then the things work. As you know, the things have to be very, very integrated and working together to have a good final solution. We do the job for many local companies. Maybe you know some of these companies that are the local ones. Here, for example, that is a French company that's here in Brazil doing oil and gas, but they are Brazilians. So we learned how to transform the demands of the industry in solutions. I can show you also the international companies. This one, I believe you know very well, car makers, energy, healthcare. So we develop different solutions for them. The big question for our speech today is the challenge of doing innovation in emerging markets. So I'm very happy to be participating, and it was possible to see some of the presentations before me. And we have some of the countries that are emerging inside the EPIC. And here we have to look for different challenges. We have to look for the challenge of supply chain, regulation, not so much players. We are bureaucratic. Many of the emerging countries have some old bureaucratic structures. We have taxes. We have not so big value perception for local partners. So Brazil is not known as a photonics development place. Sometimes we have short-term oriented business. We have to look for complementary competences. And here, the most important point, we have to look for the culture of innovation. So how we do this, and here we have a happy example. This airplane cockpit is completely developed in Brazil. That's a company we work together, Embraer. And it works. We can do with these challenges the innovation. And yes, how is the process? How is the model and how is the process? Our model we work with is that we believe a lot that institutes, you have examples of Fraunhofer in Germany, we have the MIT, we have the university, can work together with an organization like us, that we can connect scientists, students, researchers, partner of our customer, and our own team, and make a good common workforce that makes the things working. Here we have some examples from partners. There are not photonics, it's more telecom and semiconductors. But our main model is how we can put together suppliers, how we can put together the partners and the scientists to develop a solution. This we do with a process. So we are already 30 years working on the designing of this process. So we look from the business opportunity, from the concept, from the requirements for the prototyping, product development itself, validation tests, to have a good product solution working. We have to be more disciplined as some places in Europe and United States, as our resources on average are on only 1/3 or the half of the resources we have in international level, like United States, like Europe. So we have to be very, very organized and disciplined to manage this process and to have a good product at the end. We have to work inside an ecosystem. Here we have examples. You cannot do everything alone. You have to do the job inside an ecosystem. Here we have the local ecosystem of some institutes nearby us, like here our university that do the research. We have the development itself we do, and we look also for startups that they can launch the product in the market and start having revenue to have a sustainable solution development. Of course, some established companies also can make some investments to improve the growth of the company here. And a big remark, we have to work in an ecosystem. The good question you make, what we can do together, that is working inside an ecosystem. The first example I will do about ecosystems, one ecosystem, of course, we have here is EPIC, but we have also a local ecosystem, the Brazilian Society of Photonics. So we have good photonics developers. If you want to stay in contact, please, we can help the contact. I am a member of the council of the Brazilian Society of Photonics. And it's very interesting that we can work together in photonics locally and worldwide. Here, invitation, we transferred our Congress from October this year to May. So please put on your travel agenda. I hope next year we can travel again, that we will have a Congress in São Carlos, São Paulo, from 31 of May to 2nd of June. The submission is far away. You can do it in December. Please, that's the first level of ecosystem we can connect you. The second level I want to tell about, we believe a lot on international cooperation. We run it already, international cooperation with Germany, in special the region of Berlin. In this case, we had a very good support from some agency. It was Berlin Partner, it is the program Phoenix, the city of Berlin. And here we have the elements we see as important to connect international ecosystems. In this case, the interesting conciliation of companies, R&D institutes, and the support of the government, we call it 2+2, is for us one of the best ways of doing development of complex system solutions, looking for international cooperation and building this bridge with these elements inside projects we call 2+2. So we need one company at least, one R&D institute at least of both sides. And in this way, we can work internationally very well. Some examples how we managed this kind of developments in photonics. We worked on the topic organic LED in the past. In this case, we worked with institutes and companies in Germany and Netherlands. So we developed complete solutions. In this case, the critical component, the thin film, and these things were made by partners overseas. But we got the specification, we got the product, we developed the assembly, we developed the use case. And that's very interesting that this worked. The next one we worked on printed photovoltaic panels. So we also work it internationally, in special with Germany, the company Heliatech in Dresden, how we can assemble a complete solar panel. In this case, we made this supported by our local bank, the development bank BNDES. And so we also learned a lot about how to make sustainable projects that later you will have a factory that can produce the product in places like Brazil. If someone in this EPIC group is looking for photovoltaic, we are investing a lot in photovoltaic in Brazil. Here, an example, we tested 8 different types of photovoltaics inside our institute. And a very interesting new point is that we make a business plan for having a factory of solar panels. We are still looking for technology partners who can supply us with the semiconductors, with the key elements of the photocell, and how to make viable a local production of solar energy. We are very strong, as I told, in Brazil overall in software. Here the example of smart TV. I believe we will have the same thing on 5G. So Brazil is a typical place where we have very good middleware and software developers. And here we managed to develop the complete solution for Philips and others for digital TV and respective embedded software. Some new point we also want to remark, software now is going smarter and smarter, starting to be intelligence. So it's not only smart, it starts to be intelligent. So in this case, we work here with famous companies like BASF doing the development of pattern recognition. Here we also were looking for hyperspectral cameras and smart processing of this. We put together with a local drone company, Orus, a small startup. And here we have a very interesting solution that we can build up in places like Brazil, developing everything. So we can do the sensor, we can do the software, and we can also look for the end user of the solution that wants to know what kind of chemical product can be used on the right amount on field.
It is clear that everything that you do is taken by key companies in the sector. I can see industrial support everywhere and industrial support by giant companies. We are almost running out of time. Could you give us like the key message?
The last one, only to close, sensors and LiDAR and these things. We are here working on the next discussions about the airplane in the future. That's one of the remarks I want to do. We grow a lot in the embedded electronics for aeronautics. And my key message is in the next one. I saw the bridge. I was very happy in the presentation before me. The bridge is now brand new. And the idea is that we want to build bridges between Europe, South America, and other partners that we can help to develop smart systems in Brazil.
We want to build a lot of bridges, and Manuel, you are the key person for that. We have one question for you, ultra-fast photonic question. Reinhard, what is on your mind?
Yes, hi, I'm from Switzerland. So we have the CSEM Brasil, and I know that there are some people doing research. Is this a competition to you? Are you working together? Because CSEM is like all the Fraunhofers together in Switzerland, about 400, and they have a department in Brazil.
Yeah, I can give you a good example from EPIC. I know Christian Bouchard from the EPIC, so we already know the founder of CSEM Brazil, and we are close to CSEM Brazil. We look at for sensors, also for coatings, and a very special solution of CSEM for printing of labels, microstructured labels, to avoid to give authenticity to documents. So yes, we
So it's
are
no
inside.
competition, you work together.
Yeah, they are
I'm
working
from
There's
together.
Switzerland,
the market is big, so it's better to make it together as to compete. So that's my opinion.
Manuel, Christian Boschar was here, like I think 10 minutes ago, so you missed him, but it is great to see that everybody is working together. Let's build those bridges, and let's build another bridge. Let's go to Mexico. Let's go to my friend Eric Rosas. Hola Eric, espero que todo vaya bien. Thank you very much for joining this amazing, completely crazy, totalmente loco kind of meeting. The floor is yours. We want to work with you.
Thank you very much, Jose. Thank you very much, Carlos, and thank you very much, EPIC, for joining us with this incredible tour around the world for the photonics all around. Yes, I would like to talk to you now about the Mexican Photonics Cluster and its main project, which started use in 2014 with the joint collaboration between the federal government in Mexico and the International Commission for Optics, which I belong to. From that collaboration, we produced the first roadmap for this industry, optics and photonics industry, and it released 6 main recommendations. The first one was that Mexico had established an optics and photonics manufacturing shared facility hub. The second one was that it had to increase this photonics and optics specialized talent availability to foster frontier science projects in optics and photonics, to recognize optics and photonics as a priority industries for future development of Mexico, to establish a production and innovation hub in Mexico, and to foster high-risk investment in research and development for optics and photonics in Mexico. From that, which was released by the end of 2016, we started by creating the Mexican Photonics Cluster, of which I am now the president of. It was established early in 2017. Indeed, it was established on May the 16th, which it was the anniversary of laser invention back in 1960. Then we started working with this concept of the Photonics Innovation City, which is the production and innovation hub that we are developing in Mexico and that I will present to you right now. We started working and looking for the right location for this production and innovation hub. And in 2019, we decided that we were going to go to Querétaro, which is the center in Mexico. And in the same year, we also joined the Global Photonics Alliance, which, as you can see there, Jose, you must remember, we met in Arizona and then in San Francisco to gather with all the people from the clusters in Europe mainly, but also in America, and right now also in Japan. So these are a few samples of all the clusters all around the world, which are part now of the Global Photonics Alliance. There you can see we are also there, the Mexican Photonics Cluster, but we can also have Finland there. We also have all the major clusters in the US and other clusters in like SECFO in the south of Europe, and that means Portugal and Spain as well. And okay, so what I'm going to talk to you now is about this incredible project, which is known as the Photonics Innovation City. That's meant to be the first testing smart city built from scratch in the world. As you know, in many places all around the world, many small boroughs have been transformed into smart boroughs, smart cities. But this one we are building now, we are going to start building now, is the first one which has been designed from scratch, like a green field, so you can just let your imagination to fly. And this is also meant to be the first production and innovation hub in optics and photonics in the whole Latin America. Well, so the mission of the Photonics Innovation City is to serve as the bridge between knowledge generation and innovation in order to contribute to Mexico's development towards becoming a knowledge-based economy. So as you know, all the economies around the world are looking to be part of this wave, which is to become a knowledge-based economy, where the talent drives all the future development of the country. And our vision is to become the most influential optics and photonics innovation hub for Latin America. So this is our location. This is just right in the center of the state of the Mexico, of the country. And that's because, as you will see in the next slide, we have all the need connections. It is a cross-border for all Mexican productivity, north, south, south, north, east, west, west, east. So as you can see, we're very close to the Mexico City. It's only a few 200 kilometers from Mexico City to the west. We're also very close to Querétaro City, only 45 kilometers away. We are also close from an international airport in Querétaro, only 16 kilometers away. And we're close also from the US border in Laredo, Texas, which is 925 kilometers with rail trails, with roads, wide roads, and with also some other airports. We are also in the middle from the two oceans. That means the port of Manzanillo and the port of Veracruz, just in the middle. That gives us a splendorous location just to connect between Europe, for example, and the south of Asia. And well, this is the concept of the Mexican or the Photonics Innovation City in Mexico. As you can see, this complies with all the specification from the United Nations to become a smart city, and it perfectly aligns with the sustainable development objectives that have been created by UNESCO to be accomplished by 2030. As you can see, we are planning to have all the amenities, I mean, Internet of Things, Wi-Fi, eco-friendly data center, smart buildings, smart lighting, smart security, smart defense, cyber security also, smart health, everything that you can find in all the smart cities, there you will be able to find in this Photonics Innovation City in the center of Mexico. There, in this layout, you can see how it is planned to be developed. We will have not only industrial premises ready to be used in the Industry 4.0 equipment, but also we will have housing around 18,000 houses for all levels, and we will have also recreational areas for leisure. We will have commercial and all services. Also, we will have all the educational services and everything you can find in a small city. But all of this will be connected, completely connected, to work as a sole unit of intelligence. The next one. Why did we choose Querétaro? As I told you before, this is right in the middle of the country. So you can travel to the north, to the south, to the west, to the east, everywhere in a very short amount of time. We are also in the central time of the US, which is our main partner for trade in Mexico. But it happens that Querétaro is the only region in Mexico which has retained so far the global investment trade. You can see the qualifications by Standard & Poor's, by Moody's, and it has also been qualified as the second place in Latin America in 2017 to make friendly business. So it's a very, it's a location, is the right location if you want to come to Mexico and make business in the photonics industry, because it also hosts two other major industry clusters, like the one for aerospace, like the one for car makers, light car makers, which are also located in there, among some other industrial clusters. So I'd like to talk to you a little bit about Mexico and its macroeconomic considerations that you may take in consideration also if you want to come to Mexico and make business, or in Latin America as well. We are in Mexico around 125 million people, and of those, 90 million people are internet users by 2021, according to Cisco. You all know Cisco. And in the same year, we are expected to have 83 million of smartphone users. And we're having right now around 250,000 new internet connections per minute. That's a huge amount of internet connections being released every minute. We expect to have by 2021, 385 million of Internet of Things connected devices. And we expect that 80% of all the workloads in Mexico by 2021 would be of video. That demands a lot of bandwidth available to do this kind of movements. We also have some other qualifications. We are the first chip electronics acquisition place in Latin America. We are the second most competitive economy in Latin America. So it seems that if you are really interested in come to America, Latin America, the Americas, and make business, the right place for you to be is the Photonics Innovation City. Now, I'm comparing now the 3 most important economies in Latin America. And as you can see, we are 126.2 million people, according to the World Bank in 2018. And our GDP was $1.22 billion in the same year. But our inflation was only 3.8% in 2019, according to the Mexican bank. And despite the COVID pandemics, we are expected that by the end of 2020, our inflation will be lower than 3.5% and even lower to 3% by 2021. Now, in terms of the variation in the exchange rate, in 2019, the Mexican peso, MXN, was the less currency in the whole Latin America. So there you have the exchange rate. We expect that by the end of the 2020, the exchange rate between the Mexican peso and the US dollar will be 22 Mexican pesos per US dollar. Our debt in difference with other major economies in Latin America is only 53.8% of our GDP. And our reserves are around 187,000 million US dollars. So we are pretty much a health economy in terms of the international debt. Regarding the investment rates, as you can see, we are the only economy in Latin America which still holds the inversion degrees, even though this is lower, but we still have the investment degree and the investment qualifications. The Mexican economy is expected to keep this investment rate despite the COVID-19 pandemics. So we are very, very happy with that. And in 2020, the Mexican Stock Exchange, the Bolsa Mexicana de Valores, reached a historical record of 46,900 units. Now, in terms of free trade agreements, Mexico has right now 14 trade agreements worldwide. That gives Mexico access to over 60% of the global GDP all around the world. We are part of the OECD, we are part of the Asia Pacific Economic Cooperation, and we're also part of the World Trade Organization. So we're a very responsible partner if you want to make business with us in Mexico. And we're also part, of course, of the Association of Latin American Integration. In terms of our international relations in Mexico, we are also part of the United Nations and also part of the Organization of the American States. We have relations with over 39% of the countries in the world. That means Mexico has around 80 embassies worldwide and around 70 consulates, most of them in Europe and in the United States, regions in the world, which the ones that we have the most intense trade and social relations. Regarding the talent in Mexico, I must tell you that we have 1 engineer per 100 inhabitants. In 2019, we graduated almost 114,000 engineers in the whole country. And as you can see, we can compare with some other countries, even in Europe, like in France, for example. And we are almost half the graduated engineers that USA have every year. And regarding our demographics, as you can see, we are a very young society. That means that if you want to come and find talent in optics and photonics, Mexico, again, is the best place for you to come. In 2020, we are expected to be almost 129 million Mexicans. So there's no place for you to go if you want to make business in optics and photonics. So finally, I would like to give you some hints. If you want to join us in the Mexican Photonics Cluster, our fees for 2020 are more or less the ones that you can find everywhere in the world, that you can find our data. And well, you can find us also everywhere in the internet. And please Jose, I would like you to play our video if you can help us with that.
Of course, I can help you with that. It is my pleasure. It is my honor to share this beautiful video.
Throughout history, we have built our future with dreams and ideas, seeking to improve each tool we create and advancing with each step to a future of better quality and unlimited potential. Great civilizations changed the course of history, leaving us the search of our own path and the new ways to reach it. And finally today, we can glimpse in the distance the lights that show us the way. From time to time, there are people who have changed the destiny of humanity, and today is the day for you to do it too. Presenting CMF Photonics Innovation City, Mexican Institute of Photonic Manufacturing, University Campus Consortium of Mexican and foreign universities, with professional as well as schooled, dual and shared undergraduate.
Jose, we cannot see the video.
In science.
You cannot see the video?
No, it's not been displayed.
Okay, that's good. You waited 2 minutes to tell me that, and I was hoping that everybody was seeing it. Let me try again for the second time. I think you should be able to see it. Can you see it now?
Yeah, I'm watching it now, yeah.
Future with dreams and ideas, seeking to improve each tool we create and advancing with each step to a future of better quality and unlimited potential. Great civilizations changed the course of history, leaving us the search of our own path and the new ways to reach it. And finally today, we can glimpse in the distance the lights that show us the way. From time to time, there are people who have changed the destiny of humanity, and today is the day for you to do it too. Presenting CMF Photonics Innovation City, Mexican Institute of Photonic Manufacturing, University Campus Consortium of Mexican and foreign universities, with professional as well as schooled, dual and shared undergraduate and postgraduate programs in science, technology, mathematics, and engineering, focused on optics and photonics. Mixed urban set, including 18,000 homes, more than 100 standard industrial lots, and all the necessary educational, cultural, sports, commercial, medical, and recreational services. It will host companies in the optics and photonics sector, enabling industries in advanced manufacturing, security, health and medical devices, telecommunications and ICT, and energy. Created so that the light reaches farther, faster, creating a new home for photonics, the beginning of the era of light in Latin America. Photonics Innovation City is a dream. New discoveries, new technologies, new paths to design. Everything is possible. It's your chance to be here, to change history, and give light to humanity. Because your place is already here. You just have to take it. Turn the light on. Photonics changes everything. Photonics Innovation City.
Thank you very much, Jose. Thank you very much.
Photonics changes everything. Keep the Mexican light on. You guys are fantastic. Eric, thank you for sharing that beautiful picture from Arizona. I still remember you. We go now to the next speaker. Eric, do me a favor. Now we go to the north part of America. We go all the way to Canada. And we go to my friend. I'm going to pronounce his name in two different ways. In European French is Ghislain. And in Canadian French is Ghislain from TERAXION. Thank you very much for being with us. This is one of the companies to watch. We are so happy to have you in EPIC. The floor and the attention of everyone goes to Canada, goes to you. It is 8:20 here in Mission Control in Northwijk, the Netherlands. What time is it over there? I still have you muted. Could you unmute yourself? Yes.
Do you hear me now?
Yes, loud and clear. What time is it over there? Here is 8:20.
It's
we are exactly on time.
2:20 in the afternoon.
2:20 in the beautiful afternoon. The floor is yours.
Thank you. Do you see the presentation?
Yes, perfectly.
Okay, great. First, thank you, Jose and Carlos and the EPIC team for giving TERAXION the opportunity to speak today in this very spectacular event. The other thing is that I have to mention that today is the Quebec national holiday, so bonne fête Quebec. So I'll likely enjoy a glass of wine tonight to celebrate this holiday. And I'll tell you a story today, the story of the technology and market diversification for TERAXION. But at the same time, you'll get a good overview of what TERAXION is doing. So for a long time, and maybe still today, TERAXION was seen as an FBG telecom company. Indeed, TERAXION was founded in 2000 on the basis of a FBG component supplier in the telecom market. But opportunities and agility were keys to TERAXION transformation. In fact, we became a diversified technology company, and we're an established component supplier in multiple markets. I pay attention to the component aspect of our offering. We do components and we sell mainly to people doing systems and so on. So we employ 170 employees here in Quebec City. So the first market was the telecom market, and I'll summarize our story in telecom. So back in 2000, there was a shortage in telecom component supply. System vendors like Alcatel or even Nortel back then could wait 20 to 26 weeks before they can get access to different components. And it was very difficult to manage for them. So TERAXION, as part of TERAXION founders, we had this fiber rack grating expertise, and we basically started development of fiber rack gratings. We got a license from the NRC back then, and we put together the complex writing technology to give complex gratings. We also developed an thermal package because when you use the FBGs as a sensor, you want it to be sensitive, but when you use FBG in telecom, you want it to make it insensitive. So basically, the thermal package was making the gratings insensitive to temperature, which was desired in telecom. So what were the products that came out of this FBG technology? Were gain flattening filters. Back then, EDFAs were widely used. So we had this exact technology that which we were supplying gain flattening filters, and also DWDM filters to manage the different channels on the DWDM link. So then came the 10 gig and 40 gig era. It was roughly around 2005, and we expanded the capabilities in FBG to a multi-channel capabilities. In fact, we acquired a company called PHOTON Communication. It was back then it was based in California. So what was PHOTON doing? They were coding the complexity of the gratings into the phase mask itself. So you can then, with a simple manufacturing process, manufacture very complex gratings for mainly for multi-channel application. And we also developed a thermal tuning platform to allow for dynamic tuning of the FBGs in terms of center wavelength and also in terms of group delay tuning. What were the products that came out of those technology? A DCML static dispersion compensator used for 10 gig. And it is noteworthy that still today, this product is sold because still 10 gig systems are being deployed. It's even true today with the COVID-19, you know, it has increased the business activity related to 10 gig system for sure. And then the TDCX product was a tunable dispersion compensator, was mainly intended for 40 gig system. Then in 2009 came the 100 gig Coherent. So this was a real threat for TERAXION because Coherent didn't require any dispersion compensator to be used. So we reacted to that. We acquired a Optronics, a German company, and they were mastering the indium phosphide technology. And we also started the development of our own silicon photonics capabilities. And we developed also micro-optic packaging capabilities to couple the chips and to optical fiber, and also to some electronic devices as well. And what were the products that came out of those technology? Coherent IQ modulator and Coherent receiver. This technology was sold to Ciena in 2016. And but as part of the deal with Ciena, we kept access to the IP. So TERAXION basically built back all those capacities, and although it was sold to Ciena, we built back those capacities, and we have the opportunity to apply it to other markets today, and we're doing so. So then, more recently, the 100 gig PAM4 for data center interconnect. The content provider want to connect their data center together with 100 gig link, roughly 80 kilometer in length, and PAM4 is a very cost competitive alternative to Coherent, but PAM4 they need to compensate dispersion. So we developed a slope match multi-channel dispersion compensation technology. So with one device, you can compensate 50-something channel at the same time, which was not the case with the prior technology, and we can make it a slope match to the fiber itself. So the product is a TDC-MX slope match, multi-channel tunable dispersion compensator, deployed today in PAM4 system. So the first diversification effort was made in laser system. What is laser system? Two segments: high power fiber laser. So it's mainly CW high power laser used to do material processing like marking, cutting, welding. The other segment is the ultra fast laser segment. It's a cold ablation process, and it's used for material processing, but with more precise details. And those examples were shown earlier today by Trump and also by Brasil from NKT. So I won't expand on this. So enabling multi-kilowatt CW fiber laser. When we started in this back maybe more than 10 years ago, CW lasers were operating somewhere around 50 watt. Now today you have laser cavity working in excess of 2 kilowatt, even 3 kilowatt. So TERAXION has developed the technological capabilities to write gratings in LMA fiber going from 10 micron to 50 micron. We also do some femtosecond writing of FBG, so mainly used for true coating writing, and true coating is very compatible with very high power components. We have a heat dissipation packaging technology as well. And the products we have is high power reflectors. So this is basically the fiber mirrors that you put on each side of your Dahv fiber to perform the lasing function. And we also have a Raman scattering suppressor. With high power in the fiber comes nonlinear effect. Raman scattering is one of them, and we have a device that is used to eliminate the undesirable Raman scattering signal in the cavity or outside of the cavity. Now the industrialization of ultrafast laser, a less mature segment, but emerging segment, and a lot of effort are made to make those lasers smaller and cheaper. So TERAXION apply its dispersion management technology, which was developed for telecom at 1.5 micron. We have adapted our process to 1 micron because for an ultrafast laser, one of the keys is to control dispersion within the cavity. And TERAXION investment in telecom were very useful for us to open a new market. So we are doing wide bandwidth chirp FBGs at 1 micron today. We applied the thermal tuning platform again, and also the micro optic assembly that we developed for the 100 gig coherent era, and also some RF electronics. So what do we do in terms of product? Static and tunable power stretcher, the stretching function that is performed before the amplification as part of a CPA system in an ultrafast laser. And also, we just recently came out with a pulse picker to select some of the pulse output from the seeder itself. So it's at the prototype level, and we just started to sample these products to customers today. And we also developed the RF driver that goes with the AOM based pulse picker product. Now the other diversification side is the optical sensing. What is optical sensing for us? It's fiber optic sensing. So physical parameter sensing using the optical fiber, like temperature and strain, and also remote sensing. I mean by remote sensing LiDAR used in wind energy, wind measurement, and also the emerging autonomous vehicle LiDAR segment that everybody start to talk about. So every precise fiber optic or LiDAR system, they need a low noise seeding and filtering function. So TERAXION technology is used in those systems. The one technology is the laser frequency control. It is a technology that was acquired from DICOS back in 2005. DICOS was a small Quebec-based company. And we integrated the company, and the first application of their product was as part of the ALMA project. The ALMA is a millimeter telescope array deployed in the Atacama Desert in Chile, and they use a local photonic local oscillator distribution system to distribute the local oscillator to all the antennas. And the TERAXION hardware is the engine as part of this local oscillator, composed of narrow band, narrow line with lasers, phase lock to slave lasers to distribute the local oscillator. You can go on the ALMA website and you'll see some very impressive observation they're doing. They've been doing that since 2009 with TERAXION hardware. Also, narrowband FBGs are used in sensing. Again, the thermal tuning platform. What products? The low noise laser module. So this is a commercial version of a low noise laser module used as a seeder. The narrowband tunable filter. It is noteworthy that both those products are used at the interrogator level. So you may think that TERAXION as an FBG manufacturer has business in the sensor itself, but we don't have much business in there. We have business in the interrogator with the system vendors. What are we doing in the autonomous driving opportunity? More specifically, FMCW LiDAR, which allow for longer ranging. The technologies we're applying, we have started the development of an intrinsically narrow line width semiconductor laser. And for some reason, this laser has a very high linearity frequency sweeping capability. And it is when you launch a ramp into the laser, the output light is very closely following this ramp. In fact, we have a peak-to-peak deviation from the perfect ramp, roughly 10 times better than what you get with a standard DFB laser. We're also applying the micro-optic assembly. And what are the products? We have came out with a high linearity laser demonstrator. It has been tested by several FMCW LiDAR, automotive LiDAR manufacturer, and I mean successfully tested. And now we're moving to the next gen, the integrated part, where we basically take the concept and take the laser and integrate them into a small form factor package in a dual high linearity laser prototype. And we start to sample those prototypes to LiDAR manufacturer as well. And then the next generation resonant optical gyroscope, we're working with a specific partner on this. And In terms of technologies, again, the intrinsically narrow line width flat FM response semiconductor laser is key to have a very low noise OPLL laser system. We are using the silicon photonic chip capabilities, the low noise phase lock loop technique, the microassembly as well. The products out of that is a multi-frequency integrated laser source. So it's basically many laser chips combined in the silicon photonics chips and phase lock using the phase lock loop electronics, everything packaged in a gold box and driven by the electronic. So the resulting company for TERAXION is we've expanded from a FBG-based company to a very wide technology basis company. So FBGs, again, complex phase mask, femtosecond writing, the packaging capabilities for FBGs, laser frequency control, the heritage from Zedker with OPLLs and very narrow line width lasers, photonic integration as well, silicon photonics, micro-optic packaging, electronics, high-speed OPLL, RF electronics, and we have established a diversified revenue basis. We basically started diversification back in 2006 because, you know, in the 2000s, the ride in telecom was pretty rough. So we started roughly in 2006. In 2009, roughly 90% of our revenues were telecom. Now today, telecom has become 25%, sensing 25%, and laser system roughly 50%. And we have a complete suite of product that we're offering to all these markets. And so opportunities and agility drove diversification at TERAXION. We became a multiple technology and a multiple market company. And where are we heading? In terms of laser systems, we want to continue our horizontal expansion in both the ultra fast and the high power segment. When I mean horizontal, we want to stay at a component level. We don't want to do laser, but we want to work with a laser manufacturer. Optical sensing, we want to go from the prototype that we're sampling now in the automotive segment and the gyro segment. We want to move from prototypes to a formal product offering. And telecom, datacom, we see opportunities to capture 5G and access-related opportunities as well. So, and we will apply the same recipe. What's that recipe? Organic growth by investing a significant amount of our revenues into R&D to develop new product. Specific customer-driven programs, and also inorganic growth, as you've seen. We've done some M&A in the past, and we want to pursue this into this direction. So that was the presentation today. Thanks again for your time. So if you have any questions.
Thank you so much, Ghislain, for being with this fantastic presentation and this diversity of different product portfolio. I'm quite amazed on how big is the fiber sensing part. Is that growing? Are you seeing a growth in the fiber sensing part on TERAXION?
Yeah, we see a growth. You know, up to now, it was mainly related to fiber optic sensing, which is a market that everybody talks for a long time, but it hasn't emerged yet. But when I talk about the autonomous driving and the gyroscope, this is where we see a lot of growth in the future for TERAXION, especially because we're moving to the product itself. Now we're more in the partnership development mode with our customer. Now when we will move to the product, we see a lot of growth in there.
Let's talk about cooperation. I have 572 members here. The EPIC question: what can they do for you? What can you do for them?
Yeah, you know, we're seeking customers for sure. If we want to expand the number of products we're offering, we need to customers to share their roadmap with us, and so we can develop product. As you see, we invest a lot of our revenue into R&D. We want to develop products that are well aligned with the customer roadmap to make sure we're enabler into those roadmap. And we also seek partner because we want to expand the number of products as a component vendor. Expanding the number of products means multiple technologies. And you cannot think that a small company like TERAXION will develop all those technologies. So
but you have developed quite some of the amazing ones. The pulse stretcher with the low noise is out of this world. My friend Reinhard, CEO of SUS Micro-Optics, has a question for you.
Yeah, go ahead.
Yes, thanks for the nice presentation. So the million-dollar question is, which technology will really win for LiDAR? What is your guess? Because LiDAR, we have a lot of approaches. not so many cars because it's too expensive, too big, and so on.
Yeah, what we see is that, of course, today the time of flight technology is leading the pack, but it has certain limitation, and you have people in favor of time of flight, but we see a lot of emerging development in FMCW because FMCW brings some higher ranging capabilities. I think that at the end you will have a mix of those technologies depending on what is it you want to really achieve on a car.
Thank you so much, Ghislain. And we continue 8:40. We are still on time. We go to Photon ETC. We stay, of course, in America. We go to Canada. What time is it over there? Here is 8:41. Sébastien?
It's 2:40, 2:41.
2:41. The floor and the attention of everyone is yours. Tell us about your imaging systems.
Yes, let me share my screen. And let's go. You tell me if that is working.
It is working so far.
Yeah.
Go to slide. Yes, perfect.
Okay, great. Thanks. I'm Sébastien Blais-Ouellette from Photon, etc. We're going just a few hours driving west from Quebec City, where Ghislain was, and we're in Montreal. I will present to you very briefly an overview of our company. Been established in 2003. We're out of astronomy. It's nice that Ghislain talked about the Atacama millimeter array. Many of you in Europe and of course in North America know us for our tunable filter. I will talk about that, but first talk about the team. We're now 45, a lot of PhDs, engineers, tech in every department, mechanical, optical, electronics, software, firmware. We're have a diverse crowd here of expertise, and we're in the middle of the city at the very strategic crossing point of a bike path and a metro station and a creative hub. It's rare that manufacturing happens in the heart of the cities, but it's great because Montreal is a university city, and we get an influx of great talents, and it's a great living area also. Let's talk about the technology a bit. You all know, no, you don't, but many of you know that we started a company building a tunable filter. It's not a tunable filter like Ghislain talked about, because these are based on volume Bragg grading instead of fiber Bragg grading. It's great for it's great for filtering lasers, of course, super continuum, anything that is broadband, but it also can filter images, full images. The fact that it's a volume, so it's an optomechanical system, it's not fiber-based, it allows for very simple tuning and very, very wide range in terms of tuning. So out of band rejection is really, really high compared to other imaging filtering technique. And so we are distributing and fabricating these tunable filters for many partners around the world, and directly for scientists also. On the other side, many of you know the camera company, Photon as a camera company. And so shortwave camera were developed at Photons to match the tunable filter and be able to do hyperspectral imaging with these. But finally, we had great success, and now we have a very high performance and a quite large portfolio of SWIR cameras in gas, Mercatel or MCT. We stuck to T cooling, so it's really oriented to industrial and the lab. And we're developing more systems, but we're covering anything. I mean, some are indivisible, but mainly shortwave at 1.7, 2.5, 2.9 micron even. Very useful in the industry setup, and of course in the lab for many applications, both in material science and life science. When you couple these tunable filters with cameras, either like CCDs, CMOS, or infrared cameras, you can build full hyperspectral system. Of course, hyperspectral has been around for a while, mainly putting a spectrometer in front of a camera and sweeping the area either on a satellite plane or conveyor belt. But we didn't invent any spectrometer. So we say we have a tunable filter. What's it good for? And it was great for microscopy. So maybe 10, 12 years back, we started to develop the hyperspectral microscope. Very, very good success in material science to analyze, as you'll see, photoluminescence, fluorescence from different materials. You can do microscopy, but you can also do wide field. So instead of putting a microscope in front of the tunable filter, you put just a lens in a different setup. As you saw, the VEOS and CEOS for visible EOS and SWIR EOS, but also grand EOS, which cover visible and SWIR regions. So you can look at a sample. Think about a photovoltaic or some big solar cell, and you take images. You get one image at each wavelength because it's a tunable filter. And then scientists love to do analysis. I'll show you some more example a bit later. In fact, not that later, it's now. I don't have the clock in front of me, so 5 minutes. Okay, that's great. Okay, I have the it's nice. I don't want to go too fast. So global hyperspectral imaging is what we're doing, because it's based on a tunable filter to distinguish that from a bit more classical hyperspectral imaging based on spectrometers. But when you look at microscale or macroscale, we have developed quite useful tools to analyze new potential photovoltaic materials for the next generation of solar material and solar cells, solar panels. And so perovskite developers now, which is kind of a new, very, very promising material, starts to be built on a larger scale now. It's flexible, cost-effective, quite high efficiency, but very hard to develop. And people adopted our technology to develop these materials because you can get a full image, and at each point you get a spectrum, very clean, very low noise, and people can analyze the efficiency and the distribution of the grain and their efficiency on a micro scale level or a bit more macro scale. But if you look at semiconductor, sensitivity of our camera, you can couple that to our tunable filter or not. But one of the big fields in analyzing semiconductor, and especially in this case, integrated circuit, without opening it, of course, silicon is transparent in the SWIR region. So you can look at where's the activity going, because the electron, when they move, when they flip, they will sometimes emit photons. But to do that, you need a very, very sensitive SWIR cameras. The fact that we cool our systems to -80 in gas at -80, it's rare. Why would you do that? But for these kind of applications. So you look at a circuit through the silicon, and you can see what is active at what moment. Because our cameras goes to many hundred frames per second, you can really look at the activity of an integrated circuit like that. So it's very useful, it's very high demand for that. Completely different regime. But if you look at drill cores for mining, of course, hyperspectral imaging can also be useful, because you can look at, since you have a spectrum per pixel, for each point of the image, when you have a database of your ore in the area, and you can scan each of the drill cores, you can analyze what is the mineral content of these drill cores. It was a very high activity maybe 8 years ago in photons. Then, of course, mining is a really, really up and down business. So it faded out, and now it's coming back big time, because we develop more technologies, more adapted. We used to do that mostly in the visible, and now we do that in the infrared, and the results are great. So from our two basic blocks, tunable filters and cameras, we are building systems for different verticals, for different, especially partners in different light. But that also is as diverse. We talked about science, we talked about industrial, now we have a very interesting development in life science, because a few years back, people saw that we started to see publication of some researchers saying, looking at animals in the infrared and looking at the penetration of light in the sphere region. And there's a nice sweet spot around 1.2, 1.3 micron. And that's in gas region, where autofluorescence, which is a big problem in life science, normally when you do fluorescence or bioluminescence experiments, the autofluorescence is generated directly by the tissue. It's we are fluorescent, in fact. But in the infrared, of course, it's a higher, it's a longer wavelength, lower energy, no autofluorescence. And also the penetration, the absorption from water, which plagues the penetration in a longer wavelength, in hemoglobin, in the visible, in this sweet spot, there's very low absorption. So you can see through a lot through animals, and people started to do experiment, build their own system, and say, do you want one? And we develop a system for that. And if you look at this is an animal. It's black because there's no autofluorescence, and we just injected indocyanin green, which fluoresces mostly at 800. But this is at 1.2 micron. We put a filter. There's still a tail in the fluorescence of indocyanin green, ICG. And this is a mouse, just a normal mouse. And you see through the mouse, this is just normal sphere imaging, and injected with the fluorophore, very, very traditional, classic fluorophore. This fluorophore can even be injected in human. ICG is used in human also. And you can see that going through the body, and you can look at all the individual dynamics inside. Even we can look at the respiration, heart beating. But if you tag your fluorophore, you can also go directly to tumors and go directly to the nervous system. So and now we're playing all sorts of analysis. But of course, we're not biologists. We're just the tool makers for these people that are developing new drugs and new treatment on these. This is for small animal imaging, but we can also work on organoids and other, of course, other 3D bodies where penetration is an issue. Penetration of light is an issue. All that, and I could go on for the applications, but basically, Photon is based on a core of technologies where you have, we build scientific systems. If industrials come to us, say, we need this custom system, and we look at the market, we say, okay, this is an interesting market. We develop a new solutions for specific problems in markets. But with time, we have our hands and paws everywhere, and we cannot be expert in everything. So partnerships have played an essential role at Photon, either through people internally who started companies like New View Cameras, who are doing amazing EMCCDs, and now we have also Optina Diagnostics, which started at Photon and is doing, they call it deep retinal phenotyping. But basically, they're doing hyperspectral imaging of retina. And from that, because in retina, you have nerves from the optical nerve, you have blood flow, and you have all sorts of arteria and veins. You can diagnose a lot of conditions from the body. Now they have, for Alzheimer only, and it's their first indication, their results are very close to what a PET scan, which is the gold standard now to confirm Alzheimer disease. They're doing that just through an eye scan, and it's amazing what they do. Of course, now we have this preclinical venture that we are investing in with partners, and of course we have partners who are just we're either sell to us, buy from them, combine our technologies to make a new product, and we want more of these, because when you combine our expertise, especially if someone has a market expertise and we have part of the solution, that's what we love. we've been partnering with people in Europe since the beginning. My PhD was in France, but we have a foot in North America, of course. So it's easy for us to trade on both sides and be a partner for new developments. If anyone in the EPIC cluster wants to talk about the new partnerships. Thank you.
Thank you very much, Sébastien. And they all want to talk about new partnerships. Actually, I sort of made a living out of that. So if we can find the best partnerships, the best way is to answer the EPIC question. 572 members, what can they do for you? What can you do for them?
They certainly can. We have a say at Photon. We're looking for trouble. Okay. And we love your trouble. If you have troubles, you have challenges, something, we may have a new technologies in our glove box somewhere that could be applied, or our standard technologies also. But we'd love to develop new things, but we need challenges. Of course, we love partners also who can answer others people's challenges with us. So that's what I think the cluster and the people, that's what we've been doing with in Europe, in North America, but I think through the cluster, we can certainly go much faster.
For me, if I had to answer that question, I would say, Photon ETC, we have amazing filter technology. So tell us which signal to filter, whether it is the supercontinuum generation from NKT or whether it is a continuous filter in hyperspectral imaging, will make the best possible filter. At the end of the day, one thing that I'm seeing now is that you started from a nice concept and now you make amazing cameras. Hyperspectral imaging seems to be perhaps the winning one, right? Are you pushing the hyperspectral imaging sector the most right now at Photon ETC?
But hyperspectral imaging is not, to my sense, a sector. It's just a tool for many sectors, as people would, the hyperspectral people, know it's everywhere. It can be useful. So there's a lot of room to develop full solutions together. We work with other hyperspectral company because we have parts of the solutions to answer specific challenges of food industry, mining industry, transformation, sorting, waste sorting, all of that is based on hyperspectral imaging. And sometimes it's our basic technology that is the best, sometimes it's a dispersive technology that is the best. And so, but let's be agnostic and let's combine technology and address the challenge together. That's the way we like it.
Earlier today, we had a presentation from HiSpecs, and they were really happy with the market segment that is enabling hyperspectral imaging technology. They already said for us that the food and beverage and the recycling, the plastic seems to be something booming in the coming years. Is hyperspectral imaging cost effective for these markets, or do you think we have to make a paradigm shift in the optics and the assembly of the cameras for this?
I think we have to be clever about that, because if you want all the information, both spectral information and imaging information, it will always be quite costly. But if you combine, for example, machine learning, artificial intelligence with hyperspectral imaging, you can extract what is required to diagnose your problems, to look at the quality of specific food or material. And then you can extract from that what is the best cost-effective system you can build. It's often not hyperspectral. It can be multispectral. It can be a combination of clever information gathering technique. And that's, I think, the way to go to make it cost-effective.
This is exactly what I wanted you to tell me. At the end of the day, it is all about, you don't need to have the full wavelength range for every pixel of the camera. What you need to have is the right tool to make the machine decide whether that tomato or that fish is good enough to pass. So are you enabling this communication between the machine vision people and your cameras?
Interesting that you asked the question, because we're building now a system that is in a container, and currently it covers from 400 nanometer to 14 microns, all hyperspectral. So visible, shortwave, midwave, long wave, and we invite people to put their potatoes, their drill cores, anything on the conveyor belt, see what's out there for hyperspectral imaging or multispectral imaging. So we invite people to do that. Yeah.
And I invite the EPIC members to have a chat with Sébastien.
Yes,
PHOTON,
absolutely.
etc. is an amazing company. They have great technology and they have a fantastic spokesperson today. Sébastien, you are a star. Thank you very much for joining us in this completely crazy. We are completely crazy. This crazy day, 24 hours of photonics. We continue with the program and we go now to the US. We go to the US and we go to a company that in the segment of blue lasers is making a big difference in this industry. I'm very happy to have NUBURU today with us, and I'm very happy to have Mark. Mark Zediker is gonna tell us how we can help NUBURU, a great laser company, be even greater. The floor is yours, Mark. Thank you very much for joining this crazy day.
Thank you very much. I'm going to go ahead and share my screen.
It is
so
9 o'clock here in Noordwijk, the Netherlands. What time is it over there?
It is 1 o'clock in the afternoon.
Time to rock.
So nice and early for us. I'm going to apologize that I do not have a camera on this computer, so you can see my picture from this little slide, which is a little introduction to myself. And I've actually had several startup companies in my life. I began my career in Boeing in St. Louis and worked my way into a company called Nuvonics. And Nuvonics was sold to Coherent back in 2008. And then I worked at started up a company called Foro Energy for using lasers for rock drilling. So I loved the last reference to rock drilling. I knew exactly what you were talking about when you looked at drilling cores. So that was a fun thing to see again. It's been a few years since I've done that. And more recently, I started this company called NUBURU, which is blue lasers and bringing blue laser technology to the world. So that's what we do. We produce, we develop and manufacture very high brightness blue laser sources. And as a consequence, we're putting applications together that transform how you do welding and in some cases cutting on what is otherwise ultra reflective materials for the infrared, such as copper and gold. Two examples where we've had a lot of success to date, where the infrared lasers have struggled. So the company itself started in 2015. This is the nice blue skies in Colorado. I have to say they're the same today at 1 o'clock in the afternoon. So it's a great time to be in Colorado. We have here our engineering, our manufacturing, and our applications. This building is our building. We occupy this whole side that you're looking at here. And we've got about a 30,000 square foot facility. So our applications lab is outfitted with lasers up to a kilowatt, a little over 1.5 kilowatts of power. And we can go in and have customers come here and test their welding applications and validate that we can do the manufacturing steps they're looking for and demonstrate to them that this technology is going to be suitable for welds that they've struggled with in the past. We've also been doing a fair amount of work with 3D printing, and the 3D printing applications range from blown powder or LMD or directed energy, whichever acronym you like to use, where we've been able to do a fair amount of printing of copper powders. There's a lot of interest in that from the aerospace folks, particular companies that are trying to build reusable rocket engines. They'd like to make those out of copper if at all possible. In terms of welding, we focused heavily on welding copper materials and aluminum materials, primarily for electric vehicles and for batteries. We've also done some brazing tests, and we've also done a fair amount of heat treating tests as well. So why blue? So the biggest thing about blue is this is a chart showing the wavelength of light versus the absorption of materials. And in this case, we're showing one graph, which is copper. And what you see is that in the infrared, right around 1 micron, the absorptivity of the energy is right around 5%. So this basically looks like a mirror to the infrared laser. On the other hand, when you hit it with blue light, the absorption is much, much higher, around 60 to 65%, depending upon the surface condition of the copper. So there is a tremendous advantage in the energy coupling capability when going from the infrared to the blue. Now, if you look at other materials such as gold, that advantage is even more substantial. And we have shown absolutely excellent welding results of gold materials for cosmetic applications. We've had great success with copper for battery applications, great success with various aluminums for, again, battery applications, and even nickel-coated coppers and nickel-coated aluminums. All of these show a much, much better absorption ratio compared to the infrared. So there are other type of infrared laser technologies out there. There's beam wobbling, there's adjustable mode lasers, and there's all kinds of techniques that they're using today to try and get good welds in these highly reflective materials with the infrared lasers. And they're getting some reasonable results. But what really hasn't been understood yet is what is the process window of those processes, and can they indeed do a weld that's spatter-free? In other words, no defects and no porosity. So what you see with the blue is because of the excellent energy coupling, you immediately transition into making an absolutely perfect weld. This is just an example of some typical welds done with the infrared laser. These are some earlier infrared laser attempts at welding copper, welding basically the ends of two pieces of copper here, which is typical in an electric motor, and then welding a copper to a stainless steel substrate here. And here you see a lot of intermixing, you see a lot of intermetallics, and yes, you can control it to some degree, but you still have to overpower that high reflectivity in the copper. When you start welding the copper with a blue laser, you immediately couple into the part. So you can immediately do a conduction mode weld. You can do a transition from conduction mode to keyhole, and you can do a keyhole weld. And you'll notice, looking at the metallurgy of the material, and indeed the resistance of the material and the strength of the material through that weld joint is very similar to the base material itself. Now, when we look at different type materials welding, such as trying to weld the steel to the copper, and this would be the can of a battery, we're able to demonstrate a very consistent welding depth. We're able to demonstrate the ability to control that depth accurately and to not penetrate that inner copper liner. When you penetrate the inner copper liner, you expose the steel to electrolyte, and the net result is early failure of the battery. So we've been able to show a lot of great results with this technique. We put less heat into the part than the infrared laser. These welds, up to a millimeter thick, are done with only about 500 watts of laser power, whereas this millimeter thick was done with several kilowatts of infrared power. In comparisons by some of our customers, they've actually documented that the blue laser has about a 9x advantage in terms of speed when welding copper materials with the blue laser over the infrared. So in terms of the various applications we've been looking at to date, probably the two largest we've been focused on are energy storage and consumer electronics. Both of these use relatively thin materials, a lot of gold-plated materials, a lot of nickel-plated materials, and more recently, the energy storage in terms of automotive, where you have bus bars, the materials are a bit thicker, and we've been demonstrating ability to do those welds as well. In aerospace, we've been doing a lot of work with the powder deposition and welding of the powders with copper powder. And in healthcare, we've been doing a lot of work with titanium. So these are pretty much the 3D printing kind of area. And then there's some research areas that we're not going to go into today, but the bottom line is welding, additive manufacturing, cladding, and cutting and brazing are all in the wheelhouse of this technology. The three different products that we're offering today begin with a 200 watt laser. And here we've demonstrated very, very low humping when welding the stainless steel plates together of a hydrogen fuel cell. And we've had excellent results and excellent feedback from the customer. We've also done a lot of work with welding Invar and stainless steel with very, very, very little humping in those applications. We have our 650 watt laser, which has demonstrated this negative tab to casing weld, the sealing of the casing, the tab to the casing, as you see in a battery pack like this, and foils, such as in a prismatic cell. In doing these developments, what we learned is the customers would like to go faster, and they'd like to use a scanner. So we've worked very, very hard on a new technology, which we call the AE 1500, which is 1.5 kilowatts of laser power. And that laser is compatible with a scanner. And here we can do all the same welds, but now we can scan across this battery pack with a standard scanner. And combining a scanner with a 6-axis robot, we can talk about now about manufacturing large area battery packs. So NUBURU, as I mentioned, was launched in 2015, although many of the foundational patents were filed as early as 2013, 20 of which have been awarded to date for the use of copper blue lasers in the welding of copper and 3D printing. Our first ever laser capable of welding copper occurred in about 2016 with an early beta unit. And in 2017, we started shipping some beta units for tests to customers. We received a number of industry awards, Prism Award, Innovation Award, and so on for both the AO150 and the AO650. So in 2019, we launched a 500 watt laser. We demonstrated the ability to do welding in kilowatt. We were certainly a finalist in several more of the award systems, but we also demonstrated a unique, brand new single mode blue laser technology, which we'll be bringing to the market by 2021. In 2020, we released a AO200, which is 200 watts, an AO650, which is 650 watts, and the IE 1500 at Photonics West in February. In terms of the photonics supply chain, we draw from a lot of sectors. In terms of combining all these laser diodes into a single spot, we use everything from micro lenses, automated micro lens placement, macro lenses, automated macro lens placement, fibers, fiber coupling, fiber delivery, QBH, beam delivery, scanners, as well as standard welding heads. And of course, power supplies and everything else. So we draw from the entire photonics supply chain, and we draw from all over the world. Again, our product portfolio, very simple, 200 watt laser, 200 micron fiber, 15 millimeter millirad, 650 watt laser, 400 micron fiber, 30 millimeter millirad, and our new 1500 watt, 1.5 kilowatt laser, 100 micron fiber, 11 millimeter millirad, capable of producing less than 100 micron spot size with weld heads and capable of operating with most conventional scanners. As I mentioned, in 2018 and 2019, we received a number of industry awards, and we're very proud about all of them and what our products have achieved. And with that, I know I'm a couple seconds early, so that is pretty much the talk that I had prepared for today.
Mark, never ever apologize for being early, please, never. I'm having one of the happiest, I have to say, the happiest day in my life. I'm seeing so many interesting things. Mark, many years ago, something like 15 years ago, many people were talking about making blue lasers because of what you said. Blue lasers were actually processing materials that couldn't be done with infrared lasers. But people couldn't. I mean, it was a nice idea, but there was very many difficulties that didn't allow this dream to make true. What's the secret for NUBURU, if I can ask this?
Patience and a lot of hard work. So it turns out that, of course, I chair the High Power Diode Laser Technology Conference at Photonics West, and actually was the founder of that conference as well. And I have watched for years this technology evolve and develop. As the technology started reaching brightness levels and power levels that appeared interesting, my prior experience at my company called Nuvonix and my prior experience at McDonnell Douglas, it became very clear that it would be possible to combine these lasers together in a meaningful way and create an industrial product. So the real breakthrough was that the lasers reached the critical level of intensity and power and cost necessary to transition this into a product. And then, of course, there were a lot of new problems on the way that one did not expect in the blue, that do not occur in the infrared, that we had to solve. Many of which I'm not going to go into deep detail because we are almost out of time.
No, we have time. We have time. And I want to ask you what I call the epic question, Mark. I have 570 companies here who want to work with you. What can you do for them, and what can they do for you?
Well, I think it goes both ways, as you just described it. Number one, we're always looking for new suppliers, whether it is at the laser level, and that could be anything from the laser diodes to the power supplies, to the micro optics, to the optics, to the fibers. I can go on endlessly, to the mechanical components. We're always looking for new suppliers there. What can we do for other people? If they've got a soldering challenge, they got a welding challenge that they're having a difficult time doing with an infrared laser, let us take a look at it, especially if it's using high reflectivity materials. We've been very, very successful where others have failed. And we're always looking for a way to help people out and solve their manufacturing problems.
One more thing, when it comes to the beam delivery, especially for the high powers that you are managing, are you managing to find optical fibers that are actually suitable for some of your applications?
Yes, absolutely. We have worked closely with the fiber vendors, and we have tested a variety of fiber vendors to date and qualified them for use with our products up to about 1 kilowatt so far. So I should say 1.5 kilowatts, excuse me. So yes, we've been getting very, very good results with the fiber vendors to date.
I have a really good question for you in the YouTube channel. And I have to say, I didn't think about that, but luckily from EPIC, our innovation manager thought about it. He said, you said copper, you said gold. He went to the periodic table and he found silver in the middle. Why are you not speaking about silver?
So silver, if you look at the absorption curve on silver, you're only about a few percent. So we could indeed do silver. It's just not the most efficient possible. The silver absorption really peaks up in the UV, but there's no reason why we wouldn't be able to weld it. It's just going to take a fair amount of power.
Another question for you from the University of Bath, Pierre-Marie Coulon. He's wondering, question for Mark. Maybe, he said, maybe a stupid one. There are no stupid questions, Pierre-Marie. Does the output power stack up linearly with the number of blue laser diodes?
So that's a great question. And the answer is, of course, because you are adding one, a diode each time you go up in power. But I will say that we have scaled the brightness in a different way. And so the laser brightness is the power in a given angle. And we have a technique and a technology that allows us to scale this to unbelievable levels.
Another question, but this one is from me. I am doing a lot of work with different hospitals, bringing photonics to the clinicians. I saw the thing that you're doing with titanium. What is the technology readiness level? What I mean is, do you have already success stories really on the clinical part of the titanium-based material processing?
So we have done a fair amount of titanium processing, but we have not done any clinical parts yet. We've been working with companies doing 3D printing, primarily blown powder with titanium, making fully dense parts and getting very, very good characteristics from that. We have a couple partners that we have, and we love the partnership with people, and they're doing actually that work, and you'll be seeing some papers with that in probably the next year about that topic.
EPIC is working very strongly with many companies in the world on 3D printing of metal for different applications. And we are going to come together very soon at Siemens. Mark, I want you to be one of our keynote speakers because you do have amazing technology. You have a secret, which is great. And you also have the track record of being following the industry and managing to make what many people wanted to do 15 years ago. Thank you very much, Mark. It is an honor to have you here today. It is a crazy day, but having seen your presentation really have made me even happier than I already am. Thank you very much, Mark.
Thank you very much. My pleasure.
And we continue with this crazy and fantastic day. We continue to with a company that I really, really like. We go to Rio OPTASENSE. Yves LeMaitre, the president of OPTASENSE, is here to talk to us about ultra narrow line width lasers. Thank you very much for being with us in perhaps the happiest day in my life. The floor and the attention of everyone goes to you when it's 9:20 in Noordwijk, Netherlands, Central Control Unit. What time is it at your location?
Hey, good morning, good afternoon, good night. It's just after lunchtime here. It's 12:19 right now in the afternoon. So I'm getting hungry. So I'll keep this presentation as short as possible. Okay.
That's a good reason. The floor is yours.
Can you see my screen?
We see it very well.
Okay, great. Let me go to full screen. So first, thank you very much for the invitation. It's I'm really humbled. I've listened to some of the presentation this morning, and some of the speakers are so amazing in terms of their depths of knowledge and technology. So I'm really excited to be here. I think it's a truly epic event, and for me, it's even more important at this time, where kind of the world, there's so many negative forces that are trying to kind of tear us apart and divide us. And you see this true event that is truly global. It's really very, very, very refreshing and fantastic. So kudos to Carlos, to you, Jose, and to the rest of the EPIC team for making this a truly global event. The photonics industry is a community that is truly global. I had the chance of being born and raised in France to move to the US and work in both the East Coast and the West Coast over the last 25 years, and spent significant time in Japan at my last job at Oclaro and LUMENTUM, and then of course China. And so you realize how global we are, and it's wonderful to see us connected. So thanks so much for organizing this. It's wonderful. I'm doing this presentation from home here in California. As I said, it's about lunchtime. The weather is nice, always nice in California. That's, I guess, one of the advantages of working here. About a bit more than 3 months ago, we had to go and go through the shelter in place, working from home. So I'm actually working from my home office, but at Rio, we have a manufacturing and assembly facility here in the Bay Area, and our team is working on the factory floor after we, put some necessary protections and precautions in place. But the business is back running, and it's actually not too bad. So I'm touching wood. So I have a couple goals in this presentation. Of course, the first one is to introduce Rio and tell you a little bit about who we are and what we do. But my second goal, Jose, is for you. I want you to try to get you to fall asleep, and capture that on video so we can share it, for posterity.
I'm sorry to disappoint you. That will never happen.
Okay, well, there is actually, so that's the second part, because I think there is a theory that actually a conspiracy theory that you're actually not you're coming from another planet, that such energy concentration cannot be achieved in a human body. So we'll see at the end of the presentation, whether this is real or not. So a real test. So let me tell you about Rio. Really, our purpose in life is to be a supplier of really high purity lasers. We are based in California. We are a small team here of less than 50 people. We are a market leader in fiber sensing and solutions and laser sources. Really our purpose in life was to be the laser of choice for fiber sensing, and I'll cover a little bit later what that is. But that means that when you do such application, you really have to provide a very high level of performance as a laser. And typically the way people characterize our laser is around the line width of the laser. The performance of the laser is characterized in line width, both in kilohertz, in our case, that can go down even to below 1 kilohertz, but also in terms of noise, both frequency noise and phase noise. And we do that using a technology platform that is a compact solid state diode laser. And I'll cover that a little bit later in the presentation. It's got a fairly high level of reliability. It's been used both for telecom and space level qualification. And it's a customizable product that can operate typically in the range of 1 micron to 1.5 micron are the main applications. I'll cover next the fiber sensing market, but beside the fiber sensing market, really this type of technology is applicable to new markets, so renewable energy, and we'll talk about the wind LiDAR market, for instance, high-end automotive LiDAR and autonomous vehicles. And you can use it for certain optical communication application and OTDR, which is optical time domain reflectometry. And of course, a lot of scientific application use these high performance lasers, whether it's for atomic cooling or spectroscopy or some of the quantum computing. We are a business of a company called OPTASENSE. OPTASENSE is a company that acquired Rio about 5 years ago. They are OPTASENSE. We are a company focused on distributed acoustic sensing. So really using the fiber as a sensor. The fiber has amazing properties, you know. It is an amazing microphone, really, to capture all the acoustic wave and other events that are happening in the vicinity of where the fiber is buried or located. So there's a lot of applications around that, and OPTASENSE has designed a number of systems and services to detect and process all these acoustic signals and gather that real-time intelligence and basically make it actionable for the end customers who are not necessarily fiber optic specialists. It's a fascinating field. There's many applications. Some of them are just highlighted on this slide. I'll take the example first of the pipeline. Every pipeline in the world now has to be installed with fiber optics attached to it. I don't know if you knew that, but that's a new regulation on many countries have adopted in order to primarily provide a good monitoring of the pipeline to detect, locate, classify the type of threats that can happen along the full extent of the pipeline. An application that is obvious is leak detection. Obviously, you want to know if your pipeline is leaking and where it is leaking. You also want to measure, you know, and detect potential external interference. Hot tapping or people coming and try to steal some of the content of your pipeline is one of the areas that we are working on. Of course, any work around the pipeline that could disrupt the pipeline, such as other road work or digging, but also monitor the ground movement. You know, the pipeline sometimes is located in very remote environment, and you can have some landslides or earthquakes or other type of things that can impact the integrity of the pipeline. If you go on the OPTASENSE website, you'll find very good case studies about work we've done in Saudi Arabia about water distribution, you know, gas pipeline we do in Sichuan, China, and of course a lot of work in the oil industry as well. So this is kind of a very interesting application. Another one maybe is around perimeters. You know, essentially by installing fiber around a certain perimeter, you're able to really detect, you know, what is happening around that location. So typically you use that for high security environments. For instance, data centers, major data centers use this type of technologies. You can also use it for applications such as nuclear energy plants or airports. You know, you can also use this fiber sensing technology for transport. By that we mean rail and road monitoring. You can on the railway you can detect, you know, if a rock falls, a landslide on the rail tracks. You can track the trains. You can identify if there's a breakage on the rails, or you can even detect things that we call wheel flats. Yes, there are such things as wheel flats for trains. You can also, in the case of roadways, we have actually an interesting project that we talk about on our website about the work we did in Atlanta with on Interstate 20, where we can monitor the road, detect the average speed of the cars, detect the congestion, detect the road conditions. So it's really a very broad set of applications for the fiber sensing industry. Now, at Rio, what we do is we do the laser that enables this application. And to do this, obviously, you need to have the highest possible purity of a laser source, right? Think about it. You send that signal down the fiber, it's going to come back, some of it, a very small portion of it is going to come back either through backscattering if it's in fiber or through reflection if it's in the atmosphere. So you're going to have a very small portion of light to work with, you know. So obviously the light that you send needs to be as clean and as pure as possible when you send it in order for you to eliminate any potential noise and make sure that you're really capturing most of the information you're looking for. And those physical phenomena that you see listed here, whether it's, you know, called the Brillouin, or they're usually names after some very famous physicists, so Brillouin, Rayleigh, Doppler, Raman, all of these effects that you get by essentially sending photons and analyzing either the backscattering or the reflection, again, drives the need for a very high performing laser. As I mentioned, you have a lot of the applications that I listed before, but you also have applications like wind metrology. For instance, our laser was very successful in helping green energy companies characterize what they call wind farms. So they would use our laser and they would basically scan the environment for several weeks to be able to analyze the wind patterns and the turbulences and be able to detect the optimal position for them to implement their green energy farms. We also have our products used in avionics and LiDAR, obviously, for application in space, but also now entering more the mainstream market. Our platform, our technology platform, is a semiconductor-based product. It is an external cavity laser. I'll spare you the details, but essentially the important part of it is that we are really using building blocks that have been demonstrated for many years in industries that are highly price sensitive, such as data center. We are essentially using 3.5 indium phosphide or gallium arsenide laser source combined with silicon planar light wave circuit to build really an external cavity laser that is both high performing but also highly reliable and also can be deployed in high volume, which is some of the challenges of the technologies that have been used before that were more scientific in nature or were relying on more bulky and sometimes less reliable fiber laser solutions. So we are pretty excited about this and the opportunities that we have coming for the next few years. One of the new opportunities I want to highlight is coherent LiDAR. It was a very niche-y, very scientific technologies when we started about 10 years ago. And it's really expanded the scope of the LiDAR technology, driven by the need for people and for application to really sense the environment. I think we are all looking for controlling better what is happening around us and have the sensing technologies that enable this. Obviously, the wind LiDAR I talked about, but now we are talking about these navigational Doppler LiDARs and FMCW. If you follow the industry is a word that is very popular right now for the autonomous vehicles in particular, because it gives you a much higher resolution and perception of what is happening at longer distances with the ability to measure not just distance and targets, but also velocity of objects, which obviously becomes very critical, especially in the type of virtual world we are entering. So we are very excited about that technology that I think will differentiate and need the type of lasers that have the type of line width and performance that we are talking about. The technology is highly reliable. It's been deployed in space. And obviously the key now is to bring that technology to the mass market in addition to our core market of fiber sensing. So in summary, I think it's really interesting technology. The need for ultra narrow line width laser and ultra low phase noise lasers keeps expanding, as I said, from scientific to fiber sensing, which goes into oil and gas, defense, security, energy, infrastructure application, to now, a broad set of markets with automotive space. So it's really exciting to see the demand for higher and higher performing lasers. And I think people obviously, as the volume grow, want these products to be highly reliable, high volume manufacturable, and of course, cost effective. So that's a challenge for us, is to turn this type of niche market into a broader market and create this opportunity. We think our solid state, if you want, technology enables that. But obviously, we still have a lot of work to do. We are very excited to have so many opportunities coming to us. And really just want to thank our friends at EPIC for giving us here an opportunity to present our product and our technology.
And I thank my friend of OPTASENSE for a great presentation. I didn't fall asleep. How would I fall asleep? I could listen to you for hours or years. Thank you very much for this. You did fail miserably on making me fall asleep.
I'm sorry, Jose.
No, that's okay. That's okay. We can try it next time. A few questions for you. The first one, what can they do for you? What can you do for them?
So thanks for asking that question. So as I said, it's funny because EPIC is a European association, but really I see you as a global association now. So, and I think you're demonstrating that today. So of course, the first thing is, please buy your lasers. They're great. That's the obvious one. But really, more seriously, as you've seen hopefully from my presentation, it's very exciting and very beautiful that we have so many opportunities. But also, it's a big challenge. We cannot be the experts in every field. We have to be able to find the right companies going to enable our technology to be successful in some of these markets. We are only a small portion of the solution. We are the enabling laser for allowing some of these new sensing applications, but with our partners around the world to turn this technology into products and succeed and frankly, teach us about the market and what we need to do better. We will not succeed, right? So I think that's really important for me is that constant back and forth. We have really a lot of customers in Europe, but we also have a lot of customers in China, Japan, and North America. And through each of them, we really learn about the dynamics and the requirements of the different markets. So
your external cavity lasers have the potential of being very, very cost effective. I never use the word low cost, very cost effective in the volume production. But for that, we need a supply chain. We need to find you the right partners to go into that. Do you have everything lined up to do the packaging and assembly in the production volumes that you want?
So very, very good question, very relevant. I mean, as you've seen maybe from my drawing, I mean, the two key parts are some of these two chips, the PLC chips and the 3.5 chips. There are multiple foundries in the world who have demonstrated for other applications such as data center and communication that you can build those in very high volume and package them very effectively. So yes, but what we are seeing more and more for the very high volume application is the desire of our customers to integrate our laser into some custom design that they have to optimize the performance of their system, if it's a LiDAR system. So our goal is to give them the tools and the technology platform that allows them to then provide the best level of integration for their own application. And again, it's going to be very different for a space contractor than it is for somebody who's trying to build the next generation of autonomous vehicles, right? And I think we think our platform is kind of an interesting opportunity there because it's small, it's compact, it's reliable. And again, it's built on elements that have demonstrated their cost structure to be quite efficient in the past.
So for me, you are in business on fiber sensing. This is the market segment which I think you need to push because obviously low cost, reliable, easy to put with the fiber, small size. You have all the different ingredients. Are you talking now to interrogator manufacturers to add your laser, or do you expect them to knock on your door? How does it work with these people?
No, so we are. I would think we are definitely one of the very leading supplier there. Obviously, OPTASENSE or mother company is probably the market leader for distributed acoustic sensing. So we already have this kind of internal customer, if you want. But more importantly, we have spread and a lot of the companies who are pushing the envelope of fiber sensing to provide not just what we call, qualitative, but really quantitative measurements of what's going on. As you're pushing, you could detect a failure in a dam or something. It's relatively simple to detect it, but to know exactly what is happening, the magnitude of the leak, and the location requires you to move to a quantitative, analysis, and that's where our product shines, and hopefully that's where we'll continue to be a leading supplier.
On the market of fiber sensors, we had a presentation a couple of hours ago from HBK, from HBM Fiber Sensing.
I listened to it. It was great.
And he was talking about long distances. But you know what I realized in the last 2 months? A couple of companies who are not saying their name, in the automotive segment, they are growing a lot. And when it comes to the short distance measurement on harsh environments next to the engine, that is something that is a market to exploit. When it comes to these very, very harsh environments, and when the interrogator needs to be somehow close to the fiber sensors, do you think this is a place for your external cavity lasers to make a difference?
Yeah, so that's a very good question. So there are many, many sensors, as I mentioned, around the car and around pretty much every moving vehicles. People are trying to understand everything that's happening, right? And I think Our laser is a perfect fit to see pretty far in front of a fast-moving vehicle, which is one of the challenges the industry has. There's a lot of solution to look your immediate surroundings, 10, 20 feet around your car. But in order to detect what's happening far away and that's moving very fast towards you, there is no yet a good technology. We think FMCW, which is really the use of this coherent, type of light, will really create a very interesting application for many, not just for self-driving cars, but a lot of different type of vehicles.
One day in private, you and me, we're going to have a drink and I will tell you what I think of FMCW. But until then, you're a rock star. Thank you very much for a great presentation. You kept me even more awake than I already was.
Okay,
and
we go
to one of the photonics key companies in the world. We go to Coherent. Thank you very much, Clémence, for being with us from the key company in the segment with Coherent, a company that makes lasers, amazing lasers, any type of laser, all vertically integrated, located in every part of the world, American company with great locations in Europe, and it is great to have you today in the room. Clémence, the floor and the attention of everyone is yours. It is 9:40 sharp. So we are keeping the time so strictly. What time is it where you are right now?
It is 3:40 p.m.
Exactly. The time is perfect.
Yes.
And the time is for you to shine. The floor is yours.
All right. Thank you very much for the nice introduction. I am very excited to be interacting today in this EPIC conference. My name is Clémence Jollivet, and today I'm going to be talking to you a little bit about optical fibers, and in particular, our next generation of double-clad optical fibers, which are really designed to enable reliable and high-performance industrial laser beyond the 2 kilowatt output power. So I'm going to go through a fairly simple outline, but I want to first start with the landscape of industrial fiber laser and really put a scope around the study we've been trying to achieve here and what's really our goal to penetrate this market further. And I'm going to show you what tool we use to do that, which is essentially an analytical tool to come up with our scaling strategy. And I will then present what our new fibers are about and what are the key attributes to those fibers, and talk a little bit as well regarding the high power demonstration. So to jump into the topic a little bit, what are we going to be talking about mainly here? I really want to mention that we are talking about industrial fiber lasers. And currently, the vast majority of industrial fiber lasers are designed following very strict cost-effective guidelines. They need to have the fewest amount of components with typically co-pumping architecture. You can see on the right-hand side here would be a typical, very simple, very cost-effective fiber lasers, and very reduced number of components, 2 gratings, 1 active fibers, 1 combiner with a couple of pump diodes. Essentially, when you look at this architecture, the laser cavity will be driven by the selection of the double-clad active fiber, which is essentially the gain medium for the laser. On the lower right here, this is a typical design or architecture for such fibers where you have a doped core. Here we're really talking about ytterbium doped core, so 1 micron emission lasers. You have a shaped cladding surrounded by a low index polymer to ensure the cladding NA for the pump propagation to occur, and the hard shell silica. So when you look at those architecture, which are again very cost effective, the challenge for the market is to try to drive the power of those lasers as high as possible. And that will put some strong requirements on the optical fiber, which we're going to go through in the rest of the talk. But first, in order for the fiber to perform, the laser manufacturer will have to choose also what pump architecture they want to use in order to power scale the laser. So I wanted to also give a little bit of an overview of what is the state of the art with respect to those pumping architectures and the fibers that are currently used in those industrial laser systems. So the table here summarizes a little bit of the different configurations you will find. And it is important to state that to date, as of right now, the typical industrial fiber laser will be roughly limited around 1.5 to 2 kilowatts in terms of the highest volume of what's being produced to this day. And some of the main limitations are very widely known, well known from literature, will be stimulated Raman scattering or thermal transverse mode instability or thermal mode instability. So SRS and TMI will be the two physical phenomena that are going to prevent the further scaling of the output power in those lasers. Two main pumping wavelengths that you find in the field, you'll have 915 nanometer pump diodes, or you're going to have 976 nanometer pump diodes. And these are the key gain fibers that are currently being used in those systems. You can see various core dimensions between 14 micron all the way to 25 micron core diameter, and various cladding shapes as well. And you can see based on the absorption of your active fiber, you're going to be able to achieve various cavity length. And that's where the architecture of the laser has to be matched to the architecture of the gain fiber. And to date, these are the maximum pump power that seems to be available. So these values are taken from the field when you take into account the pump module and the components together in a laser architecture. And the typical output power that's achievable is roughly to date up between 1.5 and 2 kilowatt. And you can see on the right what I list here is what is the main physical phenomenon that limits that performance from being scaled further. And you can really see sometimes it will be SRS. For many 915 nanometer application, you're going to have a lot of SRS issues, mainly driven by the length of your cavity or the size of your core. Or for 976 nanometer pumping, it will be more of a TMI limitation. So the goal here is we want to say, how do we balance those limits and how do we try to further power scale this achievable output power by improving and optimizing the fiber design and pushing it even further. So that's what I'm going to be going to in the rest of the talk. So what is the parameter space we have available when you talk about an optical fiber? That's really key because these are all your tuning parameters that you can possibly consider in order to further power scale the system. So you can see here some of the key fiber design parameters. We have the ytterbium concentration, we have the fiber lengths, we have the core cladding area ratios, we have photo darkening, we have core area. And depending on what parameter you're looking at, what I was trying to capture in this table here is you will see whether it has a positive or a negative impact, whether on SRS or a TMI threshold. And what you can see very visually quickly is that the parameter that will be beneficial for SRS to push the threshold higher are going to be gating TMI threshold. So it's actually going to impact TMI threshold. And in any case, eventually it will end up limiting the power. You know, this is very, I would say, a very coarse summary of what you can find across the literature. But the point is the main challenge for further power scaling beyond 2 kilowatt is to balance both effects, which are indeed competing effects when you look at them from a fiber design standpoint. So you really have to play more games in order to try to find out what are the best configurations depending on your laser system. So how did we do that? We took a systematic approach and we created an empirical model. Starting by creating some figure of merit for the existing fiber designs that we are currently offering in the market. And then we correlated our figure of merit to measured threshold on those existing fibers. Then we use those data points to estimate how can we further push the figure of merit for the new fiber design. So what type of fiber design changes can I make to impact the figure of merit, which is going to then give me a way to estimate my achievable output power. And then we can verify those predictions with high power level oscillators and experiments. So in order to do that empirical model, we had to make a couple of assumptions, which are driven by market designs and current market constraints. So I need to be very clear. So first of all, we're going to have to assume the optical to optical efficiencies are around 72% for 915 nanometer pumping applications and roughly around 77 for 976 nanometer applications. Keep in mind that we were trying to take here a conservative approach. So these are not the highest efficiencies that are achievable. We just believe that these are the very conservative efficiencies that can be achieved widely in the field. If we want to achieve 2 kilowatt, we are going to need to have double end pumping and about 2.5 kilowatt of pump power in any case. So that restricts your single end co-pumped oscillator because now you need to essentially add a second combiner with more pump power in order to further scale your output power. The gain fiber length is set around 18 dB. And then we're going to assume that we have a good SRS performance, a good SRS threshold, when we are at 35 dB contrast or higher with the signal peak. And the TMI threshold is defined as it's a lower efficiency relative to pump, and the scaled also with the amount of light we're going to have in the cladding. So these are all assumptions that are going to be built into our empirical model. And we are going to consider now using figure of merits in order to try to empirically quantify SRS threshold and TMI threshold. And don't get me wrong, there are a lot of very elaborate modeling tools out there already published in the literature to get those thresholds. But here we wanted to have a little bit more of a practical exercise or practical tool, so we could do a real-time tuning of our fiber design parameters in order to further push those thresholds. So some of the key fiber parameters that we stated earlier, but these are really the ones that we're going to monitor with our figure of merit, is the fiber mode field radius, the pump cladding absorption, which is related to your ytterbium concentration, the effective cavity length, the laser efficiency, and what we call a TMI gain factor. And what you see on the right is the SRS threshold figure of merit is going to scale proportionally to the effective length and inverse proportionally to the square of the mode field radius, as well as the absorption, obviously. And then TMI figure of merit will scale with the efficiency, inversely proportional to the efficiency, the TMI gain factor, and the effective length. So in other words, what we're trying to do here is we're trying to reduce the FOM. We're trying to reduce this SRS coefficient or reduce its TMI coefficient in order to increase the achievable output power. And to do that, we're going to be able to now tune some of these key fiber parameters, which are directly accessible to us as fiber manufacturers, and try to mitigate both as much as possible SRS and TMI effects. So here is how it's going to look at a first glance. This is the predicted or calculated power capacity of the current double clad fibers that exist on the market. So the graph I'm showing to you here is the calculated output power, achievable output power, calculated. And here is just on the x-axis, I chose to put core diameter. Essentially, what we did here is we took, one of the largest products we have is a 20 micron core diameter fiber. So we said we're going to take that core diameter, and what if we just scale the core diameter to larger or smaller values and identify what would be the predicted impact on the achievable output power. And you can see we have the two achievable output power predictions for 976 nanometer pumping and 915 nanometer pumping. It's a little busy graph, but I think it tells the entire story. The full line is the TMI threshold. So it's going to tell you, let's say, whenever you see the full line, it's going to tell you that's the maximum achievable output power, and it will be limited by TMI threshold. When you have the dashed line, that the limitation mechanism becomes your SRS threshold. So all in all, we have built here all the assumptions from the field. And what we predict is if we take a fiber like a 20 micron core fiber, 400 micron clad design fiber, which is one of our top fiber out there, we predict that we roughly can achieve between 1.5 and 2 kilowatts. And this light gray box here that you see here is essentially the processing window for core diameter. As you know, the nominal is 20 micron core, but the fiber can be anywhere between 20 micron core or 21 micron core. So what we're saying here is the currently achievable, available fiber is going to be also predicted by the figure of merit to be limited, to plus 2 kilowatts or less in the field at whatever one of those two pump wavelengths. And keep in mind that this is a little bit of a conservative estimation because we had to make some strict assumptions from the application, from the field deployment. So it is possible that people or customers can achieve higher powers, but the exercise here is we're going to try to design a fiber on the conservative basis so that it will at least overperform when we give it, when we sell it to our customers. Note, if you increase the core diameter of the fiber, something like another product we have, a 25 micron core fiber with a 400 micron CAD will be right there. You are going to have, the larger core will suppress SRS, but it will lower TMI because of the higher order mode content. Vice versa, if we think about scaling that design to smaller core diameter, for 976 pumping, we can have some benefits of seeing higher power levels, but we're going to have some tricks or limitations when we're going to operate at 915 nanometer, because now we're going to run into SRS due to the core size being smaller. So all in all, in order to consistently and reliably ensure that our customers can operate greater, these fibers to above 2 kilowatts, we have taken an approach where we required new fiber designs tailored to each pump wavelength. So we're going to go here in the details of what our new fibers are offering here. So we're starting at 950 nanometer pumping. As I just mentioned earlier, we really want to try to dissociate now those two pumping wavelengths, because when a customer will want to operate at greater than 2 kilowatt, it's going to be very important now to consider much tailored design. So if we look at the 915 nanometer pump applications, the fiber design we are introducing right now, which is going to enable our customers to operate beyond 2 kilowatt, is a 22 micron core fiber essentially. And this is the generic part number you would find on our website, or you could request that part number. This is what this fiber is going to be selling under. Some of the key attributes here, I just said, the core diameter is larger. So we're going to have about a 20% larger area of the core. The core NA nominally is the same as the current product, the current 20 by 400. So it enables a direct integration with the existing platform. Same for the cladding diameter. And note that the clad absorption is about 27% higher, which allows you to use 27% shorter fiber lengths in your laser cavity. The result is shown on the left. This is again based on our predicted power. Our current product that I just showed on the slide before is the gray line. And what this new fiber here that we're releasing is enabling you to effectively move from this roughly 1.5 kilowatt achievable output power to above 2. So I would say 2.2 kilowatt or higher. And remember, this is fairly conservative. So what we've done is we've effectively, by making those changes in core area and absorption, we've enabled to improve the power capacity of the fiber by about 30% or more. And that's the product that is right now being released in the field to enable customers to further power scale the industrial lasers. We have done a little bit of a demonstration, not all the way to 2 kilowatts, but we have already positive feedback from the field. But what we wanted to do in-house is we wanted to compare the SRS performance and the mitigation of this new design compared to the existing fiber design. What you can see here on the left-hand side is the measured SRS contrast between the current fiber, I would say the 20 by 400 fiber, which is the normal fiber, compared to the new higher power fiber for 915 nanometer application. And what you can see is that this, while the 2400 fiber seems to be taking up a little bit of SRS above 1 kilowatt or higher, in the meantime, in the same systems, the new product is really enabling you to keep your SRS at a very, very low level. So on the right-hand side is a typical SRS spectrum, and you can see there is absolutely no sign of SRS when we use the new design, which is really demonstrating the ability of this fiber to suppress SRS. Now, no, this is not optimized. You could do the same experiment in the optimized laser cavity at 1.5 or 2 kilowatt. We just didn't have the pump power available in-house. So for 976, how do we do that? We are now changing the pump wavelengths. We're saying now we also want to allow the customers who are pumping on 976 to power scale their output power and offer them a robust fiber solution to do that. So now the fiber is going to be a 20 by 400. So we're actually not changing the geometrical design of the fiber. The core remains 20 micron. The NA also remains nominally the same. Same for the clad diameter. So it's a fiber, again, that can be directly integrated in the existing platform. And on the absorption, it's also going to be very similar to the existing fiber you would find on our website. Now, the trick is we were able to maintain the geometry and the absorption while reducing the TMI gain factor. And there is a little bit of trade secret between these gain factors, so I won't be able to necessarily give too many information, but the point is you really can play with the design, reduce this gain factor, and we also paired this design with a significant change in photo darkening. I will go through that in next slide. We have maintained the absorption in this new product while significantly reducing the photo darkening, which is going to allow this fiber to perform at even higher thermal loads while ensuring that there is no power drop over time.
And when we are running out of time, maybe you can tell us the next slide because we are super curious.
Sorry. So I'll just go to the next slide. The point you see, we have again a 30% power increase capability. So we go all the way to 2.5 kilowatts with this design. So the photo darkening performance are going to look like this. The current fibers, are operating around this range. And what we're claiming is we're having a much, much improved photo darkening performance with this new product. So a big improvement here. And if you don't mind, I'm just going to go through my last slide.
Yes,
we, of course, have the matched passive fiber available. So you can find those as well on our website. And we are not only going after power scaling CW lasers, we're also looking into power scaling ultra-fast fiber lasers. So I don't really have much time to talk about this, but it's very important to know that our preview, we are also looking into introducing new product in the next month or two for enabling power scaling of ultra-fast fiber lasers. So you can see here the first list. Please don't hesitate to reach out and contact Coherent and Nufern if you have more information.
Don't hesitate to reach out and contact Coherent or Nufern because they are amazing. It's incredible how much information you gave us in 20 minutes. It was great. And we know what you can do for the members. We know what they can do for you. And all we want is to make these connections, collaborations. It is great to have Clémence with us today. 10 o'clock in Noordwijk Central Control Station in the Netherlands. What time is it for you, Lars, right now?
When I'm on mute, it is 4 o'clock, as you can hear.
So EDMUND Optics, 78 years of history, but I watched the Big Bang Theory, the last chapter, and I see EDMUND Optics logo. You are still a very, very, very relevant, innovative company. Tell us your secret. The floor is yours.
Thank you. So this will be a quite different presentation compared to this very good presentation from Coherent. So mine is more a journey in history and why EDMUND Optics is still around after 78 years. So I'm trying to just give you sort of what has changed over the time, why do we stay relevant? And I think we still is a pretty relevant company. So
do you have some slides for us to see?
Oh, sorry. I'm trying to do that.
That's okay. You go to the bottom of the screen. There's an arrow up. It's green.
Yes.
Says share screen.
I know. I just forgot it.
Oh, it's not your first rodeo. I can see. The floor is yours.
Yeah. So what is happening here is that throughout the history of EDMUND Optics, we have been around for 78 years. We've tried to solve fundamental challenges. So why do we stay relevant? We try to focus on clean energy, safer transportation, environment, and so on. And by looking at these, what optics provide today in the COVID situation, we see that a lot of the diagnostics is using optics. We know that laser welding is using optics. So there is optics all over the place. And the strength with EDMUND is that we have changed what we do over time and what we serve, the market we service. But the thing that stays the same is we still do optics. We do lenses, we do mirrors, we do the simple stuff that all people need. The application has changed over time, so go back in history. So 78 years ago, EDMUND Optics was a salvage company. So we got surplus optics from the military. We took them apart, kept the good parts, sold it back to the military, and the broken parts we sold to amateur astronomers. So we were pretty much the first optics recycling company 78 years ago. This company has been in the family ever since. So it's today managed by Robert Edmund, who is the son of the founder, Norman Edmund. And from day one to today, we still make the optical components. Nothing has changed there. So how do we see ourselves and how do we make a difference? We say that internally that the future depends on optics because we don't really see an application that will have less dependence on optics in the future, rather the opposite. So going back in history, we saw this presentation about fiber lasers. When I started my career, they were in the cradle. They were around. We had a 400 milliwatt fiber laser in the lab, which is far away from the kilowatts that was presented recently. So communication is all fibers. Medical diagnostic is moving to optics. surveillance and inspection is also going into optics. So wherever you turn, it's more and more optics. So that is how we stay relevant. We just follow the market, and we see that the market for optics is just increasing over time. So when we look at the different applications that we service today, since Edmund has been around for 7 to 8 years, we have serviced the research market. So we have a big footprint in research and development university. A lot of automation in the industry. When people make cell phones, TVs, it's all about optical inspection, and we're in that with machine vision, and we service the electronics industry as well with optics that is doing chip trimming and so on. And the biggest on the market right now where we see a lot of potential is advanced diagnostics. And the current COVID situation is showing that that is really booming. So PCR and similar methods is just using a lot of optics, and when they turn on, Edmund has been ready. And unfortunately, the COVID situation and defense sort of go hand in hand, because with a lot of volatility on the market, a lot of uncertainty, a lot of countries is sort of beefing up the defense industry, and that is also using a lot of optics. So we service a lot of different applications, and that is how we stay relevant year after year. So what do we really do? So we started the company back in 1942 in New Jersey, USA. And over the year, we have today 5 major manufacturing sites focusing on different type of products. And the philosophy behind it is we try to do what we're good at, which is optics, and we try to source the rest. Because we know that companies like Coherent and others are really good at fiber and fiber lasers. So we don't go into that market because that is not our strong suit. When we look at optical components like lenses, mirrors, we are really good at that, and that is where we stay. So what is the business model for Edmund to sort of maintain its position after so many years? Over the years, we have developed a large inventory of unique optical components. Today, we have about 34,000 different optical components, unique ones sitting in the inventory that you can get delivered the next day. For any R&D project, you can get about 96% of the orders shipped the same day. And that is how we service the R&D, which is the foundation of all optical industry. So without R&D, without the prototyping, there will be no mass production. So here is how we serve the researchers and the product developers using this business model. When they go to the next level of their development, then they might want something that fits into an instrument, which is quite typical. So you have seen a lot of these medical instruments. They look pretty nice because it needs to convince safety and other aspects, and the standard products don't really fit. So what do? We use the big inventory to make modifications to allow us to service their product by quickly modify what we have. So we use the big inventory we have as raw material for custom optics. And this we can turn around in about a week or 2 weeks, a custom optics within limitations. So once we move from that and you go into production, then we just turn to our factories around the globe, and we make millions of components every year. And it doesn't matter if it's a stock component or a custom component, we do them all. And what we are really keen on is telling the customer what we're good at, because that is what we should make, and what we are not good at, which preferably we source. But as a big company on the market for many years, our supply chain is very strong, which means that you can source a lot of components that we don't make through us. But the vast majority of all optics that you see in our offering is made in our factories, which is a surprise to a lot of people. And also when you say about optics, it looks quite simple. We spend a lot of money on research, applied research around optics manufacturing, optical components, and similar. And the reason is we need to stay relevant, because we don't want to have a newcomer coming up and say that we have something better than you. So we just need to defend our position. It sounds a bit defensive to do R&D, but after 7 to 8 years doing it, we know it is an offense that is working. So a huge inventory and a lot of research spend. That is how we stay relevant here. Going on to the factories, what we are doing and how it has changed over time. So we have done spherical and asphere lenses for, not aspheres, but spherical for more than 50 years mainly in our Singaporean factory. Aspheres we have done since early 2000 or 2010-ish. So we have a lot of experience there as well. Back in the days when Singapore was building up their optics industry, the Singaporean government invited German companies to build up industries there. And the company that we acquired many, many years ago is one of those companies. So Singapore wanted to enter the optics manufacturing. That's why you see a lot of contract manufacturing there. You will see competitors to ours like Key Optic being there. You have Zeiss being there. You have, you name them, they're all in Singapore. And people are asking why Singapore is so expensive. There is a lot of know-how there. That's why you stay in Singapore. And one thing that we've learned over the years is vertical integration is important. So we take from the raw glass to the finished product, which means that we have all the steps in the factory. And that is how you stay focused on what you do, which means that you can cut cost, you know what you're good at, you improve the process. And after 50 years, we're pretty good at it. Looking at the other product line that we are really focusing on is flat work. We have done that for about 40 years. And the big application in the past was cameras and binoculars and similar. With the digital camera, the application has switched to something different, but I will not go into that. But what we learned over the years is doing sub-arc second prisms in super high volumes, because that is what you needed for binoculars to make sure you don't get any distorted images or get the user headaches when the tubes don't align. And from that one, we learned how to do beam splitters because it's a simpler form of a prism. It's only 3 angles, so that is simpler. And again, we do everything in-house. And we still invest a lot in coding development on beam splitters, for instance, because that is how you stay relevant. With the new laser types coming out, the demand is increasing, which means that we need to have coatings that sort of withstand the never-changing demand. Also, there is a lot of 3D head-up, 3D metrology and head-ups displays that is also using very extreme beam splitter cubes to overlay images from the real world with the artificial world in augmented reality. So that is another area that we're really focusing. I'm still doing good on time here. So when it comes to coding, it's the third field that we're actually putting a lot of R&D money into. It's coatings. When you start a new business, assume that you want to start a new business doing, say, A-spheres. You need to have a supply chain for the glass. You need to set up a machine shop that is machining the glass. You need to have polishing of the glass. You need to have coating. So the capital investment that you do is phenomenal. And to stay relevant as is the theme in this one is that you need to follow the demand for the coatings. So during telecom, it was really hot. We're talking back in 2000 when I started my career. It was really hot to do coatings around 1550 because that was the best thing, and the second best was 1300 nanometers. Today, we see all the way up to 20 micron. We have far infrared imaging, augmented reality, coatings that is partially reflective. We have coatings that are polka dot, you name it. And to get all that, you need a lot of different coating chambers and different coating type and different coating capabilities. And how do we get all that? Yeah, that is being in the business for 7 to 8 years. So we didn't invest everything at once, but a continuous investment in the company, adding coating capability over time, means that we can service pretty much any application today. It's very few coating capabilities that we are missing. And for those, we have strategic partners that is helping out. And as you might have seen in the news, we just formed a strategic partnership with Schott in Germany. So we have the know-how and we have the right partners to sort of stay relevant. And I would like to just to finish with a slide here about a case study. It is around a Danish company, Danfoss, This is actually an application where I started my career back in the 90s. It is to analyze gas in the smokestack to optimize engine performance. So Danfoss is making a gas sensing device, and we help them to develop and make the optics going into it. And this optics is facing the smoke in the gas, in this gas stack, which means that it's exposed to a lot of nasty gases and high temperatures. But again, it goes back to experience of what you have seen in the past. So we've collected a lot of knowledge over the years, which means that we can address new applications. We believe this will be a really big application in the future because the legislation around shipping is about to change around the globe, and this type of instrumentation will be critical. Danfoss is just one of the people servicing this market, I may say that, but it is a good example of what we do. So people come to us with a problem and we find the optical solution for them. So that was my short presentation. I think I didn't use too much time.
You were great. You use exactly 10, 15. Perfect. Of course, precision optics, precision is your business. I shouldn't be surprised, Lars. I have a lot of things to talk to you about. The first one, I have here 570 companies, EPIC members who want to do business with you. What can you do for them and what can they do for you?
So that is a question for me or for them?
For you and for them, but mostly for you.
Yeah, so typically how it works is that people come to us with a problem and we try to help them out. Sometimes we have the capability or we have someone in our network that can help out. So for instance, if you want, cinema is hot today because people are watching streaming cinema. And today the cinema is wanting to have narrow depth of field because that will improve the compression they can use. And the customer came and said, can you help out? And we said, sure, our A-sphere capability is what you need. So you can improve your lenses using A-spheres. And that is how we help them. Are we the end supplier? We got part of the order, but not the full order. So we're part of the solution. That's how we see ourselves. We're helping the people find a better solution for their application. That is how we help them.
In my past as a scientist, I have been a customer of you, and I was always very happy with the turnaround time. Very, very impressive on that. As a researcher, that was a gold mine. But now, as the CTO of EPIC, I'm seeing a lot of trends. And one of them is that many companies in the world are investing on IBS coating at the same time as the femtosecond laser market is starting to grow quite strongly. Is there a relation to that? Do you see, because I know that the IBS coatings of EDMUND optics are also very, very good. Do you see a relation between the ultra-fast lasers and the IBS coating growth?
I think it's highly related. This is not my field. We have a division that is handling laser optics. So, but I know roughly what it is. So yes. So when we started to go into the ultra-fast optics, designing that, we didn't today find a more viable solution than IBS. We know that you can do it with magnetron and other technologies that we used to have in the past, but we decided to exit that for many reasons. So today we're doing IBS instead, and we are very successful with that. So ultra-fast is enabled by IBS and magnetron. So I think that is a key for the future. Indeed. And looking at surgery, which is another application, femtosecond laser is coming there to do your eye surgery. So
you mentioned Singapore a couple of times in your presentation. This morning I was in Singapore because I've been all around the world in 24 hours. I've been already doing this almost for 19 hours. You know, it is crazy. And I can tell you that you are right, that many of the companies doing optics are in Singapore. When it comes to the aspherical optics, you don't have much competition worldwide. There's a bunch of good companies like you that are making a difference. Is there market for all of them, or do you think that the competition in the spherical optics started to be very fierce?
Yeah, so we know our competition and we collaborate a lot because we have slightly different capabilities. We consider us the great one, but there are many good ones. And we know that there's market for all of us. Because it's a fast-growing market, because what we're seeing is in imaging lenses and others, they're hitting the limit what you can do with spherical optics. And the next step to improve the performance is going to A-spheres. That is one trend that we're seeing. The second trend is around laser machining. It's more and more A-spheres there and freeform optics. So I think we have seen the start of that type of optics. The big competition for us is molding, and we don't do molding today.
Not yet. I heard the word today. It was in between the lines. Do you want me to suspect something, or?
Yeah, so we always monitor what's happening in the market and where the opportunities are. A few years ago, we entered the molding market with the infrared optics. So we do sort of that already, but doing oxide glasses, which is what you use for typical laser machining, we don't do that today. Not today.
Thank you very much, Lars, for a great presentation. Really, really inspiring. We could talk for hours. I was going to ask you about quantum technologies. I was going to ask you about the next stage for laser beam shaping. But of course, we have to keep the time. The time is the essence today. It has been great talking to you. I hope to come and visit you very soon as the whole world goes back to normal. And we go with the program. We continue. It is 10:20. I'm so strict with time today. Dahv Kilmer from NLIGHT. I really love NLIGHT. Thank you very much for being with us. It is 10:20 in the Netherlands. What time is it for you?
It's 1:20 p.m.
1:20 p.m. or also called Time to Rock. The floor is yours.
Okay, let me share my screen and make sure you're seeing it.
Fantastic.
So, and great. Well, first I'd like to thank the organizers and EPIC for the opportunity to participate in this unique event. As like many of you, I'm working from home, as you can probably tell from the COVID haircut. This is the first opportunity I've had to participate in a virtual conference. What I'll tell you today is about advanced metal processing enabled by fiber lasers with programmable or tunable beam quality. I'd just like to do one slide to introduce NLIGHT. We're a vertically integrated manufacturer of high-power semiconductor and fiber lasers. We were founded in 2000 with the semiconductor laser products and entered the industrial fiber laser market in 2014. We're headquartered on the west coast of the US in Washington State, and we have a global footprint for manufacturing, sales, service, and applications. Last year, our revenues were nearly 180 million, and since 2014, we've been averaging 23% growth a year. We're up now over 1,000 employees and active patent portfolio. And today's talk will really focus on industrial applications, and we also have products that serve microfabrication, aerospace, and defense markets. So what is the motivation for tunable beam quality? It's been known for quite a while that materials processing performance depends on the beam characteristics, things like the beam size, shape, divergence. These are some images from a 2007 trade journal article showing welding results with a CO2 laser comparing a Gaussian beam with a donut-shaped beam. In fact, if you look across all of the key applications, you find that optimizing the beam characteristics are very important for them. The largest industrial market is sheet metal cutting. What this graph shows is sort of representative cutting speed as a function of metal thickness. And it's known that if you want to cut a thin metal, you choose a small beam to get a very intense spot and you maximize the speed, but that small beam cannot effectively cut thick plate because the kerf is just too narrow to get the melt out. So in that case, you have to go to a larger beam. You can extend the thickness range, but you pay a substantial speed penalty for thin metal. So most tools choose some beam in the middle and essentially have non-optimized performance nearly everywhere. So the idea is that if you could tune the beam size, you could stay at the maximum of this speed curve over the full range of thicknesses and have a much more versatile or universal tool. The second largest market is welding. And there it's known that a small beam gives you a deep penetration or keyhole weld, as shown here, whereas a larger beam will give you a more shallow conduction weld, which can be desirable for weld quality as well as aesthetic reasons. And finally, the most important emerging application is additive manufacturing or 3D printing. And in a typical part, you have different feature sizes. And in order to maximize the build rate, you want to choose the spot size to match the feature size as well as the thermal conductivity of the material being processed. That consideration actually applies to other fine material processing applications as well. Unfortunately, most lasers have fixed beam characteristics, and so various technologies have been developed to allow the beam to be varied. The simplest is just manually changeable free space optics, things like a process head with a changeable focus lens. That, of course, is a low productivity solution and also has a reliability risk because every time you change optics like that, you risk contamination of the lenses or the head. More amenable to automation are various motorized free space optical solutions, things like zoom lenses or zoom process heads or fiber couplers or switches with motorized lenses or mirrors. And more recently, some all fiber solutions have been developed that involve beam combination of multiple lasers to make a sort of aggregate beam shape. That's sort of indicated schematically here, where you see you have a delivery fiber that has a central core shown in blue and an annular core shown in red. And you have a combiner that launches different lasers into these different regions. And so at the time of manufacture, by choosing the powers launched into these different zones, you can get it, have a different beam shape. Now, of course, after manufacturing, you can't change that. You can always turn off some of the lasers to get a different beam shape, but that's at the cost of, not using the laser power that you purchase. What these methods all have in common is that they've demonstrated the utility and the value of being able to vary the beam, but they all increase the complexity and cost and or degrade the tool performance and reliability. And as a result, most tools on the market today still use a fixed beam. And they just live with the non-optimum performance or lack of process versatility. In any tool, that means you often have to limit the job mix, and so the end user might then have to purchase multiple tools. So we took a fresh look at this problem and developed a new technology. The product line is known as CFX, and it's an all-fiber technology that allows tuning of the beam characteristics directly out of the delivery fiber from the laser. These are actually CMOS camera images of a 4 kilowatt beam, switching among the different shapes. And like the sort of bouncing of the color is simply rescaling of the camera gain in order to keep things on scale. Actually, 100% of the 4 kilowatt power is available in all of these different beam shapes. Because this is an all fiber silica device, the power scaling is actually limited only by silica fiber, just like the fiber laser itself. And so currently this is available up to 12 kilowatts. The key features are that you have a wide range of beam sizes and shapes, as you saw in that video. In the particular fiber design I showed you, the beam size goes from the smallest sort of flat top, about 100 microns, out to over 300 microns in this large donut. So you have a range of different flat tops, donuts, shoulder-shaped beams. This switching is very fast. You can go from the smallest beam to the largest in less than 30 milliseconds. What this means is that you get to choose a different beam, not just say for thick or thin sheet, but for to optimize each process step on the fly, things like piercing versus cutting or straight versus cornering. Being all fiber, the technology is highly reliable. We've shown more than 13 million beam changes with no measurable change in performance. And the last, this is actually not a product, it's a whole platform. It's very versatile and a wide range of specs are available with different fiber designs. We actually introduced the first products in this line and at the end of 2018, and it was very rapidly adopted, and a number of CFX-based tools are available from leading integrators worldwide. I'll actually show you some of their results momentarily. In fact, we'll now go into applications of this technology. And I'll pick, again, these highest volume applications. We'll start with sheet metal cutting. This is, as I said, the largest application for industrial lasers, and within that, oxygen cutting of mild steel is the dominant application. And this is actually the one place where fiber lasers have not managed to fully displace CO2 lasers. And the reason is that CO2 lasers still give a better edge quality when cutting thick mild steel. So one of the first things we want to do with this technology is apply it to that, that cutting application. And so what's shown in the top is a 25 millimeter mild steel cut with a standard fiber laser, sort of a normal 100 micron beam. And below it is the same material cut with this large donut beam. And you can just see with your eye the much better edge quality. In fact, it measures out to have a surface roughness that's better by a factor of 3. In fact, we wouldn't even consider this upper standard fiber laser to be a successful cut, because do you see all this sort of slag at the bottom of the part? That's a re-solidified material. Remember I mentioned that with a small beam, you can't get the melt out of the kerf. What happens here is it re-solidifies and essentially welds the part back into the skeleton, and so it has to be sort of hammered out. So this is not amenable to sort of 24/7 lights out automated operation. With the CFX laser, with the much better edge quality, you get reliable part drop. You get all these benefits with actually no speed penalty. If anything, the CFX laser is actually a bit faster. One of the first customers for this laser is the HK, which is the largest tool integrator in Korea, and they make both CO2 and fiber laser tools. So they wanted to naturally compare. So here are their results cutting 20 millimeter mild steel with CFX with CO2, and they're really indistinguishable. Now, they don't just look at the parts, they measure them, and by all their measures, the parts are indistinguishable. So what this shows is this tunable beam quality fiber laser has removed the last benefit of CO2 lasers in this important application. Now, the key thing is that tool that has this laser gets the CO2-like performance on mild steel, thick mild steel, but then when it goes to thin metal or other metals, it gets all the benefits of the fiber laser, the faster speed, the more reliable operation, et cetera. So there's really, again, no trade space there. In fact, with CFX, you get a larger process window. This is the focus position process window. With the standard fiber laser, it's ±1 millimeters. With CFX, it's ±2. And so that means a more tolerant process to variations in optics or material. So what we're seeing here is this sort of no compromises performance when you introduce this new capability of tuning the beam. And this is leading to much more higher performance universal tools. Let's now look at welding, which is, as I said, the second largest application. And with welding, you can control the weld shape and the weld depth by changing the partitioning of the power between the central core and the sort of outer ring structure in the beam shapes that I showed you before. So what this shows is 3 welds all done at the same speed power, 3 kilowatts, same speed, and putting more and more power outside the central core. And you can see that the weld shape changes correspondingly, allowing you to go from a more keyhole-like weld to a more conduction-type weld. This ability to control the weld depth and penetration has several benefits. You significantly reduce the spatter, porosity, and cracking, and also it can improve the weld stability in cosmetics. Now, you don't get all these benefits simultaneously for all materials. In any given application, you get to optimize the beam for what you want to optimize. So again, I'll take one application that's quite important, which is steel welding. This is actually a drivetrain part. And this is using just a conventional laser beam, and you can see all of these sort of spatter particles coming off of the weld. This spatter creates several problems. First, this material loss from the weld reduces its quality. You get pores, things like that. In addition, these particles go somewhere, and often they contaminate the finished part, which can require post-processing or cause latent failures. You can imagine you don't want metal particles in a drivetrain. They can also contaminate the fixtures, shielding, and other surrounding tooling, which increases the need for consumables and maintenance, and thus increases cost. What causes spatter is this keyhole being created by the laser can occasionally close from sort of surface tension and gravity, and then open explosively and kick off the spatter particles. This is the same video I showed you. Now let's see when we use the CFX laser and put some of the power outside the core. You can see here the different beam shape, and importantly, in the video, you can just see with your eye how much you reduce the spatter. It's by reduced quite dramatically. The mechanism for that is that the power just that you've partitioned outside the core sort of opens up the top of the keyhole and prevents it from closing. And so as you saw just in the video, the spatter particles are much less numerous. What you couldn't see, but when you investigate the parts, you find that those particles are also smaller and adhere less strongly to the surface. So it's you can remove them much more easily just by brushing as opposed to, you know, a grinding type operation. So the net effect is you get a higher productivity for two reasons. First, you can now increase the laser power, meaning increase the speed of processing without spatter, because the spatter often limits how much power you'll use. And then you also reduce or eliminate these post-processing steps. Some other benefits that you didn't see in the video are you get a wider process window, as we talked about for cutting. You also have a gap bridging capability, so you can reduce the tolerances on the parts that are going into the weld. And also by sort of engineering the heat input and controlling it carefully, you can prevent other types of defects. You can read more about this in a recent Industrial Laser Solutions article called "Is Beam Shaping the Future of Laser Welding?" And I'll leave the answer to that as an exercise to the reader. So hopefully in this short time, I convinced you that CFX is really a breakthrough in fiber laser capabilities by introducing this rapidly programmable beam quality in an all-fiber design. We've already seen very significant advances for metal cutting and welding. Tools are on the market, very high performance, versatile tools. And also this technology has been widely recognized in the industry, including with last year a PRISM award for industrial fiber lasers. And with that, I'll close and be happy to answer any questions. Thank you.
Thank you so much, Dahv. That was really, really impressive. It is great to have disruptive technology, but it's also great to have disruptive technology for great applications. And you made that very, very, very clear. The first question is the EPIC question. I have here 572 companies. They want to do business with you. What can you do for them? What can they do for you?
Yes, so that's a good question, and there'll be a diversity of answers, much like there's a diversity of companies. Actually, one thing I didn't emphasize is NLIGHT, in addition to selling fiber lasers, we actually sell the key components that go into fiber lasers, as well as direct diode lasers and diode pump solid state lasers. So we sell, semiconductor pump lasers that, as well as passive and active optical fibers, and then the full fiber laser product line. So we can actually serve customers all up and down that value chain, from sort of tool integrators who buy our fiber lasers to put into these high performance tools, through laser companies that are making their own lasers, be they fiber lasers, direct diode, or DPSS lasers, who use our high performance components. A real advantage of that vertical integration is we drive a lot of volume, and that allows us to invest in innovation and as well as manufacturing and cost control. So it sort of benefits the entire ecosystem of laser producers and users.
So when it comes to the all fiber beam shaping, which was fascinating, there is a lot of things here that I am wondering about. The first one, you talk about fast switching. You said 30 milliseconds, I think you said. What is the limiting factor here?
What is the limiting factor? Okay, actually, interestingly, 10 of those milliseconds is simply our internal communication delay. You know, we've set it up with various hooks where the user can change it by a GUI or a command or a hardware signal. And so just when we targeted how fast we needed to go, we had a total, and it turns out 10 of that milliseconds got allocated to that. So in principle, we could go faster by shortening that delay. The rest of it is essentially the kind of, we achieve this tuning by essentially perturbing the fiber, and it's how we sort of actuate the perturbation. We actually have a Laser Focus World article on this, which I can point you to describe it in more detail.
No, for me, I was more interested about the application behind it. I'm here to make connections. In which application do you foresee that you need a very fast switching of the beam shape?
Yeah, there are a couple. First, as I mentioned, in piercing versus cutting, in thick metal processing, the pierce before you cut can consume a significant amount of time. And so I showed you, you want that large beam shape for cutting thick mild steel, but actually you want to start with a small beam shape for maximizing the pierce speed. So what you can do is go to the, speed up the pierce dramatically and then expand the beam, go to the cut. And so on a large sheet, depending on the parts they're making, they can do up to 1,000 pierces. So if you're wasting time on the pierce, it actually adds up into your total part cost. So that's just one. Another is I told you the additive manufacturing example, where if you're making a part and you have these different feature sizes, you're going to want to be able to just toggle very quickly, depending what part of the part you're in.
The final question I need to ask, I'm sorry, I need to ask, are you putting special light modulators out of business?
So the spatial light modulators are not widely used in sort of high power industrial applications. And so I think they're, people are pushing in that direction, but we're not running into that a lot in industrial tools. I think, as you kind of pointed out, actually the EDMUND talk, it was pointed out, the sort of explosion in applications, I think is going to continue to drive an explosion of technologies to address those applications. Obviously, technologies will become obsolete, other ones will become better, but I don't think this will completely, eliminate the need for spatial light modulators. They have actually a lot of very, very cool and current applications.
I had to congratulate you for the disruptive technology. Also, my friend Fabrizio Ferranti from Jollivet is also congratulating you for the disruptive technology. So you're looking for eye safety solutions, go to Jollivet. He just paid you a compliment. Thank you very much, Dahv. It was great to have you. We stay in the US and now we go to Florida. We go to LightPath and we go to my very good friend, Sam Robben. Sam, thank you very much for being with us. It is 10:40. We're exactly on time, 10:40 in the Netherlands. What time is it in Florida now?
Okay, it's 5:40 in the afternoon.
The floor is yours.
Thank you. Okay, let me set things up here and get started. And meanwhile, I have to ask, by my calculation, you are awake for about 20 hours? Is that right?
Yes, that's right.
Okay, so if you fall asleep during the presentations, that's perfectly fine with me.
It is impossible. It's not going to happen. But I take the challenge. If you make me fall asleep, I owe you dinner.
But hopefully everyone else can stay awake. So thanks for the opportunity. This is very exciting. The whole idea of the 24 hours talk is fascinating, and your brain must be exploding from everything you're learning and hearing from everyone. So great job on that. I'll talk about chalcogenate glass and the role LightPath plays there, and in leveraging our years of experience in molding precision glass lenses with regular glass, and how we extend that into the IR, and specifically how chalcogenate glass gets used in thermal imaging and probably displacing germanium to some extent. So I'll talk about LightPath, I'll talk about the chalcogenate glass in general, our manufacturing of chalcogenate glass as a vertically integrated manufacturer, some of the characteristics of that, and our products and final products and their benefits. So LightPath's history goes back all the way to 1976, where back in Corning, precision glass molding was originally developed. And through a few different acquisitions and mergers and rollovers, LightPath ended up acquiring this technology together with a few other technologies, and for nearly 30 years now has been producing high volume, cost-effective precision glass molded lenses, or primarily lenses, as well as other components. Throughout the years, LightPath has had many innovations and many developments, all the way from the materials, the processes, developing our own molding machines, and many other different things. Part of those include in 2005, when we already dipped our toes into chalcogenate glass already, and we developed what we called the BD2, which is a chalcogenate glass with some mix of germanium in it, and started molding small aspheric lenses with that. Later on, through the acquisition of ISP Optics, a well-known infrared company, we expanded our manufacturing capabilities in the infrared and have really been growing aggressively in that area. to that extent, a couple of years ago, we started producing our own BD6 chalcogenide glass, which is a germanium-free version of chalcogenide, and is a, as I'll speak about later, is a version of chalcogenides that we have optimized for use in molding. And therefore, we're able to take the many years of experience in molding regular glass lenses and really expand that into the infrared and offer a very cost-effective solution now for any thermal imaging applications in terms of the optics. So what is chalcogenide? It's an amorphous compound that is based obviously on the chalcogen elements in the periodic table. It's an alternative to the regular crystalline IR material, the zinc selenides, sulfide, germanium, and so on. Has high transmission in short, medium, and long wave infrared, and all the way down to the near IR at 1 micron. And specifically for us, what attracted it to us is not only the other technical advantages and cost advantages in chalcogenide, but the fact that we can mold it into a final product. So we can have a much more cost-effective manufacturing process for lenses in those wavelengths using our molding technology and this glass. So all of us grew up and studied on using the crystalline materials for infrared optics, and germanium is probably the most well-known in the thermal imaging world. Zinc selenide, zinc sulfide, as the previous speaker talked about, CO2 lasers, had a massive market there and still have, and many other materials. Those materials have a few limitations. The thermal sensitivity, which means that if you have, for example, a camera lens, you would need to refocus it when the temperature changes outside. A very big disadvantage when you have the camera lens mounted on a UAV on a plane. The processing throughput is lower. You have to use traditional grind and polish and single point diamond turning techniques. Those are all subtractive techniques. We're all very familiar with them from the optics world and from every other materials. The weight is a disadvantage, and the prices are not only high, but very volatile. And that comes from the nature of the source of those materials. As opposed to that, chalcogenide is a glass, which means it is mixed together and baked in an oven to be produced. It is athermal and passively athermal, so means it's 13 times lower thermal constant than germanium. It can be molded, which again for us is the biggest advantage, has a lower weight and altogether lower material cost. All of those really lead to a lower cost of ownership or general cost altogether for the customer. Some comparison of BD6 with germanium. So of course, in the manufacturing techniques, both can be single point diamond turned and grind and polished, but the BD6, as I've mentioned, can be molded. It has a lower refractive index as well as some higher dispersion compared to germanium, but the dispersion can be easily addressed through some small diffractive patterns that are also molded onto the lens. The transmission is slightly better because it goes down to the near IR and much closer to the visible, so that allows for more multispectral imaging. And the hardness is a bit, so the material is a bit softer than germanium, but that is overcome easily using DLC, diamond-like carbon coating, which we offer for the front element of the lens. So, as I mentioned, we produce the glass in-house, and part of the reason for that is we wanted, first of all, to produce a glass that is optimized for molding as well as for diamond turning. So the glass we produce for our use and processing ends up having the same refractive index whether we process it through molding or through diamond turning, which gives a very big advantage because we can now process quite a few of the elements in a complete assembly through molding, as well as some of them through diamond turning, and not worry about the differences in the output. Something that we have seen when we try to use other glass. Additionally, the high purity materials that we use and the control we have altogether on the melting and annealing process allows us to have a much better consistency that is a good fit for our internal uses when it comes to molding the glass. Some of the technical properties that we all as engineers tend to look for and to read about, but I just emphasize that, you know, two things that are typically unfamiliar to people when it comes to chalcogenide or the coating. So chalcogenide can be coated both with a high efficiency anti-reflective coating as well as a DLC coating. And the DLC coating is really a game changer in terms of use of chalcogenide, since it allows you to have now a complete assembly, including the frontmost element, be from chalcogenide. And if you take the 13% less weight that you have and you multiply it times number of elements that you have there, it becomes already pretty significant in terms of weight saving. When it comes to processing, there are really the two paths of diamond turning and molding. From our point of view, the initial part of melting the glass and producing the ball is the same for both. From there, if we go down the traditional diamond turning path, we have the coring, we have the curve pre-generation, and then the final diamond turning. The diamond turning, we all know, has some trade-offs to it. It's a very high accuracy process that has really changed the world quite a bit in many areas and in many materials we can use today in optics, but also has a fairly low throughput and accuracy that depends significantly on the environmental conditions where you do the diamond turning and your manufacturing environment. Molding, on the other hand, is something we've been doing for many, many years. We mold thousands of lenses a day, have probably molded many millions of lenses to date. And for that, we have a mold production. So we produce the tooling and the mold itself, which has a lot of know-how that accumulated over the years and is very similar to whether we mold chalcogenide or regular glass. And we take the preform and we grind and polish it, mold it, and then have really directly from that the final lens ready. And then whether it's diamond turning or from molding, we can coat it with both AR and DLC, where some lenses have on one side AR and on one side DLC. So in summary, LightPath, as a vertically integrated company, offers lenses made of chalcogenide, where we produce our own material that allows us both a lower material cost, but also a very high controlled process. And it allows us to take this material and interchangeably produce from it lenses using either diamond turning or molding. And here again, we take the very well-defined and tested technology of molding lenses that we've been doing for many years and extend that into the infrared world. So we can see why, to many degrees, chalcogenide is replacing germanium or displacing germanium as a go-to material for thermal imaging. And the offering of our products, which goes all the way from the individual lens with a molded or diamond turned to complete assemblies for thermal imaging. Thank you.
Thank you very much, Sam. Thank you for a great presentation. I had the honor of interviewing you a couple of weeks ago, and it was really great to also hear the story behind LightPath, a publicly listed company.
Definitely.
And I really enjoy seeing the message of chalcogenide optics going into replacing germanium. The first question is obviously the EPIC question. What can they do for you? What can you do for them?
Definitely. So I'll start with what we do for them as a bit of a selfish point of view. But, what we do and what we do best is offer cost-effective, high-volume optics. So we're able to produce in any of our 3 factories around the world, different types of glass, different type of materials and finished lenses in a very cost-effective way. A molded chalcogenide lens, for example, can be anywhere up to 10 times cheaper than a similar functioning germanium lens. And that savings comes both from the material itself inherently, but also from the manufacturing technique and from leveraging the molding capability. And the same extends to our classic glass molded lenses in the visible, in the near infrared, if it's for telecom, if it's for medical, and for any application really that needs lenses in a volume, we can offer that.
I
In
have
terms
seen,
of what, sorry, go ahead.
Go ahead. I have seen a great push on the automotive sector. I have seen a great push on the LiDAR, night vision. I think that the sky is the limit. And I have two questions from you.
Sure.
The first one is from EDMUND Optics. Lars, what's on your mind? Let me unmute you first.
Yes. So the question is, chalcogenides, since we both worked with that material in the past, are you able to recycle the waste? So when you...
Yes, it's definitely a big part of germanium has always been recycling the germanium, and that comes inherently from the high costs of the materials and the need to do that. Our need in recycling chalcogenide is much smaller. When we mold it, the waste is significantly lower, orders of magnitude. And when we diamond turn it, we're also able, using a combination of the techniques, to really reduce significantly how much needs to be recycled. There is work being done on recycling chalcogenide. It hasn't, neither for us nor for other manufacturers, has got a lot of attention, because the economic drivers there is less. The cost of the material is much lower, the waste is less, so it's not needed as much.
Thank you.
The second question is from Ficontech in Germany. Greg, what's on your mind?
Thank you, Jose. Hi, Sam.
Hey, Greg.
So I remember chalcogenide fiber being researched at Southampton University in the UK 30 years ago.
Yeah.
Why the delay? Why is chalcogenide only really coming to the market? Or are we looking at very different material performance requirements between fiber and proper optics?
Of course, yeah. Well, first of all, let me congratulate you on being able to go through the corona sitting on the beach. That's not something most of us can do, so well played. I think there are differences in the material between the chalcogenide used for fibers by companies such as IR Flex here in the US and the chalcogenide for lenses. They're fairly different compositions of chalcogenide. But I think that as it comes to just about anything in our industry, and that's part of the beauty of our industry, is we have so many different technologies. And like you said, you heard about chalcogenide so many years ago. It takes sometimes a long time for the right applications and for the right demands to come into play to make some of those technologies attractive. Here, thermal imaging is, today significantly different than what it was many years ago. Part of that is because of the detectors as well. So, years ago, a thermal camera included a nitrogen tank and a 50-pound backpack, back when I was in the military, at least. Today, if it's because of the detectors themselves, or because of the optics or lenses or different advances, it's completely different. So if the detectors are much cheaper, there's a drive for much higher volume of optics, and then the interest in chalcogenide and materials like that is much bigger.
Thank you.
Sam, when it comes to thermal cameras, I have to ask. This is kind of the thing that is difficult not to ask. Did you notice a change in the market? Did you notice some more interest? Did you notice some more people asking?
Definitely. And as a public company, we also share this information with our investors and with the world. And we have definitely seen a direct impact to our sales and to demand because of this. And what we're seeing is both companies that were making contactless temperature measurement devices beforehand, now making much more of them, and companies that beforehand were not thinking about making contactless temperature measurement devices, but were making thermal cameras or different thermal imaging devices, are now saying, wait, we can also make a temperature measurement device, and we can sell a lot of those. So we're seeing demand across the board. And we've been actually selling at capacity, and we're working at 3 shifts in each one of our factories now in order to be able to deliver on the demand. But yeah, I think that has really changed the world in terms of the temperature measurement. If a temperature measurement device, a camera or a small handheld device, needed to just use germanium or diamond-turned lenses, the cost of those would be very different. And what we see is that chalcogenide enables that technology quite a bit. And the timing of that now is really interesting, definitely.
It is also great to have one of your partners. It's great to have AMS Technologies, Thorsten. I have to say they do a fantastic job advocating light path worldwide.
Thank you.
Thorsten, from the European perspective, what have you seen as the market uptake for chalcogenide optics?
Yeah,
we're seeing it. Oh, sorry, go ahead.
Sorry. So we see a lot of projects here, especially here in Germany or in Europe for firefighting applications, for person detection, for even fever testing and all that stuff. So it's great to have the PD6 material now available.
Sam, you are doing a fantastic job. You have a great company. You have great people. I would like to say hello, Devin, and he's watching me. Thank you very much for being in EPIC, Sam.
Thank you, Jose. Good luck staying awake for.
Oh, come on. Do you see me tired? Do you see me tired?
Oh, Sam? I've never seen you tired. You're always full of energy.
This is going to be a great meeting. And you know, the next one is a very good friend of mine. Robert, thank you very much for joining today. Intel is in the room. How are you doing today?
Well, Jose, it's great to see you. I can't believe you look more awake than I do. I don't know. This is really amazing.
It's exactly 20 hours now. I can tell you I could do this for 48 hours more, but don't tell Carlos because he could actually take the challenge. Thank you, Robert, for being with us today. From the point of view of having Intel in this room is a dream come true, but having you in the room is even better. The floor,
Jose, you're the best.
Of everyone is yours.
Thanks so much. So yeah, so I wanted to talk a little bit about integrated silicon photonics for high volume data center applications. As you know, we've been kind of in production for several years now, and I wanted to give you an update on what we're doing today. But let me maybe start off with the basic motivation, and it's all about data, right? I mean, it's wonderful how much data, Jose, we're generating here through this video chat. This goes all the way back to the data center, obviously, where it needs to be processed, analyzed, and then streamed back. And what we're seeing, and I've talked about that in the past, is really that there's a lot more traffic inside the data center than there is to and from the data center, right? And so we see this CAGR, this growth rate of about 25% per year, but actually the hyperscalers are seeing even larger growth rates. We've seen around 40 to even 50% per year. And it's going to be interesting to see with the virus, when the numbers get updated, how much more traffic increase there's been due to all of us, working from home and having a lot more, driving a lot more need for data. The other point that I like to make on this slide is that really there's a lot more data also generated at the edge. That's not even analyzed. That's really just there and sitting there for the future, that in the future we can really benefit from and analyze and do smart applications with it. So again, the real data at the edge is there. A lot of it is not being utilized. That is not even analyzed. But if you look at these global hyperscale data centers, really there is a huge amount of data. I just showed you the slide, or 12 zettabytes of traffic inside the data centers, and these are huge investments, right? They contain hundreds. They can contain more than 100,000 servers. They can contain tens of thousands of Ethernet switches, and they can have more than 1 million transceivers in some of these hyperscale data centers. And what has really changed over the last few years is that the connectivity, the whole networking aspect inside the data center has really increased in importance. And the way how you interconnect all these servers, the switches with each other, really is critical for the performance of the overall data center, right? And that's kind of where silicon photonics comes in, and where overall Ethernet connectivity comes in, because it allows you really to distribute compute, distribute resources, do your parallel processing, reallocate resources in a flexible way, do telemetry, do smart applications, so offload certain things to the network. So connectivity and the optical portion of it really is a huge part of the data center spend. And what we have done really with our silicon photonics platform is really that we have brought optics, we brought photonics to the Intel manufacturing platform, to the CMOS process, right? And that really allows us to do optics at scale, really in high volume, and at fundamentally different cost structures. And for those who have heard our presentations in the past, they're very familiar with our approach, where we're basically bonding the indium phosphide onto the silicon, right, into in a wafer bonding process. And that allows us really to put indium phosphide, which is quite expensive, only in the areas where we need it. And in fact, we can put different indium phosphide materials onto the same silicon wafers, right? That we have really good coupling efficiency because basically the laser is already part of the silicon waveguide. In fact, the mode is partially in the silicon, partially in the indium phosphide. So we just have to keep propagating it into the silicon waveguide. So there are really almost no coupling losses. It allows us really to do full optical test at the wafer level, right? So we have known good die that we can test optically and electrically that include the lasers, all the passive components, and so on. And then we can pass it on to the back-end assembly, really. So really, high volume testing. And also one of the things we haven't talked much in the past, we can do wafer level burn-in. So we burn in the lasers at the wafer level. So we can test them before and after, and we do the wafer level burn-in. And so over the past several years, really, we have shipped now more than 4 million of these 100 gig transceivers, both these parallel single mode PSM4 transceivers. These are all 100 gigabit Ethernet transceivers that you see on the left. So on the left side, we have 4 lasers, 4 modulators, and then they go out over 4 fibers for the transmit, and then 4 fibers for receive. But really, the high volume runner is our CWDM4, where we have 4 different lasers, 20 nanometers apart. Again, they're all part of the same chip. With 4 modulators, we have an optical multiplexer, all part of the same chip. And we're actually able to run uncooled all the way from -40 to 85 C, which is interesting for not just data center applications, but also for some of the 5G frontal applications that are emerging now. So this is huge for us because really we can make all of the thing on the left here, the transmitter chip on the right side, where you have these lasers and modulators. We can make all of that on a single chip, right? I think I'm going to skip over this, but suffice to say that really that's a huge advantage over using discrete optics to do that. But this is kind of what it looks like when you open it up. And I keep joking about this, that when you open it up, what's inside is mostly air, right? So I mean, obviously these transceivers have already been designed for hermetic packages. When I started doing datacom transceivers, we had TOSAs and Rosas, hermetic gold box assemblies for the transmitter and hermetic gold box assembly for the receiver. Now we just put it on the board, right? And we have the 4 lasers that are part of this portion of the die here. Then the 4 modulators are here. You can really see them because they're actually covered with the driver IC that's flip chip bonded on top, because we have a segmented, in this design, we have segmented Mach-Zehnder modulator, and we have a finely coupled electrical die driver IC that is coupled to that. And then we have the optical multiplexer, also part of the same chip, right? And then we go into one fiber, and then we have a separate chip, which is just a simple for photodiodes for the receive. So huge ability to integrate on a single die, really drive down cost, and also scalability, right? And one of the things, again, we haven't talked about it too much, but it's also reliability. I mean, that's really a key part of it, is that because you have so few components, because the lasers have no facets, we get really good reliability on these devices. We have about 2 fit on the laser, and we have less than 30. We have around 30 DPM for the whole transceiver modules in terms of field returns. I talked about the uncooled operation. The reliability is here. It's just some example that we did for the qual for the bonded laser. So tens of thousands of hours of reliability, and obviously a lot of accelerated aging. So we have really fundamental and good understanding about the wear out and other modes there. But as I said, around 2 fit on the laser, and there's some more data now in the domain. But fundamentally, we have all these building blocks, and we can put really complex chips together, right? So on the right, for example, you see a chip with 8 lasers, 8 modulators, multiplexer. But you can do a lot of different things. You can change the beam size, with silicon nitride tapers, for example, to adjust the beam size. You can do polarization, diversity, combining lots of different things that are possible, right? One of the things that is really that I'm particularly excited about is the ability not just to do lasers, but in general to do gain. And so what we can do with the gain is that we can do semiconductor optical amplifiers, right? And so we can go in with some input power, say 10 milliwatts in the waveguide already. We can amplify it in the section that has the indium phosphide, and then we go back into the silicon waveguide, and we have amplified it to up to 100 milliwatts, for example, right? And that's shown here on the right, where, for example, output power dBm, it's kind of a complicated plot here, but you can get 20 dBm output power, for example, with about 7 or with about 10 dB of gain, which means basically, yeah, actually I did say it right. If you go in with 10 dBm, you go out with 20 dBm. And that's actually quite interesting for applications such as LiDAR that I don't have time to talk about today. But obviously at Intel, we're also working on FMCW LiDAR now. In fact, there's a nice presentation by my colleague, Jonathan Doyland, that he gave at Photonics West, if you want to look up some more details on that. But, this is one of the key building blocks, obviously, that we have, that we can put, an SOA or multiple SOAs on the same die. Back to the data center, we're working not just on 100 gig, but obviously now 200 gig and 400 gig are going to production this year. So we have increased the data rates. Now you have, on the electrical side, you have 8 lanes of 50 gig coming in. We have 4 lanes of 100 gig coming out. So, very similar in terms of what goes inside, but, quite excited about, the need for the data center. But what I do want to do in sort of my remaining time is really talk about the optical I/O, and that's been always the vision that we talked about ever since we kind of started talking publicly about our transceivers. Is about, yeah, we're doing pluggables today, and it's great, and it's it gives us the scalability and cost structures and performance really that we can get out of silicon photonics. But the future is really and the big differentiator for us and for I think the value proposition of silicon photonics in general is that it enables, it gives you the ability to integrate optics with electronics, that you can put the photonics right next to the networking silicon in this example, right? And one of the reasons you need to do that is that if you look at the increase in data center traffic, if you look at how the switches go up in speeds, the SERTI speed, the electrical I/O speeds don't really keep up. And you're actually running into issues with not just with size and thermal dissipation and all of that, but also just your ability of getting the data in and out of the networking chip with all these pins, right? And that's why you really need to go and bring the optics closer to the networking silicon. And in our approach, really, we have the laser as part of the optical chip, right? And that actually saves overall power when you compare it to having a laser off chip, for example. So this is kind of what it looks like on the right. We would basically have this example like a 12.8 terabit switch, and we would have photonic engines, 1.6 terabit, for example, co-packaged right next to the chip, but it's on the same substrate. It's part of the same IC package. It's not like a PCB. It's the same package. And in fact, back in March, we did the industry's first Ethernet co-packaged switch demonstration. And if you want to read more about it, there are some press articles, or we also have it on the Intel newsroom. I put a link here on the slides. But we're really excited because really we wanted to try it out and see, can we do it? What would it look like, right? And so we developed a full switch where we demonstrated the performance. And maybe one thing that before I show you the pictures of that actual demo, there's a couple of things that obviously are key for this. One is the laser itself, right? Because it does get quite hot next to the switch silicon, right? And so the ability to really have a laser that can operate, at 85 C or even higher is critical, right? And the data here, I've again shown that before, is it shows you that the laser can laser, at least in theory, it lasers all the way up to 150 C, right? Which again is testament to the good thermal properties that you get through the silicon, but also to the low losses that you have inside the laser cavity. And the other thing is that we didn't want to keep using the Mach-Zehnder modulators, so we developed ring modulators to really have much smaller size modulators. And they also have lower power dissipation. And so here's some data that we published also last year, or in fact, it's almost 2 years ago now at OFC. And there's some more data, I think, even from last year that we published. So quite excited about the modulator. And when you kind of blow it up in terms of again, this is still a cartoon, But you see these. It's not that far from reality actually, but you see these photonic engines really on the same substrate, right? And yeah, if we want to move as an industry to this approach, really, there's a lot of work that we need to do. It's around standardizing on the optical. I mean, on the optical interface, we have kind of standardized already, right? But there's around standardizing on the electrical interface. It's standardizing around the mechanical footprint, because you do want to have some interoperability. You want to have a multi-vendor system. And in fact, Facebook and Microsoft, they started this co-packaged optics collaboration to work on some of these details. And so the photonic engine, actually I have a photo here for you on the top left on the slide. This is our 1.6 terabit photonic engine that we used for this demo, and you see how much smaller it is than the 100 gig pluggable module, right? And on this photonic engine, we have 16 modulators, 16 receivers. We actually have 32 lasers on there for redundancy purposes. So we can actually switch in case the laser fails, we can switch it over. And there's actually a nice paper, I forgot to put it on the slide here, that we published at OFC this year that talks about the photonic engine. And you see now how much smaller we can get once we take all the air out of the transceiver package and we can put everything on a single chip. But we're quite excited about that. And then that's what we did. We put it into the switch package. We packaged up a whole 12.8 terabit switch. And what we did, we put half the ports optical, and we left half of the ports with copper flyover cables, or electrical flyover cables that we routed to the front faceplate. And I took, when you take the lid off, actually you will not see this part. There's also a copper heatsink that goes on top of this cover here. But once you remove the cover, you'll see the switch ASIC down there. And these heat sinks, these copper ones, these are actually the heatsink that heatsink the photonic engine, the optics. And then there's a second heatsink again that goes on top that is there for the switch ASIC. And you can see how much better this approach is in many aspects. One is the front faceplate is actually open. Now you can have airflow going through. So the thermal properties of this whole big pizza box, if you will, are much better, right? When if you were to plug this shut with pluggable interfaces, you're generating a lot of heat that then goes back to the switch ASIC that you then have to use to cool the switch ASIC. Here we have these heat pipes. It's all purely passive that can cool it. It's a concept. At 12.8 terabits, we're not going to commercialize it, but it's really designed for 25T and for 50T switch generations. And we see that really being commercialized once we go to 100 gig SerDes speed on the electrical side, So I think that was kind of my last slide, really. Just to recap, right? It's a really mature, it's been really exciting time for us at Intel over the last 4 years. We really ramped silicon photonics to high volume, doing about 2 million, actually more than 2 million units a year. We shipped more than 4 million units. We're doing 200, 400 gig now this year. We have a lot of benefits from having this high volume CMOS platform and using it to do optics. Pluggables are fine. We're excited about going to the 400 gig form factors now. And even at 800 gig, I think there'll be some pluggable solutions. But as you go to these 100 gig SerDes, really the co-packaging is really going to be the future. It's the way to go because you cannot get data in and out. It has a lot of benefits. And in fact, this was one of the last live demos that we had in our lab before the coronavirus pandemic, and then people could no longer go into the lab. So literally, I think we had the last visit was in our lab, and then the next day, everybody had to stay at home. So we did this in our lab because we couldn't go to OFC in March, but yes. We're quite excited that we still managed to show it to people and show the interoperability between this switch and also industry standard pluggable modules. And that's kind of what we had in our lab. We showed that this can talk to a standard pluggable DR4 module from a different vendor and a different switch. And so we're really excited and hope to commercialize it, maybe in 3 years or so time frame. I think once you get to 50T and very certainly at 100 terabit switches, this will really be going to production.
Indeed, Robert. Actually, it was going to be one of the highlights of OFC to see your Ethernet switch with CPO. I was quite excited about it, and suddenly, I don't know, the world completely fell apart. But it is great that the innovation didn't stop. And when I see you, I always want to ask you the same. How can we help you? I have every single technology. I have micro-optics, I have silicon photonics, packaging, equipment. Is there a challenge that you have for these companies because they really, really want to work with you?
I think you're already helping, right? So I think some of the people that you have on this call, they are already helping us today, right? We couldn't do what we're doing today without, for example, some of these alignment tools or some of these other, big instruments that are needed to make this a reality. So I think connecting us across the industry with the players, giving us visibility, giving them visibility of what we're doing. I think this is really, really good, and hope to be able to do that in person again at some point. Yeah.
It is easy to connect nice people, and you are one of them. I have a question from FICON.
Thanks.
Greg, what's on your mind?
Hello, Robert. Thanks for your talk. Very informative. You mentioned redundancy in your new light engines, your co-package optics, 32 instead of 16 engines. You're making your assembly costs higher and actually, more complicated.
Well, actually, we don't, and that's kind of the beauty of our approach. I mean, we put the indium phosphide down, and then we just write the lasers on it, right? So, I mean, we can do multiple lasers under the same indium phosphide, and it doesn't really drive additional complexity or meaningful costs because it's all at the chip level. So at the chip level, we'll have, let's say, for each channel, we might have 2 lasers, and then we have a 1x2 switch. And really, we can just pick, if we see that, one of the lasers is maybe starting to wear out or something, we can switch over. So it really doesn't add additional complexity.
So, aligning a short array is just as easy as aligning a single laser.
It's all part of the one chip, and we just have to, the alignment is just on the input and output to the chip. Whether we have 16 or 32 lasers on that chip really is it's not visible to your alignment. Yeah.
Thank you.
Thank you, Robert. Thank you very much. Let's all go together now to Santa Barbara. So the day has been fantastic. We go to Santa Barbara next to the beach in California. So beautiful. And we meet my friend Milan. First presentation ever as an EPIC member. Welcome to the EPIC family. Milan, Interactive Photonics is the present and future. The floor and the attention of all my friends is yours.
Thank you. So, yeah, I'm glad to be here. I wish it were in person, but that will happen again someday, I'm sure. So I do have some exciting news and technologies to share on behalf of Freedom Photonics. So can you see my slides?
Yes, I can see them crystal clear.
Good, great. So Santa Barbara Beach in the bottom for you, and now we will move to talk on lasers. Okay. Yes. So Freedom Photonics, a little bit about us. We are a manufacturer of what we like to think of as unique and innovative photonics, and we're based in California. We make components, modules, and subsystems that span the wavelength range from 780 nanometers to 2 microns. We are an employee-based company, and our team is about 50 people. And our capabilities and our portfolio is well depicted by the images that you can see in the bottom of the slide. So we do everything from chip design and fabrication to micro-optic systems to modules and then subsystems. So what are the markets and applications that we work in? A lot of applications in optical sensing, from spectroscopy to LiDAR to fiber sensing and even some imaging. Also fiber optic and free space optical communications for both digital and analog systems. And up and coming areas that we're really excited about are in the areas of high power pumps that we have internally developed, as well as a variety of atomic and quantum sensing and quantum and cryogenic communications. And it is good to point out that a lot of our work is based around private label product development. And those products are generally based on our pretty broad technology portfolio. And I will show a few examples during the presentation. So we have a 2,100 square meter manufacturing facility based in Santa Barbara. A variety of clean rooms within for both manufacturing, engineering, and then specifically high power laser work. In terms of our manufacturing capabilities, we have everything that you need. So you can sort of glean this from the background of the slide. We have photonic chip and chip and carrier assembly, 5 different module packaging systems with active alignment, flux-free and hermetic module assembly capability, variety of complex optoelectronic and electrical measurement capabilities, as well as all the burn-in, lifetime and reliability testing. So we're a well-rounded manufacturer. We're also ISO 9001 certified. We've been certified now for 6 years. In terms of our team, we have about 50 people on our team, and it's a combination of scientists, engineers, and staff that are working on with really cutting-edge photonics to solve some exciting real-world problems. And our core competencies are in photonic components, design, fabrication, test, system integration. We have deep expertise in volume manufacturing, as well as deep expertise in control electronics for tunable lasers and complex PICs that we make. Our off-the-shelf products are shown here. So we have a family of fast tunable lasers from 1250 to 1750 nanometers, including a fully vertically integrated swept tunable laser source solution, shown right here. On the high power laser side, we have DFB laser technology at 1280 and 1550 nanometers with more than 400 milliwatts of output power, as well as single spatial mode high power laser technology with more than 1 watt of output power. We also have world record performance photodetector technology with our photodetector is able to detect really high RF power and photocurrents and then work up to very high frequencies. And as I've mentioned, a variety of private label products, which are very exciting. Some of those are actually ramping up into volume production as well. So we've been quite busy. So those leverage are both our custom laser solutions, our custom PIC solutions, as well as advanced micro-optic solutions. So let's talk about fast and high power tunable laser sources first. The application areas for these are optical coherence tomography, LiDAR, gas sensing, instrumentation, fiber sensing, as well as communication. And what you see here at the top of the screen is the spectral range that our widely tunable laser technology can cover. So it's pretty impressive. And what you see underneath are tuning maps for a variety of tunable lasers that we have in this wavelength range. So this first tuning map is a synthesis of 3 different widely tunable lasers, which together provide 100 nanometers of tuning from 1260 to 1360. And then similarly here, C and L band, as well as going all the way to 1720 nanometers. So besides this exceptional wavelength range coverage, this technology allows for fast tunability, and we have proprietary chip designs to enable this repeatable fast tuning to mitigate any thermal effects. We also offer these as part of vertically integrated solutions in our InstaTune module that was released at Photonics West this year. And some more details on InstaTune. So this is really a fast swept laser source that integrates our proprietary chip solution with control electronics into a module. It is available anywhere in this wavelength range. It is based on our tunable laser technology. Some data here, for example, you can get very high linearity sweeps. You can also get arbitrary waveform generation as well. And we have automated calibration using laser tuning maps to pretty much do synthesize arbitrary waveform that our customers need. Switching gears to high-powered tunable combo DBR lasers, this is our patented laser cavity design technology, which enables high output power tunable lasers. This technology, for example, enables us to realize first commercially available tunable lasers in the 1650 nanometer range. This plot here is from our friends at NASA who are using these lasers in their methane LiDAR instruments. So to date, we can generate output powers of around 200 milliwatts. And here's an example of a module with a collimated beam, three-space optical beam coming out of the module. Limited tunability with this implementation, as well as optical power shown here. We do have in the works a version of this laser technology that will provide for even wider tuning range with these same output powers. Now, talking about our high-power DUV laser sources, these are some other of the world record performance-wise devices that we have. They're based on innovative proprietary low-loss DFB grading design for high-power operation. And these devices, which are available at both 1280 and 1550 nanometers, demonstrate record output power and wall plug efficiency, as well as relative intensity noise in the shot noise limit of -165 dBc per hertz. For example, our latest versions of 1550 chip-on-carrier devices have in excess of 400 milliwatts of output power. And inside the module, we're getting more than 250 milliwatts of fiber-coupled power. These are available in a variety of different modules and applications, also as very high stability laser sources, which we're supplying to a few customers. So if you're interested in any of this, please let us know. Moving on to the high power photodetector side, we have this very unique technology that allows for hundreds of milliamps of photocurrents to be detected at several tens of gigahertz of linear output bandwidth, available at both 1550 and 1060 nanometers as of recently. And these are really world record performance devices in terms of the power handling ability. They are based on vertically illuminated type of solution where the light is coupled through the back of the photodiode. Of course, there's a lot of effort that went into achieving both high power, mitigating, removing heat, obviously, is very important with the types of powers that these devices can detect. And we have a variety of different footprints and packages, and then some data here showing the response as a function of frequency, as well as RF output power and compression as a function of photocurrent. We also have a variety of, a varietal, I should say, of very high frequency implementation of these devices. So these modules that we have developed operate up to 100 gigahertz bandwidth. And what's unique, because we use vertically illuminated photodiodes, we can offer these with both single and multi-mode fiber options. And some of the applications that require these require multimode optical fibers. Now I want to show a couple of private label product examples, which are very fascinating to me, and I think you'll like and appreciate it. One that we have shown before is an example of a 4-channel tunable WDM transmitter, which so basically the type of work we do is we get a customer and they give us a final functionality and a footprint. So in this case, we've completed the full design from the optomechanical design of the module to the custom chip that consists of 4 widely tunable externally modulated lasers with a single output waveguide, as well as a custom wavelength locker and control electronics to control this full module. This particular device was built for specialty communications applications, and it has been deployed. Another picture of the chip, relatively complex photonic integrated circuit, monolithically integrated in indium phosphide. Although we work with both indium phosphide, gallium arsenide, and silicon photonics, as well as hybrid solutions depending on what the customer needs, and some performance data on this chip. Another one that is something a little bit different, it's more in the micro-optic system-based realm, is a miniaturized nuclear magnetic resonance gyroscope. So here we've realized a complete, again, optomechanical design and solution from interposers with a variety of micro-optic components to the whole assembly process to a rubidium gas cell with magnetic coil around it. And the key of this implementation that it only requires one active alignment step to get to this very sophisticated sensor. So our assembly process, they're always designed for manufacturability. So in this case, you can see 2 completed physics packages and then 3 batches of sub-assemblies so you can tell what all goes into these sophisticated sensors. By the way, which are enabling a completely new level of sensing in terms of sensitivities and survivability in harsh environments. So to finish up talking about future directions just a little bit, what is next for Freedom Photonics? Well, we're ramping up volume of our production despite of everything that is happening in the world. Our business is going strong, actually even stronger. We're completing development of several exciting new private label products, and those will be transferring into production. And we plan on new products to be introduced in the atomic sensing, high power laser, and free space optical communication space. And quickly flashing through this, one of these products will be tunable mode hop free 780 nanometer and 795 nanometer laser sources for atomic sensing, very stable lasers with power shuttering capability. We also have some amazing broad area DFB lasers that show world record for this type of device at 1550 nanometer operation. These will be going in some fiber coupled pump modules, and our free space optical transmitter technology, which now operates over a 10-kilometer range. It's based on our MOPA lasers, and so these will be showing up as product soon. That's all I have. Thank you. Jose, do you have some questions?
You do have a lot, really a lot. It's great to have you in EPIC, and it is great to have more success stories of packaging and integration of photonic devices. The first question is, of course, the EPIC question. What can the EPIC members do for you, and what can you do for them?
Well, you know, what we can do for them, I think, you know, we can, this private label manufacturing model that we've been very successful with. I'm sure that there are many EPIC members who are working more higher up on the systems, and they need some type of customized components, modules, or subsystems for their systems. So I'm sure we can provide them with solutions there. And at the same time, you know, from attending a couple of meetings, there is a lot of synergy. There are a lot of interesting suppliers, potential suppliers within EPIC for us, and collaborators. So you're already doing it. Help us market our technology and cross-pollinate with other EPIC members.
We keep seeing a big growth on the OCT. And I know that that's a market that you've been targeting very well. And there is a bit of a debate. What is the ideal source for OCT? Is it a superluminescent diode or is a tunable laser? Could you tell me why you are going for the laser side? Why are you pushing for that one?
Well, you know, Freedom Photonics in general, we're opportunity driven. So the way we got into the OCT market was really through one of these private label development efforts. And, you know, from everything we've seen in terms of performance, what our customers have using a laser, in terms of the resolution, minimizing distortion, and just getting the highest quality OCT images, we are convinced that laser is the way to go, and that's where we're playing in that market.
If anyone needs a very, very well packaged and tested device, a laser diode, this is the person to go. Freedom Photon is a great company. If anybody wants to have a partner for the packaging or for the testing on the supplying side, this is also the person to go. Milan, you are a star. Thank you very much for being with us this beautiful 11:40 p.m. in the Netherlands, the beautiful night here in Europe. Thank you very much. Good day in Santa Barbara. And we go now to San Mina. And I really, really like Robert NUBURU. I met you already 2 years ago in Brussels, and you gave a fantastic presentation on non-invasive biosensing market, biosensing devices. Today, we are going to talk about infection, right? Thank you very much, Robert, for being with us. It is 11:40 here. What time is it over there? I still have you muted. Let me unmute you. I think maybe you have to unmute yourself.
Okay.
Yes, now we can hear you.
Me? Yes, it's 4:40 p.m.
In San Jose, right? No, Central. Okay.
No, I'm on the East Coast. I'm in North Alabama at the moment.
Fantastic location, North Alabama. The floor and the attention is yours.
Thank you very much. I try to share my screen. We appreciate this opportunity today. Okay, let's see.
It has been a crazy day. You cannot even imagine. It's I'm very close to be completely nuts. 21 hours.
Oh, wow. Well, I hope you get some rest. Can you see my screen?
Crystal clear.
Okay, thank you. So happy Wednesday, nevertheless, for everyone. And we really appreciate this opportunity. I so much enjoy hearing about all the fantastic technologies at EPIC and the partners that are related. So a little bit about myself. I'm coming from San Mina. We are a large-scale manufacturing. We typically produce products for other people. We operate in multiple countries. Today, I'm going to speak with you about something close to my heart and obviously relatable, which is non-invasive sensing of infection biomarkers. I am the medical CTO. I have teams in Europe and in the US, and I've been working, normally been traveling quite a bit, but since the pandemic, much more close to home. So just a very quick brief slide. We were founded in 1980 in San Jose, and we operate globally. Our main business is, as I mentioned, to manufacture custom products for other companies, multinationals, and big and small companies. We launch a lot of products across the globe, and we have a very, well-respected practice in the medical field, industrial, as well as telecommunications, among other things. So the real topic that I'm going to speak, and I'm quite passionate about this, is actually what's going on with our health. And I think all of us can relate in the pandemic time that there's really a lot of transformations going on. So what we're seeing is a large convergence of wearable technology. You've seen this probably on the press announcements and the news, where healthcare, lifestyle, personalized medicine, everything is coming together. And actually, what we see is a remapping of the monitoring to the device edge. Sanmina has been working on some technology for the last 4 years or so. We started out in diabetes and kind of evolved and accelerated our infection technology. We have a device I'm going to show you a little bit today that is put on the finger, and it really provides some fantastic analytics for the blood and for some vascular health phenomena that we're seeing. Okay, so first let me define what an infection is. Obviously, we have another organism that enters your body and causes harm. So the common symptoms of infection, just at a very bland, viewpoint, is you have a feeling that something is wrong, right? And you might be having a fever, or febrile in the medical language versus afebrile. And you might have fluid buildup and pain. And there's a whole variety of types of infections, which obviously we're talking quite common now with the pneumonia pathway and COVID, because the two are highly related. And actually, the severe cases of the COVID are actually pathways to sepsis. And that's when people become septic in the ICU wards and they really have some trouble. So a lot of things around infection, just to kind of give you a very quick baseline. So I'm going to speak very quickly just to set a reference. I know we've talked very specifically the past few speakers about lasers, and it's amazing what I saw. But we're going to first derive what common pulse oximetry is looking like, and it's using LEDs, primarily two. One of them is a red LED at around 660, and the other is 940 in the infrared realm. But basically what happens is the light goes into the finger pad, and then you're looking at the reflectance and seeing the volumetric change of blood affecting the signal. And so you're able to recreate the heartbeat, and then you comply some mathematics and look at the ratiometric differences in the absorption with some math, and then you come up with a calibration table, which then predicts the blood oxygen. So this is basically a very quick observation on how a pulse oximeter works. Now we're going to come to something different. So here is a customized PPG sensor, which we're going to speak a little bit about today. So in this case, we're using 5 frequencies. Now we've used up to 9, but for the purposes of our studies, what we've done is expanded the light frequencies that we are observing in the body. We're synchronizing them to the heartbeat, and then we're taking this, trying to be from a very low-cost method to provide very novel information. And what has happened is we've been able to use these alternate frequencies and physically map the trends of multiple organs in the body all at one time. So traditionally, a wearable has been defined with heart rate and blood oxygen, and maybe a little blood pressure. You're seeing some of that coming on the market. But what our system and research has been highly focused on is looking at the lungs, the kidney, the pancreas, the liver, and something called the endothelium, which we'll speak about in a few minutes, and even blood gases that are forming within the body as a reaction of some external stimulus. So we've done a lot of clinical studies, and this is hard work, but we've been establishing what healthy looks like versus what some of these common comorbidities like infection, diabetes, even COVID, we've been doing some studies across the globe and trying to get a better snapshot. So what this has now allowed us to do is kind of build a classifier of what's healthy and what's not, because we think we have a very unique screening application that will be of high utility for the market. So just very quickly, because I know we're all limited in time, but inside the arteries of your blood vessels, there is this lining, and it's called the endothelium. This is the main transport layer that the body uses to take the blood and feed all the cells in your body. So what's happening is, you might have heard that a high-risk patient, for example, or someone with diabetes might be more susceptible to a virus like the COVID. And why that is because their endothelial actually is dysfunctioning. And what that means simply is it's a little bit broken, right? So these cells normally are very tightly coupled, and in this case, they are having a lot of problems. And in the worst case with sepsis, you have a complete breakdown. So inside your body, you have all kinds of inflammatory responses. This infection rages, and you have fluid leakage and all of these things. So a little bit late last year, we started a study over in one of our European locations and partners, where we looked at sepsis and trying to catch patients coming into the emergency room and seeing if we could observe the onset of the infection and actually monitor them while they were being susceptible to catching sepsis. And what we found was exactly this kind of phenomenon, that the lymphocytes, which are, not going to spend too much time on that, these particles here, when they get too low, that means that the body is reacting very hard, and they're going to go very quickly into septic shock. The second point is that the nitric oxide levels, they peak very high, very early, and actually some hours before the clinical definition of sepsis is established. And what happened was, then when the pandemic came about, and I was actually in Madrid in late February, just before the pandemic was really severe. And yes, so the sepsis piece of it is actually heavily tied to COVID. And the COVID patients became, extremely sick, and we were able to verify that this phenomenon was going on. And I'm going to show you some data from this. So before I do that, what we've realized is that there's a strong utility, and across the globe, maybe at your factory, or you've seen locations where they're using a thermometer to do some kind of screening to see if someone is actually febrile. But we all know that that is catching, I guess it's the best option we have. But there's a great number of COVID patients that are actually asymptomatic or actually highly contagious, because the fever doesn't always continue, it comes in waves. And so what we're trying to do is to see if a device like this can be used simply with a few minutes of checking and potentially screen out people that have a higher risk because their immune system is expressing things that it normally should not. And we've modeled this of who is healthy and what a severe immune expression looks like. So we've been using a mixture of optics, smart algorithms, and doing something like this. And we believe that government mandated people movements are going to be restricted because of the hotspots. And we're seeing this across the globe as we speak. So one project that we're working on, that we're trying desperately to kind of accelerate and do as much clinical testing as we can. We have this device, and we have an Android app, and basically the model resides on the device, and the app is just a kind of an indicator. But basically what we found with comparing the gold standard blood plasma data as well as PCR data that our screening method works in the rough order of magnitude about 80%, which is fairly consistent with what most PCR methods are also contributing. And what we're trying to do is improve our algorithm so that we can catch as many segments of the COVID risk patients or otherwise, people that we don't want to be around that might have the flu or something like this as much as we can. And what we've learned from our previous sepsis research is that the same principles work inside the body, and the body is actually expressing itself very, very similar, in fact, even more severe in the worst case COVID patients as they are sepsis. So if you will look with me here, what we're showing you is results of this patient group here is 150 patients that came into the ER roughly from November to approximately May of this year. And they're confirmed not having COVID, but you will see that their blood plasma shows an elevated level. Okay, and a normal person would have somewhere of like 20 micromoles per liter. And you can see that they're not quite well, but the SARS-CoV-2 pneumonia or COVID-19 is actually elevated. Now, when this is the general kind of average for people in a hospital ward, the people that are in an ICU setting would have 150 micromoles per liter because the body is reacting quite severely. So this is a big difference, but the expressions are very, very similar to our septic research, and I just thought that this is quite interesting. So when we deep dive a little bit, and because of our limited time, what we're looking at inside is every single cardiovascular stroke from the heart, and we're studying this heartbeat, and there's quite a lot of phenomena happening inside your body because it's largely a chemical engine. So in this case, what I'm showing you is that the heart is beating, and then all of a sudden we see this dip. And actually what this is a pancreatic insulin pulse that the body is generating to regulate your glucose. And what happens is that if you can see here, there's this dip, and that's because the nitric oxide that is released at the same time we've learned there is another hormone called an ET1, which is a vasoconstrictor, and nitric oxide is a vasodilator. And both of these signals are emitted, and the vascular muscle of the artery or vein is being told to do two different things at once. So it becomes stressed, and the muscle tightens up. And that's why you don't have as much elasticity during this period. But the heartbeat is still going. And I'm just trying to give you a glimpse at what some of the things that are happening inside our body. And again, we're using only optics to measure these signals, a simple LED and a photodetector. So for the screening cases, what our mindset is to mainly go after public settings, industrial. Obviously, there are some ICU potentials and nursing homes. So we are involved with a variety of partners and projects to measure these different subgroups and subcohorts of patients. I won't spend too much time on that, but just to give you an idea of the status. So when we look at the actual algorithm, because I get asked this quite a lot, is how accurate is something like this?
Yeah.
And this data, what we're showing you is soon to be published. We've already submitted it. It's in preprint. But if I only focus on sepsis and not just COVID, then we're saying that our predictor works around about 82% accuracy with a very high sensitivity. And when we look at the classifier of sepsis versus non-septic. And so you can see here that we have a very good sensitivity and specificity, and these are the kind of things that we're seeing at our early research. Obviously, we need to take more data, but it's actually quite surprising when I dug into most of the blood tests that we see on the news. They are actually a similar accuracy as what I'm showing you here, okay? So now, let's look at some of the exact biomarkers. So I mentioned to you that we measure with the 5 frequencies. Now, out of that, we're able to derive around about 30 parameters from the blood, okay? Because we know how the ratiometric situation looks like, and we know how
as we reach the final seconds of the time allowed, because of course time keeping on this day is super important. I'm a huge fan of what you do. I'm really a huge fan because you start with the idea of measuring pulse oximetry with 2 LEDs, one in the infrared and one in the blue, and you manage to get so many parameters. The key question for me, what are your challenges? Just give me 2 challenges that you have for the companies who make optics, who make LEDs, who make packaging, who make medical instrumentation. 2 challenges so my people can work with you.
Yeah, so one of the things that we would love to have is an integrated LED source that would offer UV to infrared. That would be highly appreciated, as well as a photodetector that would be visible and having reactivity in the UV range all the way to infrared. So a pair of things that would match would be wonderful, because at the moment we have to use discrete components to accomplish our task.
And the way that, of course, you want that, but you want it like very, very cost effective. I never use the word low cost, but you got it very, very cost effective, and you want it very mature, of course. But there is many companies who are going to want to speak to you after that request. Robert, thank you very much for a great presentation. I'm truly amazed by the simplicity of the technology and by how well you have explained it to us. It is midnight in the Netherlands. We need to move on. Robert, thank you very much. And now we go to my friend Robin from Excelitas. It is so great to have you with us today, Robin. Thank you very much for joining in this epic journey. The floor and the attention of everyone goes to you.
Thank you, Jose. Can you hear me? Can everyone hear me okay?
Loud and clear.
And see my screen?
Fantastic.
Okay, well, you're looking remarkably well, Jose, given the long endurance test you've been going through. So I'm very impressed by that.
Thank you. It means a lot.
So good afternoon, good morning, good evening. I'm not sure where everybody is, but thank you very much for tuning in to the Excelitas presentation. It's really a pleasure to be here, to be part of this EPIC event. And thank you, EPIC, for the opportunity to present here. We're very happy to be part of the conference. So our CEO, David, wanted to be here, actually, but unfortunately, he was not available today. So unfortunately, you're stuck with me for the next 15 minutes. So I'll try my best to fill his big shoes. So is it working? The animations. So my name is Robin Swain. I'm the Chief Technology Officer of the Commercial Division of Excelitas. We have 2 major divisions and 2 CTOs. I'm the CTO of the Commercial, and we have another guy who's the CTO of the Defense and Aerospace. And my goal today is to tell you a little bit about Excelitas and who we are and what we do as a company. And this will be primarily an overview presentation because, as you can appreciate and imagine, as an OEM provider, much of what we do is confidential and under NDA, so there's very little we can talk about. So I'm just trying to give you a flavor of what Excelitas does and who we are, and give you some flavor of our technologies and core capabilities. So who is Excelitas and what do we do and who are we? So Excelitas, I would say, is a medium-sized organization, about just shy of $1 billion in revenue. We have roughly 7,000 employees in 17 manufacturing sites. We have sites all over the world, Germany, UK, Canada, US, several in Asia, in Singapore, Philippines, and Indonesia. And we operate design centers in multiple different countries also, with the intent of being geographically close to our customers, because As many of you know, engineering to engineering interaction is critical in the OEM environment. So we like to have our engineers close to our customers. Our factories range from relatively low volume, high sophistication. So we may have some products which are very complicated, quite expensive, very complicated in low volumes, maybe hundreds per year. And we also span all the way to very, very high volume production, millions of units in relatively low sophistication in mass production. So we're truly a global company in terms of engineering and manufacturing capabilities. And we're headquartered in Waltham, Massachusetts in the US. The animations are going to be a pain. So the markets that we serve, we're very diversified. We serve many markets, and which is a good thing in a situation where, the environment we're in right now, where certain markets are strained. And as I mentioned earlier, we have two divisions. So the Defense and Aerospace division handles applications such as avionics and heads-up displays and missile defense products, satellite products, and soldier-type systems, those kinds of things. The Commercial division, which I mentioned is the one I represent, handles applications in these markets such as autonomous vehicles, consumer electronics, smart home, safety systems, endoscopy, lithography, environmental monitoring, and so on. So we're very diversified, operate in many markets, and we operate in certain key applications within those markets. A little bit on our heritage. The company was founded in 1947 when 3 MIT professors peeled out and formed EG&G. And EG&G operated and grew for 50 years or so by expanding the portfolio of detectors and sensors and light emitters and illumination technologies and so on. And then in the last century, 1999, they acquired the analytical instrumentation division of PerkinElmer and operated under that banner for 11 years or so. And then in 2010, Excelitas was formed as it spun out from PerkinElmer with the help of private equity firm Veritas Capital. So Excelitas was really truly born in 2010, even though it has a long heritage before that. And then in 2010, Excelitas grew quite dramatically from 2010 onwards with acquisition. In 2012, we bought Carson Engineering and Kaiser Systems, which operates in arc lamp power supplies and custom high voltage power supplies. And then 2013 was a big year for the company, 2 major acquisitions, Key Optic and Lumen Dynamics. Key Optic back then was mainly a European-based global photonics company, making basically optical systems and optical subsystems. And Lumen Dynamics was specialized in LED and lamp-based UV curing and fluorescence illumination systems. 2017, along came AEA Investors, a private equity firm out of New York, and bought Excelitas. And then two other major acquisitions, 2018 and 2019, REO in Boulder, which is, some of you may know, is specialized in high precision optical components, optical thin film coatings, and optical subassemblies. And Axon, based in Massachusetts, in Billerica, Massachusetts, they specialize in MEMS-based optical engines for medical imaging, OCT, spectroscopy, and so on. So a rich portfolio of technologies are within the company. So we can take a quick whirlwind around those technologies. In addition to a wide array of standard components, we offer essentially end-to-end custom solutions in numerous different applications. We're experts in the conceptualization, design, engineering, and production of photonics components. We offer build-to-print services. If a customer has an existing design, we can optimize that design for manufacturing and improve yields and cost and performance and so on, and then put it into production in one of our factories, depending upon the volume and other parameters. We have multiple options where we can put things. And in many cases, we're able to manufacture the constituent components of a product and then build those into the subsystem. For example, detectors or light sources or the optics or filters, beam splitters and so on. We can manufacture them in our optics factories and then build them into an assembly or a custom solution for a customer's application. And then at the end of the day, when all the engineering is complete, we can offer a high quality, cost-effective volume production solution, which can then make steady state volume production for that. There's really 4 categories of technology that we offer. Illumination technology. As you can see from the slide, we offer a broad range of technologies and products as sources of illumination. We have in our portfolio LEDs, lasers, arc lamps, diode lasers, swept OCT type sources. We offer a wide range of wavelengths from UV to infrared, and most things can be customized in a specific way. And as you can see from this image, there's a customized LED solution there. And the products are available both in component form or integrated into some higher level of optical assembly. Just checking, doing a time check. I think we're okay. Optical solutions. With the acquisition of Key Optic and other technologies, REO and so on, we can pretty much make any type of optical component you can envision. There's very few that I can't think of. We have a large array of sizes and shapes and all sorts of different optical components, including many of the technologies, leading edge technologies that you would need for manufacturing, such as advanced clean room technology, coating technology, micro optics. We have the whole gambit within the company today. We have significant manufacturing capability in multiple locations around the world, Germany, Singapore, Colorado, and we're able to pick and choose where we do things depending upon technology needs and so on and so forth. And we can make very, very high volume components, thousands a month in many cases, all the way to very, very sophisticated components such as semiconductor grade, the most challenging applications in terms of surface figure and quality and so on. So we span the gambit. And of course, all of that can be integrated into a custom solution for a customer specific applications. As I mentioned at the beginning, we go back to EG&G, so the detection technology is the heritage of the company, and that whole business stems from that. So we've been around a long time in that industry, and we're regarded as an industry leader in terms of detection capability and technology. And as you can see, we offer all the way from discrete sensors all the way up to sensor arrays and modules, the ability to integrate them and also to produce them in high numbers and high volume, millions per year if needed. And we're also able to integrate up to a high level of subsystems. Some applications require a detector and a light source and some kind of housing or whatever in the millions, and we're able to produce that quite comfortably in our factories. And finally, we offer sophisticated power solutions. This is the acquisitions in 2012 I talked about. These are not run-of-the-mill power supplies by any means. These are advanced power solutions modules that are custom designed for a specific application. For example, a CAT scanner or an electron beam system. They can't just take a regular old power supply. They need an advanced power delivery solution. And these are the kinds of products that we make in that business within Excelitas. So what kind of applications are our technologies used in? There's so many. I just picked a few for this presentation. I've got 5 minutes left, so I think I can get through these. So as you can imagine, there's lots of talk these days about COVID, and the last presentation from Samina showed a temperature sensor. This is something that these kinds of things are the things that we're working on. And you can imagine in a post-COVID world, it's reasonable to assume that touchless applications will become the norm. And here's an example of an array detector where temperature screening is used to determine, multiple point temperature sensing is used to determine whether somebody can get access to a building or can go through an airport or any of those kinds of things. So you can imagine these kinds of products are going to be showing up more and more in this post-pandemic world that we're about to hopefully get into very soon when this is all behind us. And here you can see this is an array thermopile that's making multiple simultaneous measurements on a person's face to give an idea of whether the temperature is elevated. So you can imagine this is going to be widespread going forward. Our technology is also available in custom medical applications. There's quite a number of those, but in regard to COVID, we make components and technologies that go into, for example, PCR and other types of technologies, which are used for some of the testing in widespread testing these days. And we also offer, medical imaging products, illumination products for microscopy, and all of these can be used in the fight against COVID and other pandemics. Can't talk much about our defense and aerospace business, but we do things in space, actually, in terms of solar panel, glass covers, and retro reflectors up in space. We do heads-up displays. We do threat detection products, and quite an array of products in the defense world. Unfortunately, most of which can't be talked about. We're kind of proud of the fact that our technology is in key areas where it's important to quality of life. For example, our detectors are helping in the fight against global warming and environmental preservation, in that we offer the ability to help with the reduction of energy consumption, both in residential and in the workplace. So, for example, our smart home technology allows for more efficient energy use. Presence detection and people counting technology will allow us to vector heating and cooling more efficiently in buildings, so that we can thereby consume less power. Future medical innovations. As I mentioned earlier, we have micro-optics capability within the company. So revolutions in medicine and surgery, such as robotic surgery and high-resolution endoscopy, are clearly future applications that will be getting more and more popular, and they're growing quite substantially. And we're happy and proud of the fact that we are in that industry and propelling those marketplaces forward and those industries forward. And finally, I think everybody knows it's the future of transportation, ground-based transportation anyway, is self-driving vehicles. And, this is going to require truly cost-effective, advanced optical technology, which can survive the rigors of the automotive world in terms of temperature extremes and vibrations and impacts and so on and so forth, and be very low cost and be very rigorous and high volume, be available in high volume manufacture. So we're proud of the fact that our technologies are well suited and to be able to support this emerging industry, and when it will inevitably become mainstream in the next few years. So with 1 minute left, in summary, we offer end-to-end solutions for numerous different applications, from concept to design to system integration to prototyping to volume manufacture. We're highly experienced. We're a one-stop shop for photonics, where you can bring a concept to us and we can help you engineer it and optimize it for manufacture, and then we can put it into volume manufacture if needed. So we're very proud to be helping to enable the future and help with the future advances in technology through the use of light. And with 35 seconds to go, I will say thank you very much for your attention, and I'm happy to answer any questions if anybody has any.
That's why Excelitas rules the world of precision, because it's 35 seconds and exactly finish on time. I really, really appreciate that. I don't know if you notice how serious I'm taking the time today. It is great to have Excelitas in the room. You have covered every single technology solution that you provide. When I say technology problem solver, the solutions are coming from your customers. Let's cover a few of them. So one of the key technology that you're covering is the UVC. And of course, you talk a lot about other COVID-19 potential solvers. Everybody's talking about those. But did you see a big market pull lately on UVC?
Yes, we do. It's clearly an area of interest, and in terms of obviously disinfecting and killing this contagion that's affected all of us. So yeah, we do see a pull in that area, and we're actively involved in that technology, and we think it potentially could be a market going forward.
In the US, the UVC light for purification is far more advanced than anywhere in the world. Actually, it has been already implemented for water purification and successfully been regulated for that. The rest of the world is a bit behind on that, so we need to learn a little bit. But do you think, I'm sorry to ask so directly, do you think there is a bit of a hype? Can UVC really, really, really disinfect surfaces from COVID-19?
Well, there's multiple applications, don't forget. There's the surface disinfectant, but there's the airflow disinfectant as well. So if you can force the air through a UVC light source and any airborne contagions can be killed that way, then there's multiple applications other than just surface decontamination.
I think that there is a lot there, and I also think that, for example, you talk about the touch display. I think they are not going to disappear because we still need the pin from the cash machine. So disinfecting these kind of things, I think there is a big role for UV LED, and I also agree with you. This is going to grow like crazy in the coming years.
So, yeah, I agree.
Autonomous driving. Everywhere I go, any LiDAR conference I go, I will see a big booth from Excelitas and your people there that they look like they are giving free cookies because everybody's going to the Excelitas booth to talk to your people. You talk about cost effective. But the word cost effective means a lot. Can integrated optoelectronic devices ever be cheap enough for the automotive? How do you think about this?
Well, I think they have to be, right? I mean, autonomous transportation is coming, whether we like it or not. I mean, I personally am not sure I would be comfortable in one of these vehicles, but it's definitely coming. It's the future. So one way or another, I think companies will solve the cost problem and solve the technology problem, and this kind of technology will come one way or another. There's no question about it, I don't think. The question is, what form will it look like? And exactly how will it be, integrated into the vehicle? But it's coming.
Excelitas technology has already been integrated into the automotive sector, so it's already in cars. How do you automotively qualify Excelitas? Do you have some stories to tell us on that?
It's a challenge. I mean, the automotive requirements, as we all know, are extremely challenging, extremely rigorous, tough to meet, understandably, because we want our products to be robust and have a long life and be highly reliable, and zero margin for tolerance. So I think that is one of the major challenges of this whole sector is how to get these things up to the grade needed for automotive manufacture. It's really very challenging. And as you said, we're involved in that right now, and it's been painful, and it will continue to be painful. But the companies that have the backbone and kind of work their way through it will be the survivors who will profit from the market on the back end.
Robin, on a day like this, you learn a lot. I learned a lot. So 6 hours ago, we had a presentation from Autoliv that told us about the automotive homework. It was the Bible. I recommend all of you to watch that presentation. It was fantastic, as good as yours, Robin. Thank you very much for a great contribution to this epic journey. Thank you very much.
Thank you. Pleasure.
Why don't we do some spectroscopy now? Let's go to Ocean Insight. Let's try to understand a bit how we can help one of the key spectrometer manufacturers worldwide. Steve, thank you very much for being part of the epic journey today. It is 20 past midnight in Noordwijk, the Netherlands. What time is it at your location?
It's only 3:20 in the afternoon, so quite easy for me. I'm in Seattle, so thank you for having us.
It is great to have you. The floor is yours.
Okay, well, thank you so much. So I'm going to talk today about applied spectral knowledge powering our ocean solutions. And Ocean Insight, as many of you know, is the new name of Ocean Optics. It's now been our name for a little bit more than about a year. And we're proud to be part of this epic, what I call photonics marathon. So I'm impressed by the amount of energy you have, Jose. So, most of us know Ocean and Ocean Optics for the research side. I mean, we've been powering research solutions for over 25 years. Modular spectrometers, modular light sources, fiber optics, and that's still a large portion of our business worldwide. The thing I'm going to focus on today is how we have also transitioned that into what we call our solutions business. Not so different from some of the things Robin was just talking about, how we solve problems with our customers to help them find success in spectroscopy in particular. And so we like to say this is creating the confidence to act with our applied spectral knowledge. And so a little bit about Ocean. As many of you know, we're owned by Halma, which is about €1.5 billion euro turnover company. Ocean itself has 8 locations around the world. We've placed over 300,000 spectrometers with our customers. and we're on 3 continents. We're in North America, both at our headquarters near Orlando and then in Tampa. We have an office in Rochester, and then we've got locations all over Europe, in Deuven, in the UK, and in Germany. Small sales office in India, and then one in Shanghai. So really the sun never sets, just like on this photonics epic journey, it never sets on ocean, which we love. And one of the things that really drives us, and it always has, is the curiosity of our customers and solving those problems. So we like to say we can be instigators of the possible. Many of you know us for our spectrometers. We also have a full line of multispectral cameras. Our Pixeltech brand and that line of cameras thrives. We have both filter wheel cameras and filtered cameras on chip, so we can do all kinds of both visible and SWIR multispectral cameras. Lots of different kinds of spectral sensors, and then the spectroscopy that goes with those, Raman spectroscopy, Lib spectroscopy, as well as just transmission absorption systems that we make. Along with that, a whole set of light sources, fiber optics, and accessories. One of the things that people don't always associate with ocean, but which is a big part of what we're doing now, is some advanced software. So you might be familiar with Ocean View, which is much similar to LabVIEW. That's kind of a visual way to set up optical and spectroscopic experiments. But we also have a full suite of machine learning and chemometrics that we can build into our custom solutions behind the scenes. We can deploy these in the cloud, and we've built these for multiple companies that you wouldn't know about, because we just make the internal subsystem, and then we also make some turnkey systems as well. So I'm going to talk a little bit more about the latter bit, the systems side of this in a moment, but first we'll just cover some of what you probably already know about ocean, and that is our technology. The basis of all of our technology is, of course, we think the best in the world, small, rugged, and reliable spectrometers, from really 200 nanometers all the way to 11 microns. So you can go from very small and simple, our STS line, to our more high performance HDX, to our QE Pro. And then we've got NIR versions as well of all of these spectrometers. Really super proud of these, and these underlie a lot of our spectral solutions, probably obviously. And then we've got, a full set also of LED and halogen light sources. We implement things with laser and other sources as well. And we tie these together with, as I just said, a full set of software, including chemometrics and cloud deployments, leading to systems that we build for our customers. So a little bit about those. First, I guess I'll touch on some of our cameras as well. Our Pixeltech camera line, this is an example of it looks like an 8-band multispectral camera. This is from about 300 or 400 nanometers to about 900 nanometers, but we can design those bands custom for our customers. So if you have a hyperspectral or a multispectral application, we'd be pleased to talk with you about it. We also distribute headwall in China. That's a new development. So Ocean's team in China is working with a lot of our OEM customers there to get headwalls, hyperspectral cameras into the hands of our customers in China, which is a new development as of only a few months ago. So together then with these spectrometers and this multispectral and hyperspectral imaging driving toward applications, and that's what we'll talk about next. So when you're not just buying a spectrometer from us off the shelf, how do we interact with our customers? Well, we really take a very staged process, because a lot of our customers, we realize, are not spectral experts. They don't have the in-house capability, and so we walk you through a process that's very safe, right? We will do a feasibility study. We'll understand your requirements, and we do that feasibility through lab services, which I'll talk with you about in a moment. And then we'll walk you through some solutions that may work for you and try to nail down your requirements, applying our engineering expertise, and then helping you get to prototypes that are really MVPs, these minimum viable products that basically just do the problem that you're trying to solve in the most simple way. If we can prove out an MVP, then we know we probably together have something that you as the customer would want to pursue. And so then we go into a design partnership where we build in the bells and whistles that are going to make the product a success for our customer. And of course, then that's the job of my group. I'm the VP of Engineering and Product Development. And then we turn that over to our operations, where because we're ISO certified, we can supply at scale, and we can supply anywhere in the world at high volume. So that's really this is our process that we call ASK, Applied Spectral Knowledge. So it starts really in lab services, and it proceeds, and this kind of process has taken us into lots of different areas. I mean, we'll talk about some of these. This is just a smattering of some of the customer areas that we see and are active in right now. So, you know, the beginning of it all is often in lab services. We have a team of PhD scientists who basically take in all kinds of problems, biological problems, chemical problems, industrial problems, and we'll prove out a solution with the customer in mind. So we bring in the customer, we can demo the solution, we can try things out, and we can give you a pretty good feeling in the first, you know, kind of couple weeks. Yes, we can do this, or no, we think we should probably pass on this. Spectroscopy might not be the answer. And that's part of being safe when you work with ocean, is that you know that we're just going to take it as far as we can and really no farther. But beyond our lab services, then we would move into development. And some of the developments that I wanted to highlight in this presentation are coming up. So one of them, many of you know Malvern Panalytical. They have a terrific microscopy system called the Morphology. And they needed a solution to implement Raman inside the morphology. This allows them to look at tiny particles, get the 3D characterization of the particles, and now they can get the chemical characterization as well. That's all done in partnership with Ocean. We provide the inside to this system, and now they're able to really offer a unique product to the pharmaceutical industry, looking at pharmaceutical API as an example. Another example of a really great product using our multispectral imaging capabilities has been with a company from Texas called Spectral MD. They wanted to create a custom multispectral imaging system to look at burn monitoring. So when you get a burn, the treatment is to excise the tissue that does not have any blood flow. If you do that efficiently, the wound will heal more quickly and the patient outcome is the best. And normally that's done visually by a doctor. But the doctor, you know, even given their experience, may not be able to get all of the tissue excised properly. And so what they found is that they can be 30 to 40% more effective with this multispectral imaging system that we supply them, that makes patient outcomes and the healing process much quicker. So this is a way that kind of we're involved in the medical industry with our multispectral imagers. And then a final example, you know, a lot has been made of airborne pollution, especially during this period of COVID. There's a lot less transportation, so a lot of our cities are cleaning up. But one of the things that we may not focus on as much, because we're not all in the ocean as much, is that you can see them from satellites, is that 5% almost of the 3 to 5% of the airborne pollution and much of the sulfur emission is currently from maritime transportation. And so we've worked with Danfoss ICSA in Denmark to provide a world-leading kind of emissions monitoring system that actually sits inside the smokestack of a ocean-going vessel and monitors and controls sulfur and NOx emission in real time. So this allows the ship captain to tailor the engine parameters to minimize emissions. So these kinds of examples, you know, most people understand that ocean builds spectrometers, but they don't necessarily know that we go deep with our customers in providing these solutions as well. Some of the other solutions, just to give you a sense, these are more custom industrial design solutions. This is a liquid flow system called our liquid transmission monitoring system that we provide to multiple customers for flow monitoring. We provide fluid handling with that. This can be reconfigured for complex samples, even like sunglasses, if you want to see what the transmission of your sunglasses are. We had a customer interested in that. And we do lots and lots of custom configurations. So here's another one that has our high performance HDX spectrometer inside with a cuvette holder, custom software. We can tailor this for our customers, integrated shutter, integrated light source, and custom machine learning to provide a solution that can be branded our customer's brand and that can be carrying kind of the solution to their customers. So just one final industrial example. This is a very interesting color measurement device mounted on a robot, monitoring customer and painting. They were the colors in this helmet, for example. We could monitor the quality of the decals and paint in the colors. So so anyway, that's sort of a quick tour. Last one is an example of how we do a lot of our industrial color measurement for architectural and commercial color and lighting, and for horticultural light metering as well. This is called the WAVE system, and it has a cloud-based implementation, works on Bluetooth, really neat little device for more of a consumer almost application. So, you know, Ocean, I think, remains this, you know, premier supplier of modular spectrometers. We do multispectral devices, we do light sources for research. But what I hope you've learned about us is that we actually have a full stack engineering team that also stands ready to help our customers develop and integrate our spectroscopic measurement systems for both our OEMs and industrial customers. So thank you with that. I'm happy to take any questions. And again, thanks to EPIC for the invitation to be part of this.
Thank you very much, Steve, and thank you for bringing all the different solutions that Ocean Optics can bring. Actually, when I finished my PhD 20 years ago, Ocean Optics was like the kind of place everybody wanted to work, because you had this booth, this corporate image, these beautiful t-shirts that everybody was wearing there, and you realize there was so much energy in that company. It was an inspiration. Today, you presented a lot of spectrometer solutions, all of them in the visible range, solving many problems. But today we had a really long day, a fantastic day. I will never forget it in my whole life. And a couple of hours ago, we had people in the mid-infrared region talking to us about gas sensing, and they actually talk exactly about the same chemical compounds that you were talking. So where do you stand on this? Are we talking in the mid-infrared? Are we going in the mid-infrared or in the visible for environmental monitoring, for this cooperation that you have with the Danish people?
Yeah, so that one, you know, is primarily a UV application because it's doing SOx and NOx, and those are efficiently measured with absorption in the UV. We have a number of NIR kind of applications as well, and we've been pushing into the MIR with our MX5 spectrometer, which I didn't highlight. But we do have both a miniature FTIR MEMS-based spectrometer in the NIR, as well as our NearQuest, more standard, larger bench. And so we've a lot of our environmental applications that are tending toward that UV range, just because, I don't know, you know, a lot of our legacy customers are using that for NOx and SOx in particular. Yeah.
One more thing, it is we are in the time of the big cells manufactured at wafer level, and also they need to be tested at wafer level. Is it the wafer level testing of big cells identified as a key market segment for Ocean Insight?
We're very active in that and a number of kind of display kind of relevant things as well. So yeah, there's a lot of activity in that, both actually a lot of that's in Asia, obviously, but throughout North America and some of our North American market, and are working on development of new systems as well as serving long-standing customers, and that's been a big thing for us. You know, and you mentioned you know, before the whole question with Excelitas of the UV disinfection. You know, I think that's another great area for all of us to be contributing. As you know, I think there's a lot of push in that direction for the spectroscopic community as well. So.
I love when people connect and when people talk to each other. So I would like to remind people in YouTube, if you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asa.com, and I will make sure you get introduced the way that you deserve to be introduced. I would like to ask you something else. So now we go to another thing coming, another big thing in photonics coming, which is the world of micro LEDs. And a lot of companies are going to develop amazing technology for micro LEDs, and we still need to test them properly. Is that a key market segment for Ocean Insights? Is there a possibility to test micro LEDs? Are they small?
I'm so glad you asked. Yes, I'm so glad you asked. So actually, I don't know that you know this because we haven't publicized it, but we have a great quantum efficiency system, both microscopic and a little bit more macroscopic, that's actually been developed out of we have an engineering group in Shanghai that's been developing that, and it's mostly only known within China. We've sold probably 30, 40 systems in China, and we're about to roll it out globally. So I didn't mention it because it hasn't been fully rolled out, but let this be the announcement that if anybody would like to, you know, you heard it here first, thanks to Jose's question, but we have a neat little quantum efficiency system that's really great for that. And certainly would love to be in touch with anybody watching this about that or anything else I've talked about. So thank you so much for having us.
We have been working very hard on bringing a supply chain on micro LED manufacturing, and my colleague Sana has been actually positioned Ocean Insight in that supply chain already last week. So I've been talking to many people. We are happy that now this is public, but it was the result of some research. Thank you very much, Steve, for a great presentation and for being epic. Let's go to the next company. I really look up to these guys. Infinera, I'm a fan of indium phosphide. I'm a fan of indium phosphide photonic integrated circuits. And when people make a difference in the industry with indium phosphide peaks, not only making wafers, not only making chips, but actually solving optical networking problems, then I'm their friend forever, the #1 fan. Mehra, thank you very much for joining today. The floor and the attention of everyone goes to Infinera. The floor is yours.
Thanks. So, I watched you before going to bed last night. When I woke up this morning, and you have as much energy as when I went to bed. So I don't know how you do it, but
coffee, only coffee.
Okay, sounds good. Good, great. So let me start sharing the screen. And
everybody see how right on time we are? I'm so happy with this. We are waiting for seeing the beautiful slides from Infinera. They are almost here already.
So do you see it?
Orange, so beautiful. Such a great corporate color.
Yeah.
Go ahead, the floor is yours.
Okay, so I'm Merdon Ziari from Infinera. Today I'll talk about PICs, but more than PICs, I'll talk about some network applications, because I think throughout the day, you probably heard a lot of device talks and things in the range of, micrometer, nanometers. I'll probably go a little bit into the application side and talk more about that. So what we do, we are in optical networking business at Infinera. And we do it in a very unique way. We have been developing and offering, optical networking solutions, but we have had a legacy of deep vertical integration, and we make our own subcomponents, PICs being one of them. We cater to several markets. Some of the biggest names in the industry, have a lot of customers in fixed and mobile services, submarine, enterprise, and a lot of internet content providers. This talk is probably going through Infinera gear. Some of us in this talk are probably are connected with fibers that are using PICs. It's actually very difficult these days to avoid them. So what we do, our group, we're part of Optical Innovation Center. Infinera is uniquely organized with a very high degree of vertical integration. It was very uncommon in our industry. I think other people are now moving in that direction. As part of this Optical Innovation Center, as I mentioned, we design and make our own PICs. We have our own fab in California. We have analog IC groups. We have a very large DSP group. We design our own packages. We have a packaging plant in Pennsylvania. Connecting these things together, we have developed a lot of expertise in RF interconnects, and we take this holistic approach to co-design. The level of performance that applications require, I don't think one can do justice by designing just a PIC or a DSP or ASIC. These things need to work together, and in order for that to happen, they kind of need to be designed together. So our designers sit together, design it, our manufacturing people work together. Today, I'll showcase 3 examples. One of them is a leading high-performance optical engine. The other one is a revolutionary point-to-point coherent optical solution. This is sort of a part of a innovative approach we have to networking. And I will also talk a little bit about our foundry service. So first on the optical innovations, many of you may have seen this plot from me or my colleagues. If you look at the evolution of optical transceiver technology over the past 2 decades, you can map the advancements and scaling along 3 key dimensions. The first one, which we all used to do, is the vertical axis. Just make light switch faster. The symbol rate goes higher and higher, and that gives you more information capacity. The second one, which started with coherent optics, is use advanced modulation schemes where more information is encoded in light. You use the phase of the light and encode more information. We started with 4 constellations, now 64, and as part of it, develop probabilistic constellation shaping where the amount of information isn't the same in all the constellation points. So this has been key in increasing the bandwidth, the capacity, and almost everyone has been doing this. A unique axis, which is number of devices or wavelengths per device, number of channels or wavelengths per device, is something that Infinera started in 2001, our first commercial offering in 2004, 2005, where we put in this early example 10 wavelengths and a multiplexer on a chip. As the integration became more complex, as we got into coherent optics with more and more functions, these circuits became very complex and almost started to look like VLSI chips. And when you look at the density, it is a VLSI chip. So overall, by increasing the symbol rate, using complex modulation schemes and adding these channels, we have been able to have a very rapid increase in information capacity. So our optical engines started at 10 gigabit per second per wavelength in 2004, and now we are reporting 800 gigabit per second in 2019. We reported it, and we're shipping it commercially sometime this year. So if you can look at it, 80-fold increase of capacity per wavelengths. And we have demonstrated or commercially offered 2 channels per PIC all the way to 40 channels per PIC Some of these things were demonstrations to just show the capability of the platform. So today I will talk more about our latest development, which is a 1.6 terabit module. This is 2 wavelengths, each running at 800 gigabit per second. It is a PIC, an ASIC, and a package that integrates all of these things and fiber that comes out. This runs at 64 QAM and delivers 800 gigabit per second. I'll explain more about the PIC and the ASIC there. Here's a picture of a drawing of the PIC. So it includes 4 lasers on a single piece of indium phosphide, 2 for the transmitter, 2 for the receiver. We've learned how to just add more lasers. So we think that adding lasers to the receiver for a local oscillator gives us more options and better performance. We also, with indium phosphide providing native gain, we throw in a couple of SOAs to amplify the light that comes out. So that provides a lot of advantages for the system. There are 2 dual polarization modulators and 2 coherent receivers on this chip, indium phosphide chip. Next to the indium phosphide chip, we have developed a silicon germanium ASIC with 4 modulator drivers and 4 transimpedance amplifiers. And we have a set of optics, array optics, where it efficiently combines 2 polarization into a single output or splits 1 input into 2 polarization inputs to the device. So the results are shown here. Bandwidth in excess of 50 gigahertz, 55 gigahertz in this case. With this sort of bandwidth, we were the first to show 100 gigabaud 64 QAM operation. I think we showed this 2 years ago at ECOG, running at 64 QAM, very good constellation, clear, and running above the effect limit. So we have made a product out of this thing. So the product includes a DSP that we developed at Infinera, DSP, PIC, some support electronics, and routing constitute what is called in the industry a digital coherent optical module. And we have demonstrated this thing to run at 800 gigabit per second for each wavelength, so 2 of them 1.6 terabit. The results, this is a back-to-back, shows the spectrum, about 100 gigabaud wide. We divide the spectrum into slices. Each slice is called a subcarrier. This is the receive constellation. It looks very nice and clear. And with this, we demonstrated around OFC time an 800 kilometer link. This has been in the news lately. I think we had a live demo with Windstream on their commercial network. Other customer paying traffic was running on this piece of fiber. And we set a record for this fiber, 730 kilometers between Phoenix and San Diego. And while it was running, we did a round trip. So it was 1460 at 700G. So this is a world record by a factor of 2 or 3x better than other demonstrations of this technology. And overall, this shows that the holistic approach to integration, designing the PIC, the DSP, the electronics, the package, once you do everything together, you can actually reap a lot of benefits and performance out of it. I don't think something like this would have been possible otherwise. So we've developed all this technology, our PIC design, we have a fab, and as part of AIM Photonics, we do offer foundry services. It took us a while to develop this thing in a foundry model such that it's turnkey access and design. We have completed multiple runs for our partners. The same robust scalable fabrication process that we have developed for our commercial products is leveraged in this. So all the production controls, capabilities, everything that we use in our production line is now used in this foundry service. As part of developing this capability, we had to develop PDKs, and design automation environment, some examples here where you pull down from menu, click, connect things, and you have a circuit that will run well within our Foundry's capability. This works with many of the common design tools, whether it's simulation or layout, and it is offered through AIM. So I talked about two of the efforts. Now I will change gear and talk about something very new. It's about optical innovation. I think it's late in the day, so maybe it's time for us to sort of hear about things that aren't, offered already in the market, but a very different way of doing things. And again, this shows the power of how you can transform a network that everyone has been staring at for years and years to do a better job. So what is the problem? I think if you look at the pattern of data, you have a data center and many users. Some of them are wireless antennas, some of them are neighborhoods, some of them are enterprises, office buildings. What is clear is that everything comes from one place and it goes to many other places. So the pattern, it goes from one to many. When you look at optical networking technology, what you have is point-to-point connections, and these things don't match. So, in a mobile network, you have an antenna and many users. The antenna transmits, all the users receive the same signal, and they transmit back what they need to transmit back. So you have N+1 radios. When you look at how you connect the data center or whatever you have to users in optics, you have 2N transceivers. Each one of these will have to talk to something that's exactly the same on the other side. Now, that's a problem because optics use 2 times as many transceivers. It is too expensive and it is operationally very inefficient. Every time you need to provision a new service, someone needs to go put one of these in place, connect them together with its own fiber. That is not probably the most efficient way of doing it, and we want to do it differently. So wouldn't it be nice for optics to be like wireless? You have one 400G where the data comes from, different users, whatever capacity they need, and this guy transmits, they all receive, and at whatever bandwidth they need, they go back to the source. That would be an N+1 transceiver. So you can imagine if you could do this, you immediately get a 50% reduction in number of transceivers. You can transform the network and 70% plus reduction in cost of ownership. So how do we do that? So again, the way the problem exhibits itself in optical networking is that you have a hub where all the data is. Users, whether it's wireless, neighborhoods, or enterprise, the data comes from an aggregation point and 2N transceivers, each connecting same type of transceiver to each other in a coherent fashion to the edge of the network, and then on-off key at lower baud rate, at lower capacity to different users. How could one change this? If you put an electrical aggregation point, you put what we call XR optics. If you could make this gadget in a pluggable form factor where it is capable of transmitting from one to many, you can transform this network. So get N+1 transceivers. And also, once you can do that, you can get rid of this intermediate location. Just make it a passive optical coupler. So the network transitions from a 2 times N inefficient way to something where you've removed something and you've cut the number of transceivers in half. You do that, you get a lot of economic benefits. So how do we do that? In a traditional fiber optic link, you have a fat pipe, one blob of spectrum that connects 2 points together. For our point-to-point applications at Infinera, for the last 2 generations, we've actually sliced the spectrum into subcarriers. We do it because subcarriers provide better performance. It does better relative to some of the nonlinearities, and we have benefited from that for 2 generations of devices. So Imagine that you're slicing the spectrum into subcarriers. So what do you do with it? Subcarriers effectively become your currency, unit of capacity. So you can divide your spectrum into 50G subcarriers or 2 times as many 25Gs. This basically number of subcarriers is the total capacity. Each one is what you can use and connect to places. So for example, you can have a 25G user in a smaller form factor, pluggable. Someone who needs 100G, okay, that application will use 4 subcarriers. This guy would use 8 subcarriers, and the hub may have 32 subcarriers transmitting. So think of subcarriers as basically the units and how you connect them together. The way we would do it is divide the 400G into 16 subcarriers and connect them to each node at 25G. Now, if one of them needs more capacity, you can, like a radio antenna, send it 2 subcarriers and bill them for 2 of them. Or if someone needs a lot more, send them 75 and they would upload only at 25. The DSP capability that we have here and this concept enables, provisioning for this service in a way that matches the need without having 2 times as many transceivers and different fibers connecting them together in a way that is inefficient. So again, this makes fiber networks similar to wireless. And we have demonstrated this. This was around the OFC time where we used 400G, we split the spectrum, and we had a user that was only using 1 of them or 4 of them, and we connected them. And actually, I think the video is on our website, one can see it. So the concept is demonstrated already.
It's such a beautiful concept. Oh no, you're in the conclusion now. You're out of time, so please tell us what is the main takeaway.
So main takeaway is that vertical integration is critical. It enables holistic design, its foundation for innovation for us. Showed examples of how you do it on a PIC, how an innovative way of connecting users to a hub is enabled by vertical integration. In our business, performance matters. PICs provide performance and cost advantage. And I think we see a way of doing optical networking better, fueling new applications such as 5G. So we're really excited about this ourselves.
Thank you very much. You are one of the success stories of the interactive photonics ecosystem worldwide. I really want more people from EPIC to work closer with you. We already have made many introductions. We know what are the main challenges on the packaging, on the testing, on the system integration. I really want to engage you more. You are the holder of the indium phosphide flag. Thank you very much for being with us in this EPIC day. It is 1 a.m. right now in the Netherlands. I would like to ask my friend Werner Kress from Microsoft. Hello, Werner. What time is it in California?
Hi, Carlos. Here it's about 4 p.m. I'm actually in the state of Washington, not in California. I'm spending my time between California and Washington for Microsoft.
So thank you very much for being with us. Let's hear right now. Let's hear the beautiful, beautiful HoloLens story.
Hi, my name is Bernard Kress. I'm the partner optical architect at Microsoft HoloLens. Since 2015, prior to this, I was the principal optical architect on the Google Glass project at Google X Labs. Today, I'm going to talk about HoloLens and the state of the MR industry. Very excited to be part of this EPIC Photonics World Tour today, June 24th. So after half a century of 2D display technologies with very limited immersion experience, such as TV, computer screen, laptop, tablet, cell phone, watch, you name it, finally we go to near-to-eye immersive displays where the display sits about an inch away from your eye and provides an immersive experience spanning from 40 degrees up to 220 degrees. Why is this important today? Well, AR and VR have a tremendous impact on enterprise first, and then consumer. For enterprise, in 2019, more than 800,000 jobs globally have been impacted and enhanced by VR and AR. This number will go to a quarter, 25 million jobs, which is an amazing number, and this is only in 10 years. So this technology has the power to revolutionize how we work, but also has the power to revolutionize our private lives, and this will come a little later. We had an amazing SPIE AR VR MR conference earlier this year in February, just before the pandemic hit us. And we had an amazing turnout of companies that showed their latest products in MR and AR, and also their latest optical building blocks to build up next generation mixed reality headsets. So what is mixed reality? Well, it is the merging between the physical reality and the digital reality, which we call mixed reality, a blending of physical and digital worlds.
Mixed reality breaks down the barriers between physical and virtual realities. Let's see how we can alter realities across people, places, and objects. Here we have a real office, populated with real things. Let's now adjust reality by adding virtual objects to this physical space. Notice how these objects are aware of the real surfaces in the office. Next, let's replace the real person with an avatar. This allows her to be present, even though she is not physically in the room. Now let's adjust the environment itself and make it virtual. Notice how the virtual objects and avatar continue to persist. Finally, let's tie back this entire virtual scene to the original physical room. A subtle boundary grid can reveal real obstacles, making it safer to walk around this virtual environment. Mixed reality unlocks exciting new experiences that merge the physical and the virtual worlds.
So, as you have seen in the previous video, mixed reality can have tremendous impacts on a pandemic and post-pandemic world by allowing presence and real physical experiences while not being present in the same room with other people. Typical mixed reality sample use cases are remote assistance, training and task guidance, collaborative visualization, and contextual data access. But this is only the tip of the iceberg, and we're discovering with our partners who are using HoloLens in the field every day new use cases. Again, these are enterprise use cases. Consumer use cases are not very well defined yet, and it'll take some time to hit reality. Smart eyewear and AR/VR headsets. Let's see how they're compartmented. Well, first of all, and one of the first implementation of smart glasses was Google Glass. This is an extension of an eyewear. It's not an extension of a gaming console or a PC or anything else, or even a cell phone. It is an extension of eyewear, and more than 90% of the time, you would use smart glasses for their prescription correction functionality and less than 10% for their digital content. Second, we have the AR/MR headsets, and a typical example is Microsoft HoloLens. Here's a V1. These are extensions of computers, and at Microsoft, we really believe that mixed reality is the next computing platform. And last, you have the VR headsets. VR headsets are mostly an extension of gaming consoles, as you can see with the VR headset from Sony PlayStation 4, and also the range of Oculus headsets, again targeted for entertainment. So the question that arises is the following: is there a solution today which would allow merging of all three functionalities, smart glasses, AR/MR headset, and VR headset, into a single super headset. Now, mainly because of current optical technologies which do not allow such emerging at this time in terms of weight, in terms of size, in terms of power consumption for the display, etc. But this fusion will happen eventually, and this is what is very exciting. Now let's look at the mixed reality experience pillars. There are mainly two: comfort and immersion. Comfort comes in many different declinations, from wearable comfort to vestibular comfort to visual comfort and social comfort. So comfort and immersion, but I forgot to refer the third one, which is costs. Not so important for enterprise or defense headsets, but is crucial to target any hardware development that would target consumer. So at the confluence of comfort and immersion, we have, well, the device has to be obviously untethered for best comfort, has to provide a wide IPD, interpupillary distance coverage and prescription correction, high angular resolution, no screen door effects, small size, small weight, center of gravity, very close to the center of gravity of your own skull, vergence accommodation, conflict mitigation that relates to visual comfort, high brightness, high contrast, no ghosts, no pupil swim, and good thermal management. As immersion comes, of course, one would like to have the largest field of view possible, but also arm's length interaction, which allows us to talk about the third dimension of the field of view, which is the Z direction. World-locked spatial audio for immersion, foveated and peripheral displays, hard edge occlusion, active dimming, soft edge occlusion, high dynamic range, gesture sensing, which is very important. And at the confluence of comfort and immersion, you have motion to photon latency, which should be as small as possible, less than 10 milliseconds. And of course, very good 3D display world locking, which is based on spatial mapping and in our case, time of flight, 3D sensing. What is very important is that most of these specs are very tightly linked to fast, accurate eye tracking. These are examples of MR optical architectures in HoloLens V1 on the left and HoloLens V2.
Mixed reality.
So the previous video showed the introduction of HoloLens H2 as it was done in Barcelona at Mobile World Congress last year, 2019. Let's see the differences between the display engines and waveguide combiners in HoloLens 1 and HoloLens 2. Both versions of HoloLens use waveguide grating combiners, but the display engine is very different. In HoloLens V1, we have integrated two LCOS, liquid crystalline silicon, micro display illuminated by RGB LEDs positioned on the top center, as you can see on the lower left. These optical engines are linked to waveguide combiners. You can see them also on the upper left side, one per eye. There are 3 guides, one for each color, and these guides are replicated by a nano imprint. These guides have 2 functionalities: merge the digital display and enlarge the exit pupil of the display engine, which is very small, about 3 millimeters, to something that is much, much larger to accommodate a wide IPD range. This would be the eye box. In HoloLens 2, we still use a waveguide. It's a little different. We have a symmetric entrance port located on the top, and the field propagates in both directions rather than in a single direction. But the main difference is the display engine, which is not an LED LCOS display engine anymore, but rather a laser MEMS display, very similar to a laser MEMS pico projector. In the next video, you will see a little better how this laser MEMS display engine works. So, let's talk a little bit about the future of wearable displays. Well, the task is to get closer and closer to the brain, starting with VR headsets. And today we see many exciting technologies that allow reduction in the form factor of VR headsets by using pancake lenses, pancake polarization lenses, or multipath lenses. Some companies that develop this are 3M and Limbach in Madrid. And this is very exciting. There are also some efforts to provide ultra small form factor curved VR headsets, which are very, very different from the headset that you might find today in supermarkets such as Oculus and HTC Vive and Sony PlayStation. Very different. Then you go to AR and MR headsets, which typically are much smaller and much closer to the eye. Smart glasses, smart eyewear. We talked about Google Glass. There are many others. And then, of course, smart contact lenses. A few companies have started to work on this. You might recall the smart contact lens, which was not a display, but a sensor, a glucose sensor for glucose level monitoring by Google X. And also, more recently, a Mojo Display in the Silicon Valley, who raised some substantial capital to integrate a micro display based on inorganic LEDs and micro lenses on a contact lens. This is very, very exciting, but a lot of challenges due to data communication and, of course, also power on a contact lens. Then there are efforts in introducing digital displays in smart intraocular lenses. Not that much yet, but this will come. There are many efforts in implementing smart retinal implants, especially at Stanford University and other academic groups. And then last but not least, there are some attempts to even forego the photon and work directly on the visual cortex as a visual cortex implant that would allow you to see without having a pair of eyeballs. And this is not science fiction. It has been proven to be a viable path, but of course that poses a lot of questions for this type of future. Thank you for your attention. This was an introduction and very quick painting of the status of the MR industry today. I have a SPIE short course that goes a little bit more into details over 8 hours, so you're welcome to take this one if you want to know a bit more. Thank you. And if you have any questions, here's my email. Please send me any questions you might have. Thank you.
Thank you very, very much, Bernard. It's been so great to hear this story directly from you and to have the whole community understanding what is the present and what is the future of AR, VR, MR. Bernard, we've been talking a lot about this in the past with the community of optics, micro optics, freeform optics. Many people are here in front of you and they want to talk to you. If I could ask you, do you have perhaps a challenge or an idea of cooperation with the optics, micro optics, freeform optics, polymer optics communities?
Oh yeah, I mean, there's many challenges. As I said, you know, the challenges range from optimizing the optics for improving the wearable comfort, smaller, lighter. But of course, there is no Moore's law in optics, so you can't just shrink optics, just like you would shrink electronics. But going to different type of optics, I'm thinking about metasurfaces, for example. And polarization gratings, which are now used, polarization grating holograms, which are now used, switchable elements, even switchable metasurfaces that are really interesting and that are not implemented yet in any of these cases. But this is really where the challenge is. Not so much using traditional optics and reducing them, because again, there is no Moore's law in optics, and you're stuck with the law of étendue. But really using different optical technologies to implement functions that are better adapted to the human visual system and not a camera.
Bernard, one thing that I have observed in the community, in the optics community worldwide, is a new revolution of high-end micro optics, high-end freeform micro optics. Right. I think I have a common friend here in the room who I want to say hello. Reinhard, how are you doing today?
I'm doing still well. I started this morning 5 o'clock, but we'll say still two hours ahead. Hey, hi Bernard, how is it going?
Hi Reinhard, how are you doing?
I don't see your picture. Where's the camera? you're the most.
My camera doesn't work very well. Yeah. So it's a little overexposed, but you can see I have a COVID-19 haircut.
I see. You look like the Beatles, huh?
Exactly. Yes. Yeah.
Good to see
so it's true that freeform optics and custom micro optics is really paving the road towards more compact and more efficient head-up displays, and we see this every day. And I not so much in the classical architectures that you see in VR headsets, which uses just one lens, but architectures that use more, micro lens arrays and curved micro lens arrays. There's a lot of stuff happening now, and also nano photonics, such as metasurfaces. So,
absolutely.
Yeah.
But get back to the Bavarian hut once was our friend Jim, and some music from you, huh?
Exactly. We should do this.
Bernard, thank you so much for joining this crazy day that I'm living. Already doing this for almost 23 hours.
I have no idea how you do this, Carlos.
a lot of coffee, a lot of energies, and a lot of photonics. Thank you very much, Bernard.
Well, continue. And now, this is very exciting, and congratulations for this 24-hour thing. This is just amazing. Yeah.
And this is the amazing lineup today. We go from Bernard Kress to Brandon Collings. Brandon, thank you very much for joining today's my day, the happiest day in my life. You cannot imagine what it means for me to be in front of all these people talking about photonics, talking about my passion. The floor and the attention of everyone goes to LUMENTUM. The floor is yours.
All right. I hope my screen is coming up on everyone's picture.
It's perfect.
Okay, very good. So let me introduce myself. My name is Brandon Collings. I'm the CTO for LUMENTUM. Pleasure to speak to those that have survived the 22 or 23 hours for today. I'll be talking about LUMENTUM. We're quite a wide company, so I'm going to try to compress all that Lumentum does into 15 minutes, so bear with me. So I'll touch some of our photonic technologies, communication, sensing, and cutting. Okay, so just from who we are, we basically address 4 different major business units or major market areas. Obviously, communications is the heritage. That we're big in coherent transceivers and wavelength management. We do a lot of the chip level sourcing for all the datacom interconnect. We build very high power and ultra short pulse lasers for material processing, cutting, welding, semiconductor processing. And we've recently been the pioneer in using VCSELs for 3D sensing applications, primarily in handsets. So we're a company based exclusively on photonics, and we're global in every way. We have our headquarters are in San Jose. Just moved from Milpitas to San Jose, but we have another large site in Canada, a series of fabs and installations in Europe as well as Asia. As I said, we are a company that is based in photonics, and across the bottom here you'll see a lot of chip activity from VCSELs to edge emitters, direct modulated lasers, coherent technology, liquid crystalline silicon, and then some high power gallium arsenide pumps. And all of this, this is our foundation, and we build upon that for subcomponents to modules, all the way up to systems in the communication systems as well as the laser systems. And I'll go through, give you a bit of a snapshot on that today. All right, so for photonics, a big aspect of what we do is not so much, I'll get to the generation and receiving of light, but a big thing of what Lumentum's a leader in is managing light as it transitions through the network. So the simple example is networks aren't just simply point to point, but there's a lot of different paths, a lot of mesh network construction these days. And as you may expect, these systems have to survive real world faults and failures. So a simple example is on this little cartoon, if you have a network and you suffer some failure, you want to be able to move that light around from that failure and restore that connectivity without having to completely rebuild that connection. So something that's Lumentum's been a strong pioneer in, and that has to do with optical switching and wavelength management. Just to give you an example of how advanced these photonics have been over the years, in 2007, Lumentum was, or JDSU back in that time, was shipping a large number of simple 1x9 wavelength selective switches that were used in the configuration you see on the left, basically a broadcast and select architecture. Wavelengths came in, you broadcasted them to both locally adding and dropping wavelength AWGs, as well as the other side of the network, or other side of the node. And that wavelength selective switch was in charge of managing what's wavelengths left that network or that node. On the right is what we see in 2019, and it's obviously a much richer arrangement. You see there, we now have WSSs on the inbound and outbound of all degrees. These are actually integrated together into twin WSS structures. And we now use contentionless M/Ns as our add drop colorless directionless contentionless structures. So basically any wavelengths can enter this network on any color and go in any direction from transceiver to receiver without any manual intervention, any wavelength, any route, any time is sort of the mantra. So this gives you that flexibility to provision new services, restore services, balance your network, all through automated topology control. But from a photonics point of view, we like to sort of put in a nutshell what we've accomplished over this, roughly 15 years. Actually, it's longer now, 18 years. You can see on the bottom is years, and on the horizontal axis is a parameter we use. It's number of WSS ports per volume, per physical XYZ volume of the hardware. And you can see that in 2002 we had basically a 2-port device that was quite large. Easily could hold a door open. We now in 2020 have gone through almost 2.5, almost 3 orders of magnitude of improvement of this number of ports per volume. So we've gone from 2 ports to today's twin 8x16, which is somewhere around, what is that, about 60 ports in a device that's actually smaller than the original 2x2. So you can see this nice trajectory, and that has a lot to do with all the photonics, optical design, micro lensing, new improved switching mechanisms. All have been packaging styles, thermal management, all that photonics that goes into a mature manufacturable switch. You can see that progression over those years with this chart. From a coherent transceiver point of view, obviously we've gone from very simple direct detect a decade ago to now very compact, very high speed, and from a photonic point of view, extremely complex capabilities. And here you see what we're doing today in photonics for coherent. We're putting 32 gigabaud, this is a workhorse of the industry today, 32 gigabaud CFP2 ACOs. All that photonics is packed into an ACO transceiver. To do that, you have to execute all these functions you see at the bottom, which I think we're all pretty familiar with, but in something that's about the size of your thumbnail. And we can't stop at 32 gigabaud. We're currently rolling out 64 gigabaud. We need to get even smaller again to fit into a DCI application for 400 gig ZR in a very small QSFP form factor. And it ain't gonna stop. We need to get to 64 to 128 in these similar form factors. And the only way to do this is through very advanced optical integration, chip level, indium phosphide, silicon photonic chip level innovation and integration. You can see here, just to put that into scale, this is a CFP2 with the lid off. You can see it basically composes of 3 things: the DSP itself, a little chip that's here. This is the support circuitry, backplane connector, and obviously the optics resides in this gold brick in the front. That's a CFP2. That's the luxury. That's the minivan of optical compact pluggable modules. This is a QSFP DD. This is the same DSP, and you can see the relative size, and all the optics has to fit into something considerably smaller. These are 2 LC ferrules, just to put this in perspective, and all this has to pack into something extremely tiny. And this is what we're doing at 64 gigabaud today through very advanced semiconductor photonic integration. Okay, switching to hyperscale interconnect. So that was coherent transmission technology. We're now talking about the interconnect. And for this, Lumentum is one of the world's leaders in the chips that go into these interconnects, where we're talking about EMLs, DMLs, and VCSELs that ride into whether it be the servers at the bottom at 25 gig VCSELs or AOCs. Direct modulated lasers are very cost-effective solutions at a little bit lower of a data rate for maybe top of rack switches, 100 gigabit applications, and 400 gig applications are using today's 100 gigabit per second EMLs in a CWDM format. Just looking, there's a lot of other applications, including 5G backhaul, whether it be 25 gig or 50 gig for front haul or mid haul. A lot of applications for these direct detect based 1310, 10 kilometer, 20 kilometer applications. And these are really just emerging with 5G, primarily driven in Asia. Just to give you a very quick snapshot on performance, you can see this is a DML operating at 25 gigabaud. You can see that the PAM4 signal of a higher quality, higher fidelity EML versus a 25 gigabaud DML. You can see you get pretty much the same performance. DMLs, again, are cheaper, lower power, smaller, so much more efficient if you can get them to work. Here's the latest results at 23 gigabaud. So this sources to 100 gigabit per second per lambda. So this is the 400 gig generation. It's not exactly the same. You can see MLs are much higher performance, but we're getting close. We're getting closer with DMLs, and the mantra is basically DMLs tend to be about one generation behind their EML brothers. Looking quickly at VCSELs, VCSELs are something the industry has worked hard on for a bunch of years for data communications, and we're now beginning to, well, we've transitioned them into 3D sensing applications, and it not naturally included a lot of work on the design, but the critical aspect we had to overcome was quality manufacturing and cost-effective doing so. So we've moved into a 6-inch state-of-the-art gallium arsenide foundry and highly concentrated on the quality of the process, the repeatability of the process, the on-wafer testing. And you can see we've delivered, well, it doesn't say here, but we've delivered hundreds of millions of VCSELs and to date have the quality that reflects zero field failure. So this has been a very good transition from datacom to 3D sensing, and now it's paying back. We're now taking our 3D sense, our datacom VCSELs into our 6-inch foundry and finding very cost-effective ways to build datacom VCSELs. So it's coming full circle. For sensing applications, this again is this is using VCSELs, and the original 3D sensing uses basically a spot-based pattern that gets lit onto the scene, and then simply the distance of those spots transitions to the distance from the camera. But that's not usually good enough. So in the future, we need to move. It's good enough for about 1 meter, but we need to get to 10 meters for, to cover an entire room, to depth sense a room. And then for automotive applications, we need to get even further up to 200 meters. All this has to be effectively done in compact form factors. So structured light, we structure the light, then we look at the density and the difference between pixels. To improve this, we need to get just basically more power, better efficiency, and tighter apertures in our VCSELs. But to go beyond that, we need to move towards time of flight, which is basically send a pulse, wait till it comes back, and do that in a 2-dimensional zone. To do that accurately, you have to have very high peak powers, very short pulse widths, so you get the signal to noise, and that drives a lot of requirements onto the VCSELs to generate these very high power short pulses. For automotive, you can use the same technique, time of flight. You can see some of the 200 meters sensitivity at a pretty wide field of views. Think of putting this in the front of your vehicle and trying to sense a brick 200 meters down the road at 120 kilometers an hour. So we need some pretty compact, very cost-effective yet high-performance solutions. And there's 2 styles to do this. Time of flight is one of them, and the photonics unit that are necessary for these applications really require very high power. So we're moving to multi-junction stacked VCSELs. So you're basically building 3 VCSELs on top of each other. You increase the voltage, decrease the current per power, and that's very effective to generate high peak power short pulses. For FMCW, which is a coherent style, it's how radar activate is done. You can take very similar technology to what's done in coherent telecommunications and use that for frequency modulated CW LiDAR. You're basically chirping a laser, sending it on the scene, having it come back, mixing it with your local oscillator, and detecting the difference in frequencies. But the technologies you need are very, very similar to what we use in coherent, as well as some scanning technologies from our optical switching products. So this is a very nice reuse of photonics for a brand new application. I think I'm coming close to the end of my time, so let me quickly blow through. The coolest pictures I have is high power cutting, welding. These are kilowatt class fiber lasers, which are replacing the conventional CO2 lasers simply because they're solid state, they're have better reliability and operation costs, and they're pretty simple. Very high power pumps and multitudes of them combined together, pumping a double clad ytterbium fiber, and delivering, these pumps deliver about 200 watts per pump assembly, ultimately delivering about 4 kilowatts per laser. And then we couple multiple of those lasers together. You see 3 of them down here to generate up to 12 watts of total cutting power and very high brightness delivery fiber. This will be my last slide. power isn't the only thing. Sometimes you want to generate very short pulses. Actually, let me go to the next slide, because power simply cuts with thermal properties, but very short pulses cut with more ablation techniques. And you can see the difference between a thermal drill here on the left with the CW, to nanosecond pulses where you're getting a mix of ablation and thermal, to pico where you're mostly ablating, to femto where it's a very clean cut, simply because you're ablating the material, not sort of melting and thermally removing it. So this is a very quickly emerging space, particularly as some of this is an example of via hole drilling in flex PCBAs, which, as you can see, is now kind of the engine and the interconnect for consumer electronics. This is an iPhone where you see all the flex elements circled. So I think I'll stop there. Please take some questions.
Fantastic, Brandon. Thank you very much. I have to say one thing. Lumentum is very engaged with EPIC. Your people are actually coming to all our online technology meetings on 3D sensing, on high power lasers, on datacom telecom transceivers. It is great to have in 15 minutes an overall view of the whole company, and we already know how to cooperate between the members and Lumentum. But I would like to ask you something, because I know that you are a visionary. You just told me about the last 20 years. I want you to imagine this conversation in 10 years. What is your preferred future for Lumentum?
Well, I think I mean, certainly we interact with a lot of different market spaces, and I think the prognosis on telecommunications and the need for optical communications, I don't think anyone has any evidence that growth pattern and that infrastructure requirement for modern day society is changing. I mean, I think the COVID-19 work from home progression is just is really more just a realization of that, not a real gigantic transformation. But we have some physical, we're approaching Shannon's limit in that area. We have a lot of activities that are looking to say, how do we continue to grow capacity, even though we're facing that very fundamental limit? And that's, I think there's some very doable engineering requirements that we can overcome to continue to satisfy that. And then in the sensing domain, I think we're really just getting to the beginning period of what optical sensing can do. Yes. Certainly LiDAR and cameras are not new, they're age old, but getting the photonics matured, compact, integrated, manufacturable, in a form factor and at a cost point that opens up new applications like mobile handset Face ID, or LiDAR for, iPads now have a version of LiDAR in them, and certainly we're trying to put it in consumer vehicles. Once you open up that third dimension, what other applications can you do if you have 3D sensing and very high precision depth sensing in your toolbox, if you will? So I think we have a long road ahead in telecommunications, and an obligation to continue to grow the capacity to suffice our video needs. But yeah, on the sensing space, I think it's going to be a much more dynamic, exciting future.
Sensing plus consumer, I think that's, in my mind, the future of all the companies that are in the big cell for datacom, and they realize that the sensing is the market, and now we go to the 4D sensing, we know to environmental monitoring. I think there's going to be a bright future. I think, Brandon, on that we agree. Lumentum is doing fantastic, and it will be doing fantastically. It was an honor having you with me today in this completely crazy day. We go from Brandon Collings to Lumentum.
Right, thank you.
To Claudio Mazzali in Corning. What a day, right, Claudio? Thank you very much for joining us today. Tell us how the EPIC members can make Corning communication technologies great as you are, even greater. The floor and the attention of everyone in the whole world is yours.
Thank you, Luis, and congratulations for the event. Can you guys hear me okay? Can you see the slide?
Loud and clear, crystal clear.
Okay, perfect. So this is amazing. I'm not the last one, but we're getting close to this long day. So let's see how it goes. And actually, I have to say thank you to Brandon. He's going to make my presentation much easier after his overview of LUMENTUM and some of the markets there. And what I decided to do here is really not going through products or specific technologies, but to make a reflection on the impact of optical communications, because this is a special year for us, right? 50 years in the journey here. This is a journey that started 50 years ago in the 70s. So we are celebrating the 50th anniversary of optical fiber, the 50th anniversary of optical communications, because by a coincidence, you got optical fiber and the room temperature solid state laser coming up at the same time in the 70s, in 1970. So I'm going to go through that. I'm going to go cover a little bit of where we are and some of the growth vectors that we have, because it is a special year, as Brandon said, with what we're living. This event is a great example of what we can do with this technology that we have been developing for 50 years. So everybody knows, right? It was Cal that came with the vision of, hey, if somebody can get to a less than 20 dB per kilometer optical waveguide, we can probably transform the world and use optical communications as a way to connect ourselves. We counted as the invention of fiber in the 70s, at least the low loss fiber, when folks come up with 17 dBs per kilometer of waveguide. And I put here, actually, this is a copy of Don Keck, from Corny Don Keck's lab notebook, where he actually found it, did the first measurement. It was a Friday afternoon on a 17 dB per kilometer. First time they were able to get below 20. And I think even better than the 17 is his comment there, whoopee, because he knew that he was getting something special. But even today, Don Keck is very clear in saying that he had no clue that would be the beginning of something so transformational. And of course, there are several other things that came after that with AT&T, McChesney with the MCVD, and of course NTT on Aizawa with the VAD, and lots of other contributions to make fiber and optical communications where we are today. And that 17 dBs per kilometer right now, if you look, the record is around 0.14 dBs per kilometer, and that is standard single mode fiber. And there is a lot of coming at with very different types of fiber. Multi-cores is starting to become more real, more practical. It's an idea that has been there for a long time, but now there are some real applications that can really take advantage of that. Field molded fibers as well, starting to get some traction in some areas. And we just got some pretty interesting results with anti-resonant fibers getting to laws that are pretty good, 0.65, I think, ORC in Southampton reported recently. And I think when we think about this, where this is going, right, and what, how this is started and where this is going, optical communications is actually, it's much more than just connectivity or connecting us all. If you pick your buzzword of the day, right, 5G, cloud, AR, VR, AI, autonomous driving, IoT, quantum communications, it's kind of difficult to find if any of those things would be as effective as they are today or will be without a very robust network behind the scenes to support that. Just as an example, I picked here the Gartner Hype Cycle for emerging technologies. They update that every year. This is not the latest one, maybe it's a year old. And I was looking to this list of emerging technologies, and I kind of did my assessment, okay, which one of those would survive or would exist or would be effective without relying on a super robust communications network, right? And I put them in red, and it's a big percentage. So what I'm trying to say here is that we think about optical communications about, can you still see the slide? Everything okay?
Everything crystal clear. The floor is yours.
I'll try to not say anything bad so the Zoom doesn't go bad at me. So things are moving more, as I was saying, right? Things are moving more to the optical side. We try to look into this diagram here, data rate as a function of distance. And then we have this rule of thumb. It's not physics, it's a combination of physics and economics that tells us that when you multiply the data rate by the distance, when you're getting to 100 gigabit meters per second or close to that, things go to the optical domain. And of course, it's easy to see those things when you look into the longer distance kind of transmission, submarine, long haul metro. All those are already on the optical domain, but there are some interesting new areas, and that's what's driving the growth for this space now. I think Brian from LUMENTUM talked a little bit about some of those, but it's access 5G, fiber to the home. This is driving more optics now, more photonics into this area. And then you look into two pieces of data centers, not the switch to switch. Switch to switch is already a lot of optics there, but now DC switch to server is one opportunity coming, and then inside server, of course. So the red bubbles here are the ones that are driving the growth. And I'm going to talk specifically about this feedback loop that we see between the hyperscale data centers and 5G, right? You got the big fabric, optical fabric inside the data centers, right? Enabling AI, VR, AR, machine learning, things that were described today in this optical cloud, requiring much more, providing much more services, and also requiring more connectivity at the access. That's why we see the hyperscale data centers and the 5G access as the two big drivers. And we always look into, okay, what's the need, what's the limitation, and why photonics, why optics to solve that? Starting with the 5G, the need is very clear, right? There are the 5G KPIs, the low latency, the high speed, the high bandwidth, all those things are big needs. The limitation is basically spectrum. There is a technical economic limitation there I will describe in a minute. And actually photonics and optics is coming here to the rescue. How can you better utilize the spectrum? How can you take more out of the very expensive megahertz of spectrum in wireless that you can take? And there is a similar case going on in hyperscales, and I'll describe that later. But let's go to 5G first. I'm trying to go a little bit quicker. You guys know three different ways that I can get more bandwidth, right, in a wireless network. I can buy more spectrum, I can increase the spectrum efficiency of my radios, or I can put more antennas in the ground. I share my spectrum with less people, that I get better services. Spectrum is not cheap. You can see here, this is 3 years old, 2017, 31 megahertz, which is nothing when you think, for us, optical folks, but in RF is a big deal, 31 megahertz for $8 billion. So if you can find ways to optimize the use of that spectrum is super important. And the simplest way to look, skipping the equation for a second, you increase the densification, you put more antennas, you need less spectrum. Of course, as you put more antennas, your cost to build that network goes up. So cost of spectrum goes down exponentially, 1/x. Cost of putting antennas in the ground goes up linearly. You put those two curves together, you get into a point where there is a minimum somewhere. There is an optimum point into how much you're going to densify. And as capacity grows, that minimum point keeps moving to the right, more and more densification. Just to give you a visual picture of what we're talking here, if you pick an area of about 10 by 10 kilometers, with 3G, you would need one antenna. 4G, about 25. If you go to 5G, it's more than 400 antennas in that 10 by 10 kilometers. Each one of those antennas or antenna sites, you probably need between 1 and 6 fibers there. And of course, those fibers with WDMs and transceivers, so photonics and optics there. And depending on the population density in those areas, you will need even more than that. Now, let's look into the other side, right? Into the data center space. The chart on the top right is from Facebook, right? I think it's a famous chart. The traffic, the internal traffic into data centers, it was driven this for us, for photonics, for optics. It's a lot of servers talking to servers. The technical economic limitation is that you have to have all servers connected to all servers, and you don't have a switch capacity for that. You don't have a single switch. So you're going to solve that also with lots of optical links. Basically, if you need to connect 100,000 servers to 100,000 servers, that's what you have into a big hyperscale today, and you don't have a single switch that has 100,000 ports there, you're going to have to build that fabric with many switches all interconnected. They all need to be high-speed optical links. And that traffic is growing faster than the capacity of the switches anyway, so that trend tends to keep going. So people have to change the architecture. They used to have clusters and build the data center in a different way. Now they you saw a similar chart on Brandon's presentation from Lumentum recently. It's a different architecture where you have this fabric connecting all servers to all servers. The amount of optical links here and the amount of fiber that goes there it's just unbelievable. It's super impressive, and it's growing as we speak because of those new applications that I was talking about. Every time you got more AI and more machine learning and more VR, AR, more of those things will happen. So I try to put some orders of magnitude here to give you a feeling. In one single data center that one example, one of our customers here in the United States, in one single campus, you can get more than 1 million fiber kilometers in a single data center campus. And as a reference, 1 million kilometer of fiber is what you need probably to do fiber to the home to the entire suburbs of Dallas, right? About 2 million residents. So that's how much fiber and connectivity you got into a single campus there. And between the buildings on those campuses, you're gonna have many cables, and with more than 3,000 fibers in each one of those cables. So it's just unbelievable what's going on. Those are the two major big areas of growth that we see now. And when you think about future, many areas that are leveraging that technology. And specifically in data centers, we see, as we said before, the last connection between switch and the servers, right? The top of the rack to the server is still copper, mostly. There is a chance that will move to optics at some point. Don't know yet when. Maybe we'll never move, but we believe that there is a chance that, again, techno-economics will drive to that at some point. And even go inside. When you think about onboard optics and co-packaged optics, lots of activity in the industry now, bringing that optical signal inside switches and getting very close to the switch ASIC. That brings to my last point, something that we are working with some partners, and I know some other folks working on as well, where you bring that optical signal now outside of the fiber, and you bring that to flat waveguides, perhaps in flat glass, a flat glass that becomes already the substrate where the silicon, the switch ASIC is. So basically trying to bring that optical signal as far as you can. So I went fast trying to recover some of the time here, but I guess my final message is 2020, a very special year for this area of our industry. 50 years, it's an anniversary. We're planning to celebrate that. And I think lots of things bad happened this year, of course, but it always reminded us that the criticality of photonics and optical communications, right? The way that we work, the way that we entertain and interact with each other. And I think nothing better than an event like this one to show how important for us to rely on a fast and reliable network that is enabled by photonics and optics. So thank you.
Thank you very much for an inspiring talk. Of course, we are completely crazy. I don't think this is an example of anything. 24 hours cannot be healthy. We cannot really sell this as added value for humanity. But we can tell you one thing, which is that the whole supply chain is wondering about onboard optics. What is your vision here? Is onboard optics somewhere a stop on the way towards something bigger? Is onboard optics something that it has an idea, but we go to co-package optics? What is your vision on this?
Yeah, that's a question that there is a lot of people trying to answer now. I think that until sometime recently, I think it will ever happen or not. I think we passed that phase. I think now it's when. There is some discussion when that will happen. I guess right now, if you pull the industry, you're gonna get somewhere between 2025, around that time frame. Of course, there are some tricks that folks may use to push that far. But you said well, right? It's the ecosystem. It's us. We are the folks that will have to make that happen by creating solutions that are low cost. Costs will drive this thing. I think that there are ways to survive the capacity. People say that the 50.1 terabits per second switch ASICs may be a driver for that. Some folks say that, nah, not yet. Maybe we need to get to the 100. 50 terabits is not enough to push for optics. But it's not only when copper or PCBs will not be capable anymore. It's when we make the optical solutions cost effective for that, right? And not only the components, but mainly the packaging and assembling of that. we are spending a lot of time on termination, connectorization, and making sure that that connectivity, when you bring the optical signal from the fiber to the switch ASIC, that's a critical point that we're spending a lot of time, how we make that simple and low cost. So it's up to us.
Thank you very much, Claudio. It is up to us. We are getting together constantly. I'm sitting with the IEEE standard people next week, try to understand what this very weird text is saying and to see what we can have clear. But the key question here is that if we all work together, and this is what EPIC stands for, if we all work together, amazing things are going to happen. Thank you, Claudio, for a great, great contribution to this crazy, completely crazy day. And we go to the next presentation. We go to OPTASENSE. We go to Christoph. Thank you very much for being part of this adventure, this epic journey, an impossible journey in normal circumstances, but the world has gone crazy and so has EPIC. Christopher, the floor and the attention of everyone is yours.
All right, thank you. I appreciate it. Thank you for the invite. Let me pull up my presentation and I shall share the screen.
In the meantime, I would like to thank the European people that are with me from the very beginning. Greg, you are a star, and all of you. You guys have so much energy. You give me energy. Christoph, the floor is yours.
All right, so you guys see my screen?
Yes.
All right. So as stated, I'm Chris Heisler with OPTASENSE Corporation. I'm going to be going over some basic insertion loss measurements on connectors, fiber optic patch cords, etc. Quick overview of OPTASENSE and who we are. We've been designing fiber optic test equipment for 20 years. We specialize in measuring insertion loss and return loss. It's kind of our core technology. We tailor test equipment to the needs of our customers, and we take pride in simplifying the test and measurement process for our customers to help increase efficiency, especially in the production realm. One of our main pieces of equipment is the OP940. It tests insertion loss and return loss, 2 wavelengths in less than 3 seconds. So it's finely tuned for a production environment. You can use external switches to expand the channel count. This allows you to test MTP or MPO type connectors. And a quick overview of the insertion loss webinar that I'm going to be giving. So I'll go over what is insertion loss, where does it come from. So we'll be looking at single mode and multi-mode fibers. And also we'll be looking at launch conditions in multi-mode fiber and how this affects insertion loss measurements. So insertion loss in fiber optic cables is the amount of light that's lost with respect to the light going into the fiber optic cable. It's typically expressed in decibels, and it's basically the ratio of the input light with respect to the amount of light coming out, right? If you have 1 milliwatt of power coming in and you have 0.5 milliwatt coming out, you're losing about 50% of the light, which gives you about a 3 dB loss. So where does insertion loss occur? Occurs at 2 main locations along the fiber optic cable. One of the main locations is at connections, so where 2 fibers mate together. This can happen between 2 connectors, 2 fusion splices, maybe mechanical splices. So here you see we have a launch fiber. We have light coming down the launch fiber. It's going to enter into the connection. And when it hits the connection, some light's going to be scattered. Some's going to exit through the cladding. Some will be reflected back. And this reflected light is typically referred to as return loss. However, return loss doesn't contribute much to actual insertion loss at matings. Another location where loss can occur is basically along the fiber optic fiber itself. So fiber has inherent attenuation due to absorption and scattering. So as the light travels down the fiber, some of it will get absorbed in the fiber and some of it will be scattered and exit through the cladding. So as you see, as it travels down the length, you lose some of the light. This is typically referred to as attenuation. Attenuation is expressed in dB per kilometer. A standard single mode fiber has about 0.3 dB of attenuation per kilometer. And standard multimode fiber, so say a 50 micron OM3 type fiber, has about 2 dB per kilometer of attenuation. So connection loss comes in a few forms. There's a few different ways to lose loss when two fibers are mated to each other. One is a lateral misalignment. So you see we have two fibers butted up against each other. There's a slight misalignment. Again, another misalignment. And as the light travels through that connection, it's going to experience, in this case, at this, can you guys see my cursor right now? All right, so at this core cladding overlap right here, where light experiences that overlap, there's going to be light that actually deflects out of the cladding, and that induces loss on the connection. Another area of loss is mode field diameter mismatch. The mode field diameter describes the electric field intensity of the light exiting the fiber. This typically relates to how much light a fiber can accept for single mode fibers. These are typically in the 9 to 12 micron range for a standard single mode fiber. And you can think of the mode field diameter as the effective core size of single mode fiber with respect to the wavelength. So in this case, we're gonna, light's gonna travel from a large mode field diameter into a small mode field diameter fiber. And you'll see as it travels through, you're going to lose light again at these core cladding overlaps. And then some light will also transfer down into the fiber. So a large mode field diameter into a small mode field diameter induces a large loss. However, on the flip side, if you have a small mode field diameter into a large mode field diameter, you'll see that there are no core cladding overlaps when you're going from the small mode field diameter fiber into the larger mode field diameter fiber. So you'll see a very minimal loss going through that type of a connection. Another type of misalignment is an angular misalignment, and this will also induce loss on a connection. So you see here, if you have a slight angle on the receiving fiber, as the light travels through that connection, you'll still get some light that exits through the cladding. Now, for multi-mode insertion loss, multi-mode links present a distinct problem when testing insertion loss. So a single mode fiber only has one mode that can induce loss. Multi-mode fibers have many modes that potentially can induce loss. So in this case, we have kind of a perfectly aligned fiber. We have a multi-mode fiber that has, a completely populated core. And because of the perfect alignment, everything travels through this connection. So you have roughly a zero loss going through it. Now, if light is propagating through the entire core, so you have a fully populated core, small misalignments will induce loss. So as we misalign these fibers, you'll see some modes transmit through, some are lost. Again, this comes at a core cladding overlap here. So that mode will be lost through the cladding, inducing insertion loss at this connection. Now, also a core size mismatch would lead to losses. And this is similar to a mode field diameter mismatch in the single mode fiber. So when you purchase 50 micron fiber, 50 micron is the nominal core size of that fiber. That fiber can vary anywhere from 47.5 up to 52.5 micron. So if you have a larger 50 micron fiber launching into a smaller 50 micron fiber, you'll see losses as well. So if we reduce the size of this fiber, you'll see that at these core cladding overlaps, we'll lose light as well. So that induces more loss. Now, the loss of the connection is dependent on how filled the launch fiber is. So in this case, the launch fiber has all modes populated through it. So if we induce a loss on this connection by presenting it with an alignment offset, we'll see that we experience a loss here, right? So we've populated the entire core with light with as many modes as possible. And we see these two modes here at the core cladding overlap, they escape through the cladding. So if we look at the transmission ratio here, we have 8 modes coming out of the fiber and 10 modes coming into the fiber. We get roughly an 80% transmission which corresponds to about 1 dB of insertion loss. Now, if we reduce the launch of the, or reduce the amount of modes in the launch fiber, so let's take the modes away from the outer portion of the fiber, you'll see we now have 8 modes coming into this connection, and we have 7 modes coming out. One of these modes was at the core cladding overlap and escaped through the cladding. So we have 8 modes coming in, 7 modes going out. So we have a 7 to 8 ratio. So that's 87.5%. This gives us an insertion loss of 0.56 dB. Now, if we restrict the launch even more, we have 6 modes coming in. And because we restricted it so much, there is no core cladding overlap with any of the modes. So we get 6 modes coming out. So these 6 modes coming out give us a 100% transmission ratio, which gives us an IL of 0 dB, right? So now a more filled core on the launch fiber produces a high loss. A lower filled launch fiber produces a low loss. So in all of these cases, we're testing the same connection and the same quality of connection, right? However, we got different results. If we test with these lower filled fiber, we get a really good result. If we test with an overfilled fiber where all modes are populated, we get a high loss. So there's a discrepancy there, right? So due to insertion loss being highly dependent on launch fiber fill, standards were developed to harmonize measurements. So in practice, insertion loss on cable assemblies really only matters on installed cabling, right? So when we produce cables, we want to test them and make sure that when we pass them, they actually function in, when they're installed in a communication system. So encircled flux, the encircled flux launch was developed, and what this was developed for was to mimic the worst case transceiver VCSEL source launch. So when we're testing our fiber optic patch cords, in the production facility, we want to make sure that we test them to the worst case scenario, so that when we take them from the production facility and put them into the field, they're going to function in the field, right? If we tested them with the best case scenario in the production facility, when we install those in the field, there's potential for failure because we did not, because they may experience a worst case VCSEL launch in the field. Encircled flux was also developed though, so that multi-mode insertion loss measurements were more reproducible. So if I take a multi-mode cable and I test it with a piece of equipment in one lab, and then I take that same multi-mode cable, test it with another piece of equipment in another lab, I should get the same results. So if the equipment was encircled flux compliant, I should get very good agreement amongst those results. However, if the equipment is not encircled flux compliant, you may get quite varying results on your measurements. So here, just to give a general overview of some encircled flux terminology. So we have on the left here an overfilled fiber, so we've populated all of the modes. We have a near-field profile here that's fairly wide. We've populated the entire core of the fiber. And then on the right here, we have an encircled flux results graph, which just shows that we failed in matching the encircled flux compliance. So we're on the low end here, so we want to be in the middle of all of these steps. We're on the low end, so we failed. Overfilled launches don't satisfy an encircled flux requirement. So now we've reduced the launch. We've taken a few modes away from the launch. You see that our near field profile is a little bit narrower, so we're not fully filling the whole core. And then you'll see that we've come into encircled flux compliance. All of our measurements fall between this stair step here. Now we could go further, and if we go further, we now have what's called an underfilled launch. So we have a very narrow near field profile, and you'll see that on the encircled flux graph, we've also failed. So we've gone too far in limiting the amount of modes. And that's the point of the encircled flux, is to keep that launch as narrow as possible, or the requirements for that launch as narrow as possible, so that when we do our measurements in the production facility or in the lab, we get good agreement amongst our measurements. So a quick recap. Insertion loss represents the light lost through connections and through fiber. Light at connections is lost due to lateral misalignments, angular misalignments, mode field diameter mismatches, and core size mismatches on multi-mode fiber. And light is lost through fiber due to absorption and scattering. This leads to attenuation along the fiber. Insertion loss in multi-mode fibers is extremely dependent on the light filling of the fiber. So launch conditions were standardized to make insertion loss measurements on multi-mode fiber more reproducible, and that's where the encircled flux launch comes from. Thank you for your time, and if you guys have any questions, go ahead and fire them at me.
Thank you very much, Christoph, the CTO of OPTASENSE. It was really great to see all the way that you want to understand the insertion loss. Is there a similar way that you have for reflections? Because at the end of the day, I'm also very scared of those.
What was that again?
Reflections. You talk a lot about insertion losses. You never mention reflections. I'm very, very worried about those too. Do you also characterize them?
You should be worried about those. As shown, we have an instrument that measures return loss as well at connections. So reflections do affect the amount of light that's transmitted through a connection. However, at most typical fiber optic connections, these reflections are very low. So the light loss going through the connection doesn't affect the insertion loss much, but the light reflected back towards the source can potentially damage a source if it's high, or you also potentially get standing waves inside your communication line, which increases bit error rate issues.
Christoph, there's a lot of companies in the fiber assembly sector in EPIC that want to talk to you. I'm going to make the introductions later. It's been such an amazing day. I would like to thank you very much for being part of this historical day in the life of EPIC, historical day in the life of Carlos and me. And we go to a common friend of all of us. We go to the person who started the idea of Luxtera and now is a person that everybody is very envy of. Peter, thank you very much for joining us today from Cisco. I still have to say Luxtera sometimes. From Cisco, the floor and the attention of everyone is yours.
Thank you very much, Jose. I'm going to share my screen. Yeah.
It is coming. It is not here. By the way, do we look tired? That's Carlos and me. Do we look tired? We've been doing this already for almost 24 hours.
Yeah.
Here you are. You look fantastic. All right, let's start.
So I want to share my presentation here.
It's the last but one. I'm going to feel sad when this is over, I'm going to feel really, really like crying of happiness. No, I'm kidding. It's been such a great day.
Moment, yes.
It's the bottom of the Zoom window. There is an arrow up that says share screen in green. Press it, and then there will be some options of which screen to share.
A moment, please. Okay. Yes, that should be okay. Sorry for that. It's only
no problem.
Yep, there we are. Okay,
yes,
can you see my presentation?
Yes, we can.
Okay. Yeah, the title of my presentation is High Density Optical Transceivers. As an introduction here, I have a slide that shows that over the years, the data rate for optical connections and electrical connections has increased significantly. So what you see here in this graph is over the years, the bandwidth of optical transceivers and optical and switch ASICs. So an optical transceiver connects a switch ASIC with an optical network. And for that, you need to have an electrical input and you have also an optical output. So for the electrical input, the data rate has been going from 10 gigabit per second, 25. Currently, there's an introduction of 50 gigabit per second. And in the pretty near future, we see 100 gigabit per second as the electrical interface to optical transceivers. That is the data rate of this thing, electrical signals that go from on the PCB, from the Ethernet switch chip to the optical transceiver. When you look at how the data rate, the aggregate data rate of the Ethernet switches has evolved, you see there we went from 640 in 2010 gigabit per second up to now at 6.4 and to 12.8 even. And in the future, we'll see 25 terabit switches coming as well as 51. And for that, you use optical transceivers to connect these electrical interfaces with each other. And that results then in optical transceivers, 40 gigabit Ethernet transceivers using NRZ modulation in a very standard QSFP plus form factor. And currently, one of the workhorses in most of the data centers is 100 gigabit Ethernet, where the electrical signals and the optical signals are both 25 gigabit per second. And the form factor for those transceivers is usually 100 gigabit Ethernet QSFP 228 module. And in the future, we see higher data rates coming. We see that for the electrical signals, there's a switch to PAM4. Also for the optical signals, a switch to PAM4 to increase the data rate per differential pair or per optical fiber. And it is like the evolution that we're seeing. And you see also that the customers don't want to have the systems grow dramatically, so they want to have higher density, and hence they need higher density optical transceivers. Looking at the technology that is there, I mean, currently there are many companies, and us as well, introducing 400 gigabit optical transceivers. And beyond that, there's definitely a lot of opportunity to go further than that. You can go to higher modulation rate, you can add more lanes, you can add more wavelengths. You can look at special modulation, and specifically, there's also a lot of talk about using coherent communication for the intra data center interconnect. Coherent is usually used for long distance, but people think also using it for shorter distance. But we see that most of the customers want to have backwards compatibility. That's something that always comes back. People want to have backwards compatibility with the older technology. That is an important point. And another important point is that all these applications where things go faster usually dissipate more heat, and power management and heat sinking becomes a very important element. Another thing is that many companies, and we as well, have invested a lot into the 400 gigabit Ethernet infrastructure. And therefore, we believe that it will stay for a longer time because we need to have a return on the investment. And so when we see emergence of higher density optical transceivers, it will likely be an instantiation of multiples of 400 gigabit Ethernet rather than 800 or 1.6 terabit Ethernet. And here you see an example. So on the left, you see the workhorse. That's the QSFP 28, 100 gigabit per second transceiver. At the left, there's the electrical input. At the right, there's the optical connector for the optical output. Everything is 25 gigabit per second. For the next generation that is currently being introduced, the package is in a 400 gigabit per second QSFP DD. There, the electrical signals are only at 50 gigabit per second. So you need double the number of electrical connections as you need on a QSFP. So that's why you need that DD. You need, instead of 4 electrical transmit and 4 electrical receive, you need 8. And the optical input and output there are already 400 gigabits per second. So 100 gigabits per wavelength or per fiber. There's a lot of work being done currently with mostly electronics, where you go from 50 gigabit electrical to 100 gigabit electrical. And that allows you then to reduce to half the number of electrical interfaces on that QSFP module. And then you can go back to the QSFP, that is then the QSFP 112. And then you can think, oh no, let's use the QSFP DD again, but let's double the aggregate data rate and go use the higher electrical interface in combination with the QSFP DD 8TX 8RX electrical to make an 800 gigabit per second module. So that is making things denser by improving the electrical interface. Another form factor besides the QSFP and the front pluggable modules are the embedded optical modules. And I will talk in the rest of my talk a bit more about those. we have as advantage that they can have a much smaller footprint, and hence you can have a higher bandwidth density. The electrical connections, there are many options, but here you see an example using a land grid array using an interposer. Of course, since the transceivers are getting much smaller and denser, the power dissipation doesn't scale the same, so you get more heat generation locally. So the power dissipation density is higher, and that needs to be dealt with. But luckily, the embedded optics modules allow more flexibility to design heat sinking, actually much more than a front pluggable module. Another advantage is that in the front panel, there's more space becoming free to let cooling air in. So that is in the system an advantage. But again, and that is a very important point, is the embedded optical modules are not front pluggable, so to replace them is much harder. So serviceability is harder, and hence reliability and performance is very important for those applications. So here you see an example of a product that we currently are in production with. This is a 4x100 gigabit per second embedded optical module. It is about 5 times smaller in footprint than 4 QSFP modules that it replaces. It has 16, therefore it has 16 channels of 25 gigabit per second, and it emulates exactly 4 QSFP 28 modules. So it has the same controls signals. It has the same optical interface. I mean, the optical performance is the same as a front pluggable module. It can exactly interoperate with front pluggable modules. So that is an example, and also the footprint is 5 times smaller. The engine of such a module, you can see that here. That's a silicon photonics chipset. So basically it has one large photonic chip, which is 25 millimeters by 9. That chip contains about 5,000 photonic devices on it. It also has 2 electronic chips made by TSMC, and that contains all the electronic functions like the drivers, TIA, CDRs, and so forth. It's also interesting to mention that the photonic IC is made by TSMC in Taiwan using their photonic process. And you see the other elements there are these little 4 boxes. Those are the micro packaged laser diodes. These are packages that contain the very standard DFB laser diodes with an optical isolator and coupling optics. So here you see the application. I have an example of that product in 2 applications. One of them is with Facebook. It is used in their photonic interface module, or PIM, for their mini-pack fabric switch for their data centers. In the picture, you see one of these mini-pack fabric switches with multiple PIMs in them. So you see the ones that look darker. Those are the ones with standard QSFP, and those in the center with the white connector plugs, those are the ones with the embedded optics modules. You see that there is, in the front plate, a lot more opening there to let cooling air in. So that is much better for the cooling than having these front pluggable modules. Each of those PIMs have 16 QSFPs, or 4 of those of our embedded optics modules. Facebook did a whole presentation on these embedded optics application in their data centers, and that was done at the OCP Global Summit a little bit more than a month ago. Another example you see there in a top of rack switch with Acton. You see there the picture. That is a 3.2 terabit top of rack. So there are 8 of those embedded optics modules in there. The height is the standard 1 RU. And it fulfills the same function as the front pluggable, as an implementation with front pluggable optics. Of course, it is already pre-assembled, so there is no need to plug modules in and out. And the data center customers can use it directly by installing that blade into their racks. Then there is another more futuristic point on the roadmap, that is where you don't have embedded optical modules, you use co-packaged optics. That is where you have an optical functionality co-packaged in a multi-chip module with the switch ASIC. And we see that that might be a solution for 51.2 terabit switches and above, because of the signal integrity, bringing the signals from the switch ASIC to the optical transceivers, if you have them outside, becomes very difficult. So the idea is then that we built a multi-chip module with all those chips, silicon photonics chips and electronic chips ASICs, with electrical interfaces and optical interfaces. The light source is external and is brought in with an optical fiber. So this brings us, like in the roadmap, you go from contemporary front pluggable modules that are going into plugged in the front of the switch system. We believe that this form factor will still stay because it's extremely easy to use. But as you can see, in some specific applications where the customers have specific needs, embedded optical modules are getting used more and more. There are multiple customers now asking for those. And ultimately, we see that co-packaged optics will be something for the future. There are a lot of technical challenges there, but we're already working on those so that we are ready when the need is there for the customers. That brings me to my summary slide. Looking at the technology, we definitely believe that more than 100 gigabits per lambda or per fiber intensity modulation direct detect will be feasible for intra-data center interconnect. We believe that 400 gigabit Ethernet, once it's introduced, will stay for a longer time. We think that 800 gigabit Ethernet is further out because of the investments made in 400 gigabit Ethernet, and we have to give a return on our investment. We believe, though, that there will be modules with more than 400 gigabit Ethernet, but there will be multiples of 100, 200, or 400, as I showed you an example. And we also believe that co-packaged optics will have the 400 gigabit Ethernet interface to be interoperable with the pluggable modules and with embedded optical modules. And we believe that silicon photonics in combination with suitable IC packaging technology will enable those high density optical transceivers that you've seen in some examples. It will enable co-packaging optics because we can leverage a lot from the semiconductor industry. And also, thanks to silicon photonics and the miniaturization of the photonic elements, we believe we can easily get higher than 100 gigabits per wavelength or per fiber. That's the end of my talk. I mean, there are many people contributing to this work, also not only within Cisco Luxtera, but also technology partners all over the world. And we want to thank them for their contributions. Thank you.
And we would like to thank you, Peter, for being here and also for being a role model for the world photonic industry. I have a few things I would like to discuss with you. The first one is you said that co-packaged optics is going to solve the 51.2 tera. If I speak in years, when this will become an issue? When do we think we'll implement the CPO?
Yeah, it will depend on a lot of factors that have to do with what the customers want and what their roadmap is. But I think 51 terabit switches could probably come 2023, 2025. It all depends on what the, I think first we have to go to the hurdle of the real introduction of 400 gigabit Ethernet. That is about to take off, but there's all the challenges for that. We have to work through that, and the customers have to work through that. And we are already preparing for the co-packaged optics, but when it will really occur, I think it's somewhat further out. I think 2025 or later even, because the challenges are large and the customers don't follow that fast. I mean, they're always promoting, you have to go quick to the new technology, but yeah, the reality is sometimes a little bit behind. But yeah, we see that as an important opportunity, and we're definitely looking into this technology.
I was amazed by your presentation, but you know how much I like what you do. So basically you had these 4 boxes there, these 4 beautiful boxes, and you told us these are DFB laser packaged very nicely in there. Are you controlling the temperature of the DFB lasers?
No. It's a CWDM application, so there you can allow a temperature drift of the wavelength of the lasers.
A few nanometers.
And the output power of the lasers, you have to have good lasers that perform well in the temperature range that the product is designed for. So usually that's 0 to 70 or -40 to +85.
So I have a lot of companies here who want to work with you, in the alignment and automation for manufacturing, in the testing. They want to work with you into incorporating new materials. You've been a star with us. It is so great to have you in the EPIC network, Peter. I hope that we meet soon, once again, in the normal circumstances, and we continue engaging you with the members of EPIC.
Okay, thank you.
Thank you very much, Peter. And now, oh my God, Carlos, and now we go to the last presentation of the day. And I thought I was going to be happy, but honestly, I'm not. I really am having an amazing day. I think I will remember this day for the rest of my life. And when Carlos was putting the program together, he thought there was no better person in the whole world to finish this in style than Michael Levy. Michael, thank you very much for closing this historical day in the history of EPIC. Thank you very much for taking the lead on being the last speaker on the 24 hours World Photonics Tour. The floor, the attention of everyone, and our friendship is yours.
Hey, thank you very much. This is like the old Le Mans, right? You know, the motor racing, where I think this is the first time I've ever seen any technical session last 24 hours. Photonics, we've had some fabulous talks from all over the world. I tuned in at 6 a.m. this morning, and it's 6:40 tonight, so it's 12 hours. It's only half the time you guys have put in, but it's been a brilliant show. So let's share the screen, and we'll get started. And I just want to make sure that you can see that.
We can see it.
And so today I'm going to talk about something new for microwave logic. And you can see in the title, there's 2 wavelengths, 1550 and 1310. And the long and the short of my presentation, just on one slide, is 1310 is brand new, never really happened before, because electro-optic polymers are always 1550. So let's get down into the details. And I'm going to give you a quick overview. We're a public company, and quick agenda. I'm going to talk about the environment, some of the technology. I'm going to finish with the photonics roadmap that I've worked with the Europeans and the Americans, just to give a nice overview. It's been a 24-hour event. Obviously, the roadmap's not going to cover everything, but I wanted to end with just a look into the future over the next decade, get a feel for how exciting photonics has become, and then just summarize. So in terms of the environment, from our standpoint, you know, we need to look at some of the pain points that are facing optical network operators. And so first of all, folks are really looking at how to get energy savings. Yes, we can go faster. We can do lots of things with our optical signals, and we've seen lots of that today. Energy is one of the biggest issues. I mean, big data centers, it's a big problem. People have to figure out how to get the power consumption down. Faster networks, clearly everybody wants to go faster. We've seen that time and time again today. And we've got to look at some engineering advantages. And for us, that's chemistry, that's electro-optic polymers. And so what we are trying to do is address some of the customer pain points. And so in order to do that, just a quick slide here is that we've really been amassing a lot of patents over the last 2 or 3 years. We've got over 50 now, but you can see all the way from materials chemistry to optical devices to packaging to photonic integration. And so that's something we take extremely seriously, especially when you're looking at optical polymers. And so what is it really that we have? We have electro-optic polymers. And what are those? They're internally engineered organic polymer materials they use less power, and they actually can increase the data throughput through existing network infrastructure. So really exciting stuff. Polymers, as everybody knows, has been around a long time, but we've actually now engineered these to be a lot more stable, a lot more reliable, and we're very happy with our progress. So I'm not going to go through all the words here because I am the last talk. I want to make sure there's time for questions. But the takeaway at the bottom of the slide is that our polymers enable faster devices and much lower power solutions today. And so what is it that we have at Lightwave Logic? We actually synthesize our own chromophores. And so we craft them with high electro-optic activity, and we pair them with host polymers. And they're chosen for the balance of stability and performance. That takes a lot of engineering, modeling, and design. And then we put them into a demonstrator, which is a Mach-Zehnder modulator, which is an optical device. And that's designed for internal and customer technology evaluation. And then we package them in high-speed pigtailed evaluation packages. And so what we are trying to do is put ourselves ready to partner with folks like transceiver companies, external partner applications for EO polymers that are in one-dimension, two-dimensional, and three-dimensional applications. And so this is where we think our strengths are, and we understand we can't do everything, but partnering and being a member with EPIC is going to allow us to think about those gray circles at the bottom of the slide. You have 500 members, you have plenty of folks that we think we can partner with down the road. So in terms of technology, what is polling of chromophore molecules all about? In fact, it's really similar to LCDs, just like we see in LCD televisions and displays, except we're using polymers. So we just pole with the voltage, we align all the dipoles, and that's really the electro-optic polymer engine. And it sounds really simple, it looks really simple, it works just like LCD technology, but it is difficult to engineer, I will give you that. But this is what we have been working on, that's what we have optimized over the years. And so we put those polymers into a Mach-Zehnder modulator, and you can put an optical input in, which is the green arrow, and you can get optical output with data with the green square wave with an RF electrical signal, which is in orange in the bottom left-hand side. And this is what we view as a polymer building block that switches light really fast with very low voltage. And just as a quick demonstration, we're already showing it in EO, S21, analog optical bandwidths greater than 70 gigahertz. And 70 gigahertz, if you really think about it, is 100 gigabits per second NRZ, or it's 200 gigabits per second PAM4. It basically is a very fast optical device. And so we're looking at taking the next technology node in speed for the optical networks. And we're looking to do that at very low voltage. And one of the critical things is, how do you get the voltage very low? Well, you've got to use the R33, which is the electro-optic efficiency of the polymer, and you have to get that very, very high, and you have to get that very stable. And this graph shows over time, for the last 3 years, the trend of the R33, the orange line is in the 1550 nanometers. And when I joined the company in 2016, we were running R33s, and a bunch of other companies were doing the same, about 50 to 60 picometers per volt. And you can see the latest data is we're actually nearly quadrupled that. So we're running 165, close to 200. And recently we put out a press release. We've now actually perfected our technology to work at 1310. And so that is really exciting for us. It means not only can we think about 1550 applications, we can now really look at the data center, the 1310, with force and with lots of excitement. And this is the thing that really drives low power, high performance EO polymers. And so, quick slide, faster devices, lower power, lower cost, robust and stable polymers. This radical innovation makes us differentiated, but really is essential for the fiber communications market. And if you look at the quick sort of view from spider charts, which is a classic way of looking at competitive technology, and what I've done here is I've plotted silicon photonics in blue, indium phosphide in green, lithium niobate in red. And clearly in spider charts, you want a wider cross-section of the diamond. And polymers, as you can see on the bottom, cover a wider cross-section of the diamond, which is really exciting. It means polymers are actually attractive. And so this slide is labeled competitive charts. But if we really think about the way polymers can work in these types of applications, this next slide really says it. Polymers are not really competitive, but they're additive to technology platforms. So in polymers, electro-optic polymers, you spin them on just like photoresist, and then you cure them. So that means you can put them onto indium phosphide, you can put them onto silicon photonics, and you can put them onto dielectric PLCs. So you can create interesting and exciting hybrid platforms. And this is something that we're really excited about. And so polymers are not really competitive to other platforms. They're additive. They actually allow other platforms to get more higher performance and lower power. So we see polymers as being a hybrid solution going forward. And that I think is really exciting. And then just to sort of end, a couple of slides here. One is I've been working with the INEMI and the AIM Photonics, and in Europe, the Photon Delta, to try and put roadmaps together. This is a photonics roadmap, looks out at PICs over the next 10 years. And there's a couple of trends here. You'll see an 800 gigabits per second, 1600 gigabits per second in that top red circle for modules and transceivers. You're seeing data rate densities of 100 terabits per second per 1 RU, which we just heard about in the last 2 or 3 talks. And then the lower circle there, you're seeing a lot of push towards PICs and OAICs with higher speed optical devices, lots of complicated coding and parallel schemes. But really the takeaway is that the photonics roadmap challenges the industry for faster, lower power devices and lots of photonic integration as we move forward over the next decade. And that's really, really exciting. And we see our technology fitting into that roadmap. And as you can see on the green column on the vertical, you've got things like indium phosphide monolithic, silicon photonics, hybrids, polymer photonics, dielectric photonics, and even gallium arsenide VCSELs that are used in structured light, as we heard from various companies earlier today. And so just to summarize, lightwave logic has EO polymers that certainly perform really nicely. We've got a world-class design team and facility in Colorado. We've certainly persisted where the other companies have really given up on EO polymers, and now seeing a little bit of resurgence in the academic community, which is exciting. We've got some great results, great powerful patent portfolio. And we see the polymers now solving customer headaches. So, they differentiate, they bring potential competitive advantage, and they're additive, which is really great. And so additive as a polymer building block, I think we're going to see some big impact. And so maybe lightwave logic polymers are the innovation the internet has been looking for. I certainly think so. And on that note, as the last speaker in the Photonics Le Mans, 24 hours, I hope I finished on a good note.
You did. You definitely did finish on a fantastic note. But of course, there is Q&A, there is discussion. The first part is the 70 gigahertz modulator. The 70 gigahertz modulator is like the golden fruit. It's the 100 gigabaud channel. So you have there Nokia with the plasmonics on one hand, and you have the people from the indium phosphide pushing. Then you have you with the polymers. Is that really the golden fruit? The 70 gigahertz is really the added value that polymer photonics has? Do you think, would you use this as the 30-second elevator pitch to convince the right person?
Yes, and the simple answer is the optical devices at some point have to go faster. They have to be lower power. Now, having said that, our industry has done a fantastic job of encoding schemes with PAM and QAM, and they've done really nice jobs to take a 35 gigahertz device, make it 50 gigabits per second NRZ, 100 gigabits per second, or 100 gigabaud PAM4, and they've worked really hard to try and get the voltage down. But really, and the other thing they've done is they've gone into parallel solutions to get the data rate up. And so I would say, yes, we're really innovative. And if we look back today, we've done some fantastic things with the 35, 40 gigahertz indium phosphide silicon photonics technology. But I think at some point we have to go to 70 gigahertz so we can do the 100 gig NRZ, the 200 gigabaud PAM4, and we can really push the speeds up at low power. So it has to happen. Now we can argue when it's going to happen, but I certainly see it at 400 gig and beyond. And that's why I'm really excited. So that's your 30-second slot.
No, but you guessed my next question. Your preferred future. When do the market need a 70 gigahertz modulator on chip?
I think the market would use something like this today. And I think the market is waiting for the next generation devices. In fact, if you look at indium phosphide and silicon photonics, and you look at some of the advanced development, people are trying to figure ways how to increase the speed. And we're sitting here with a technology that Mother Nature really works with us. And so that's what makes it exciting.
There is no better way of saying Mother Nature really works with us. Michael, this is fantastic. We have a question in the room from The Survivor. I call Greg Flynn The Survivor. You've been the longest from Europe in the room. Greg, what is on your mind?
Michael, hi, thanks for your talk. That roadmap, I imagine it's a work in progress, but is it in the public domain? Is it, are changes made to that roadmap also visible?
Yes, so the answer is yes. And part of the AIM Photonics and the Photon Delta, there was actually a meeting just a couple of weeks ago. Roadmaps are being updated all the time. That roadmap is public. I think if you go to either AIM Photonics or Photon Delta, you will be able to find a PDF, download it, take a look at it, but it is being updated. And it should be updated. I mean, these are working roadmaps, and they shouldn't be set in stone. They should be cognizant of what the industry is doing. And if other devices and other technologies do better, I mean, we've seen nice results from plasmonic modulators, slot modulators. I'm waiting to see how that all pans out. But certainly there's been some really nice results over the last year. So yes, absolutely, you can get your hands on it.
On that, I fully agree with you, Michael. I've been involved in the last 10 years in so many roadmaps, and I never reached the end of the road. It was always something that was constantly updated, and that's actually the trick. Is the idea of the roadmap is having an idea in which we all can elaborate and make it a better idea. So that's why EPIC is, it's working with so many roadmaps. I would like to have from Peter. I'm going to go to Peter Develer now from Cisco, because I would like to have your final idea on this. Peter, we are talking about the need of a 70 gigahertz modulator on chip. We are talking about the need to go to that direction towards perhaps the 200 gigabaud NRZ channel. Where do you stand on this? Where do you think the industry really demands 70 gigahertz modulators on chip?
As I said, I mean, currently in this, it will, I mean, we see that from the business standpoint when there will be a standard around that, when there will be mass adoption. And indeed, yeah, 400 gigabit per second, there the standards have pretty much concluded. And work has started on looking at what are the options to do 800 gigabit Ethernet. But as I said, we believe that will be, the introduction of that will be somewhat delayed because people won't have the return on investment on 400 gigabit, which is just now starting to roll out. So I expect that in the generation after the 51 terabit switch, that then there will definitely be a need for 200 gigabit per second per lambda or per fiber. And the work for that will be very hard. I mean, it's not only in the photonics world, you also have to have the electronic circuits that are driving them. That is not so simple. And we see that also the electrical interfaces need to be there. So it's more like an ecosystem that needs to be taken care of. You cannot have only a photonic device. You have to have all the rest that comes with it. And it's quite challenging. I mean, like the investments, I mean, if you want to drive just for now for 400 gigabit per second for such transceivers, you have to use very advanced electronic nodes just to drive the electronics with that. So it's not only the photonics, it's also the packaging, how you connect those devices. And it's also not only the modulator, it's the photodetector is also a huge pain. The bandwidth of the photodetector is actually also a big challenge. Also has to be 70
yes.
gigahertz. And
there you go. Michael, the final remark. Just let's finish this day strong. The final sentence, no pressure.
Final sentence, I mean, Peter is absolutely right. Just because you have faster devices doesn't mean you have the final solution. You need the eco-structure, you need the infrastructure, you need the complete photonics value chain supporting faster devices, lower power. And so I think the final comment is we can't do it on our own. We need to have partners. We need to work with trade associations like EPIC who have 500 plus members. And so this is the right forum to get these types of things completed. So thank you, guys.
Thank you very much. I cannot believe that we did it, we made it, and I actually enjoyed the last discussion so much that it felt so short. 24 hours of photonics, 72 speakers. I would like to first of all thank the EPIC team, all the people behind the scenes. You were fantastic. Everything couldn't have been done with all these hardworking people. The second, 72 speakers, all of them in time. Look at this time, all of them in time. That's crazy. I don't think this will ever happen again. I don't know what stars aligned today, but it's been a magical day. And the third, our families who support us, and Greg, who has been there like the rock star. We are going to finish right on time, 3 a.m., 24 hours sharp. Thank you very much for making history. Thank you for being EPIC. Thank you.
Thank you very much.
And thank you to the support team behind you guys.
Yeah.
Bye-bye.
Thank you.
Yep.
We did it. We're all waiting for this to say 3, right?
Oh, yeah.
There you go. Thank you very much. See you later. Bye-bye. See you.
Bye.
Ciao, ciao. Bye-bye.
Bye.
Incredible. See you. Thank you very much, Mike.